This is Audible.
A Short History of Nearly Everything by Bill Bryson. Read by William Roberts. Introduction. Welcome, and congratulations. I am delighted that you could make it. Getting here wasn't easy, I know. In fact, I suspect it was a little tougher than you realize. To begin with, for you to be here now, trillions of drifting atoms had somehow to assemble in an intricate and curiously obliging manner to create you. It's an arrangement so specialized and particular that it has never been tried before and will only exist this once. For the next many years, we hope, these tiny particles will uncomplainingly engage in all the billions of deft, cooperative efforts necessary to keep you intact, and let you experience the supremely agreeable, but generally underappreciated state known as existence. Why atoms take this trouble is a bit of a puzzle. Being you is not a gratifying experience at the atomic level. For all their devoted attention, your atoms don't actually care about you. Indeed, don't even know that you are there. They don't even know that they are there. They are mindless particles, after all, and not even themselves alive. It is a slightly arresting notion that if you were to pick yourself apart with tweezers, one atom at a time, you would produce a mound of fine atomic dust, none of which had ever been alive, but all of which had once been you. Yet somehow for the period of your existence they will answer to a single rigid impulse, to keep you, you. The bad news is that atoms are fickle, and their time of devotion is fleeting. Fleeting indeed. Even a long human life adds up to only about 650,000 hours, and when that modest milestone flashes into view, or at some other point thereabouts, for reasons unknown, your atoms will close you down, then silently disassemble and go off to be other things. And that's it for you. Still, you may rejoice that it happens at all. Generally speaking, in the universe, it doesn't, so far as we can tell. This is decidedly odd, because the atoms that so liberally and congenially flock together to form living things on Earth are exactly the same atoms that decline to do it elsewhere. Whatever else it may be, at the level of chemistry, life is fantastically mundane. Carbon, hydrogen, oxygen, and nitrogen, a little calcium, a dash of sulfur, a light dusting of other very ordinary elements, nothing you wouldn't find in any ordinary pharmacy, and that's all you need. The only thing special about the atoms that make you is that they make you. That is, of course, the miracle of life. Whether or not atoms make life in other corners of the universe, they make plenty else. Indeed, they make everything else. Without them, there would be no water, or air, or rocks, no stars and planets, no distant gassy clouds or swirling nebulae, or any of the other things that make the universe so agreeably material. Atoms are so numerous and necessary that we easily overlook that they needn't actually exist at all. There is no law that requires the universe to fill itself with small particles of matter, or to produce light and gravity and the other properties on which our existence hinges. There needn't actually be a universe at all. For a very long time there wasn't. There were no atoms and no universe for them to float about in. There was nothing. Nothing at all, anywhere. So thank goodness for atoms. But the fact that you have atoms and that they assemble in such a willing manner is only part of what got you here. To be here now, alive in the 21st century and smart enough to know it, you also had to be the beneficiary of an extraordinary string of biological good fortune. Survival on Earth is a surprisingly tricky business. Of the billions and billions of species of living thing that have existed since the dawn of time, most, 99.99%, it has been suggested, are no longer around. Life on Earth, you see, is not only brief, but dismayingly tenuous. It is a curious feature of our existence that we come from a planet that is very good at promoting life, but even better at extinguishing it. The average species on Earth lasts for only about 4 million years. So if you wish to be around for billions of years, you must be as fickle as the atoms that made you. You must be prepared to change everything about yourself: shape, size, color, species affiliation, everything, and to do so repeatedly. That's much easier said than done, because the process of change is random. To get from protoplasmal primordial atomic globule, as the Gilbert and Sullivan song put it, to sentient, upright, modern human has required you to mutate new traits over and over in a precisely timely manner for an exceedingly long while. So, at various periods over the last 3.8 billion years, you have abhorred oxygen and then doted on it, grown fins and limbs and jaunty sails, laid eggs, flicked the air with a forked tongue, been sleek, been furry, lived underground, lived in trees, been as big as a deer and as small as a mouse, and a million things more. The tiniest deviation from any of these evolutionary imperatives, and you might now be licking algae from cave walls, or lolling walrus-like on some stony shore, or disgorging air through a blowhole in the top of your head before diving 60 feet for a mouthful of delicious sandworms. Not only have you been lucky enough to be attached since time immemorial to a favored evolutionary line, but you have also been extremely, make that miraculously, fortunate in your personal ancestry. Consider the fact that for 3.8 billion years, a period of time older than the Earth's mountains and rivers and oceans, every one of your forebears on both sides has been attractive enough to find a mate, healthy enough to reproduce, and sufficiently blessed by fate and circumstances to live long enough to do so. Not one of your pertinent ancestors was squashed, devoured, drowned, starved, stuck fast, untimely wounded, or otherwise deflected from its life's quest of delivering a tiny charge of genetic material to the right partner at the right moment to perpetuate the only possible sequence of hereditary combinations that could result, eventually, astoundingly, and all too briefly, in you. This is a book about how it happened, in particular how we went from there being nothing at all to there being something, and then how a little of that something turned into us, and also some of what happened in between and since. That's rather a lot to cover, of course, which is why the book is called A Short History of Nearly Everything, even though it isn't really. It couldn't be. But with luck, by the time we finish, it may feel as if it is. My own starting point, for what it is worth, was a school science book that I had when I was in 4th or 5th grade. The book was a standard-issue 1950s school book, battered, unloved, grimly hefty. But near the front, it had an illustration that just captivated me. A cutaway diagram showing the Earth's interior as it would look if you cut into the planet with a large knife and carefully withdrew a wedge representing about a quarter of its bulk. It's hard to believe that there was ever a time when I had not seen such an illustration before, but evidently I had not, for I clearly remember being transfixed. I suspect in honesty my initial interest was based on a private image of streams of unsuspecting eastbound motorists in the American Plains states plunging over the edge of a sudden 4,000-mile-high cliff running between Central America and the North Pole. But gradually my attention did turn in a more scholarly manner to the scientific import of the drawing, and the realization that the Earth consisted of discrete layers, ending in the center with a glowing sphere of iron and nickel, which was as hot as the surface of the sun, according to the caption. And I remember thinking with real wonder, how do they know that? I didn't doubt the correctness of the information for an instant. I still tend to trust the pronouncements of scientists in the way I trust those of surgeons, plumbers, and other possessors of arcane and privileged information, but I couldn't, for the life of me, conceive how any human mind could work out what spaces thousands of miles below us, that no eye had ever seen and no X-ray could penetrate could look like and be made of. To me, that was just a miracle. That has been my position with science ever since. Excited, I took the book home that night and opened it before dinner, an action that I expect prompted my mother to feel my forehead and ask if I was all right. And, starting with the first page, I read. And here's the thing. It wasn't exciting at all. It wasn't actually altogether comprehensible. Above all, it didn't answer any of the questions that the illustration stirred up in a normal, inquiring mind. How did we end up with a sun in the middle of our planet? And how do they know how hot it is? And if it is burning away down there, why isn't the ground under our feet hot to the touch? And why isn't the rest of the interior melting? Or is it? And when the core at last burns itself out, will some of the earth slump into the void, leaving a giant sinkhole on the surface? And how do you know this? How did you figure it out? But the author was strangely silent on such details. Indeed, silent on everything but anticlines, synclines, axial faults, and the like. It was as if he wanted to keep the good stuff secret by making all of it soberly unfathomable. As the years passed, I began to suspect that this was not altogether a private impulse. There seemed to be a mystifying universal conspiracy among textbook authors to make certain the material they dealt with never strayed too near the realm of the mildly interesting, and was always at least a long-distance phone call from the frankly interesting. I now know that there is a happy abundance of science writers who pen the most lucid and thrilling prose. Timothy Ferris, Richard Fortey, and Tim Flannery are three that jump out from a single station of the alphabet, and that's not even to mention the late but godlike Richard Feynman. But sadly, none of them wrote any textbook I ever used. All mine were written by men, it was always men, who held the interesting notion that everything became clear when expressed as a formula, and the amusingly deluded belief that the children of America would appreciate having chapters end with a section of questions they could mull over in their own time. So I grew up convinced that science was supremely dull, but suspecting that it needn't be, and not really thinking about it at all if I could help it. This, too, became my position for a long time. Then, much later, about 4 or 5 years ago, I suppose, I was on a long flight across the Pacific, staring idly out the window at moonlit ocean, when it occurred to me with a certain uncomfortable forcefulness that I didn't know the first thing about the only planet I was ever going to live on. I had no idea, for example, why the oceans were salty, but the Great Lakes weren't. Didn't have the faintest idea. I didn't know if the oceans were growing more salty with time or less, and whether ocean salinity levels was something I should be concerned about or not. I am very pleased to tell you that until the late 1970s, scientists didn't know the answer to these questions either. They just didn't talk about it very audibly. And ocean salinity, of course, represented only the merest sliver of my ignorance. I didn't know what a proton was, or a protein, didn't know a quark from a quasar, didn't understand how geologists could look at a layer of rock on a canyon wall and tell you how old it was. Didn't know anything, really. I became gripped by a quiet, unwanted but insistent urge to know a little about these matters, and to understand above all how people figure them out. That, to me, remained the greatest of all amazements, how scientists work things out. How does anybody know how much the earth weighs, or how old its rocks are, or what really is way down there in the center? How can they know how and when the universe started, and what it was like when it did? How do they know what goes on inside an atom? And how, come to that, or perhaps above all on reflection, can scientists so often seem to know nearly everything, but then still not be able to predict an earthquake, or even tell us whether we should take an umbrella with us to the races next Wednesday? So I decided that I would devote a portion of my life, 3 years as it now turns out, to reading books and journals and finding saintly, patient experts prepared to answer a lot of outstandingly dumb questions. The idea was to see if it isn't possible to understand and appreciate, marvel at, enjoy even, the wonder and accomplishments of science at a level that isn't too technical or demanding, but isn't entirely superficial either. That was my idea and my hope, and that is what the book that follows is intended to do. Anyway, we have a great deal of ground to cover, and much less than 650,000 hours in which to do it, so let's begin. Part 1. Lost in the Cosmos. They're all in the same plane. They're all going around in the same direction. It's perfect, you know. It's gorgeous. It's almost uncanny. Astronomer Geoffrey Marcy, describing the solar system. Chapter 1. How to Build a Universe. No matter how hard you try, you will never be able to grasp just how tiny, how spatially unassuming is a proton. It is just way too small. A proton is an infinitesimal part of an atom, which is itself, of course, an insubstantial thing. Protons are so small that a little dib of ink like the dot on an I can hold something in the region of 500 billion of them, or rather more than the number of seconds it takes to make 500,000 years. So protons are exceedingly microscopic, to say the very least. Now imagine, if you can, and of course you can't, shrinking one of those protons down to 1/1000th of its normal size into a space so small that it would make a proton look enormous. Now pack into that tiny, tiny space about an ounce of matter. Excellent. You are ready to start a universe. I'm assuming, of course, that you wish to build an inflationary universe. If you'd prefer instead to build a more old-fashioned, standard Big Bang universe, you'll need additional materials. In fact, you will need to gather up everything there is, every last mote and particle of matter between here and the edge of creation, and squeeze it into a spot so infinitesimally compact that it has no dimensions at all. It is known as a singularity. In either case, get ready for a really big bang. Naturally, you will wish to retire to a safe place to observe the spectacle. Unfortunately, there is nowhere to retire to, because outside the singularity, there is no where. When the universe begins to expand, it won't be spreading out to fill a larger emptiness. The only space that exists is the space it creates as it goes. It is natural, but wrong, to visualize the singularity as a kind of pregnant dot hanging in a dark, boundless void. But there is no space, no darkness. The singularity has no around it. There is no space for it to occupy, no place for it to be. We can't even ask how long it has been there, whether it has just lately popped into being like a good idea, or whether it has been there forever, quietly awaiting the right moment. Time doesn't exist. There is no past for it to emerge from. And so, from nothing, our universe begins. In a single blinding pulse, a moment of glory much too swift and expansive for any form of words, the singularity assumes heavenly dimensions, space beyond conception. The first lively second, a second that many cosmologists will devote careers to shaving into ever finer wafers, produces gravity and the other forces that govern physics. In less than a minute, the universe is 1,000,000 billion miles across and growing fast. There is a lot of heat now, 10 billion degrees of it, enough to begin the nuclear reactions that create the lighter elements, principally hydrogen and helium, with a dash, about 1 atom in 100 million, of lithium. In 3 minutes, 98% of all the matter there is, or ever will be, has been produced. We have a universe. It is a place of the most wondrous and gratifying possibility, and beautiful too. and it was all done in about the time it takes to make a sandwich. When this moment happened is a matter of some debate. Cosmologists have long argued over whether the moment of creation was 10 billion years ago, or twice that, or something in between. The consensus seems to be heading for a figure of about 13.7 billion years, but these things are notoriously difficult to measure, as we shall see further on. All that can really be said is that at some indeterminate point in the very distant past, for reasons unknown, there came the moment known to science as T equals 0. We were on our way. There is, of course, a great deal we don't know, and much of what we think we know, we haven't known or thought we've known for long. Even the notion of the Big Bang is quite a recent one. The idea had been kicking around since the 1920s, when Georges Lemaitre, a Belgian priest-scholar, first tentatively proposed it. But it didn't really become an active notion in cosmology until the mid-1960s, when two young radio astronomers made an extraordinary and inadvertent discovery. Their names were Arno Penzias and Robert Wilson. In 1965, they were trying to make use of a large communications antenna owned by Bell Laboratories at Holmdel, New Jersey, but they were troubled by a persistent background noise, a steady, steamy hiss that made any experimental work impossible. The noise was unrelenting and unfocused. It came from every point in the sky, day and night, through every season. For a year, the young astronomers did everything they could think of to track down and eliminate the noise. They tested every electrical system. They rebuilt instruments, checked circuits, wiggled wires, dusted plugs. They climbed into the dish and placed duct tape over every seam and rivet. They climbed back into the dish with brooms and scrubbing brushes and carefully swept it clean of what they referred to in a later paper as white dielectric material, or what is known more commonly as bird shit. Nothing they tried worked. Unknown to them, just 50 kilometers away at Princeton University, a team of scientists led by Robert Dickey was working on how to find the very thing they were trying so diligently to get rid of. The Princeton researchers were pursuing an idea that had been suggested in the 1940s by the Russian-born astrophysicist George Gamow, that if you looked deep enough into space, you should find some cosmic background radiation left over from the Big Bang. Gamow calculated that by the time it had crossed the vastness of the cosmos, the radiation would reach Earth in the form of microwaves. In a more recent paper, he had even suggested an instrument that might do the job, the Bell antenna at Holmdel. Unfortunately, neither Penzias and Wilson nor any of the Princeton team had read Gamow's paper. The noise that Penzias and Wilson were hearing was, of course, the noise that Gamow had postulated. They had found the edge of the universe, or at least the visible part of it, 90 billion trillion miles away. They were seeing the first photons, the most ancient light in the universe, though time and distance had converted them to microwaves, just as Gamow had predicted. In his book, The Inflationary Universe, Alan Guth provides an analogy that helps to put this finding in perspective. If you think of peering into the depths of the universe as like looking down from the 100th floor of the Empire State Building, with the 100th floor representing now and street level representing the moment of the Big Bang, at the time of Wilson and Penzias' discovery, the most distant galaxies anyone had ever detected were on about the 60th floor, and the most distant things, quasars, were on about the 20th. Penzias and Wilson's finding pushed our acquaintance with the visible universe to within half an inch of the lobby floor. Still unaware of what caused the noise, Wilson and Penzias phoned Dickey at Princeton and described their problem to him in the hope that he might suggest a solution. Dickey realized at once what the two young men had found. "Well, boys, we've just been scooped," he told his colleagues as he hung up the phone. Soon afterwards, the Astrophysical Journal published 2 articles, one by Penzias and Wilson, describing their experience with a hiss, the other by Dickey's team explaining its nature. Although Penzias and Wilson had not been looking for cosmic background radiation, didn't know what it was when they had found it, and hadn't described or interpreted its character in any paper, they received the 1978 Nobel Prize in Physics. The Princeton researchers got only sympathy. According to Dennis Overby in Lonely Hearts of the Cosmos, neither Penzias nor Wilson altogether understood the significance of what they had found, until they read about it in the New York Times. Incidentally, disturbance from cosmic background radiation is something we have all experienced. Tune your television to any channel it doesn't receive, and about 1% of the dancing static you see is accounted for by this ancient remnant of the Big Bang. The next time you complain that there is nothing on, remember that you can always watch the birth of the universe. Although everyone calls it the Big Bang, many books caution us not to think of it as an explosion in the conventional sense. It was rather a vast sudden expansion on a whopping scale. So what caused it? One notion is that perhaps the singularity was the relic of an earlier collapsed universe, that ours is just one of an eternal cycle of expanding and collapsing universes, like the bladder on an oxygen machine. Others attribute the Big Bang to what they call a false vacuum, or a scalar field, or vacuum energy, some quality or thing, at any rate, that introduced a measure of instability into the nothingness that was. It seems impossible that you could get something from nothing. But the fact that once there was nothing and now there is a universe is evident proof that you can. It may be that our universe is merely part of many larger universes, some in different dimensions, and that Big Bangs are going on all the time all over the place. Or it may be that space and time had some other forms altogether before the Big Bang, forms too alien for us to imagine, and that the Big Bang represents some sort of transition phase, where the universe went from a form we can't understand to one we almost can. These are very close to religious questions, Dr. Andre Linde, a cosmologist at Stanford, told the New York Times in 2001. The Big Bang theory isn't about the bang itself, but about what happened after the bang. Not long after, mind you. By doing a lot of maths and watching carefully what goes on in particle accelerators, scientists believe they can look back to 10 to the minus 43rd seconds after the moment of creation, when the universe was still so small that you would have needed a microscope to find it. And we mustn't swoon over every extraordinary number that comes before us, but it is perhaps worth latching on to one from time to time just to be reminded of their ungraspable and amazing breadth. Thus, 10 to the minus 43rd is
0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000
of a second. Most of what we know, or believe we know, about the early moments of the universe is thanks to an idea called inflation theory, first propounded in 1979 by a junior particle physicist then at Stanford, now at MIT, named Alan Guth. He was 32 years old, and by his own admission had never done anything much before. He would probably never have had his great theory except that he happened to attend a lecture on the Big Bang given by none other than Robert Dicke. The lecture inspired Guth to take an interest in cosmology, and in particular in the birth of the universe. The eventual result was the inflation theory, which holds that a fraction of a moment after the dawn of creation, the universe underwent a sudden, dramatic expansion. It inflated, in effect ran away with itself, doubling in size every 10 to the minus 34th seconds. The whole episode may have lasted no more than 10 to the minus 30th seconds. That's 1,000,000,000,000,000 millionths of a second. But it changed the universe from something you could hold in your hand to something at least 10 trillion times bigger. Inflation theory explains the ripples and eddies that make our universe possible. Without it, there would be no clumps of matter, and thus no stars, just drifting gas and everlasting darkness. According to Guth's theory, at 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second, gravity emerged. After another ludicrously brief interval, it was joined by electromagnetism and the strong and weak nuclear forces, the stuff of physics. These were joined an instant later by shoals of elementary particles, the stuff of stuff. From nothing at all, suddenly there were swarms of photons, protons, electrons, neutrons, and much else, between 10 to the 79th and 10 to the 89th of each, according to the standard Big Bang theory. Such quantities are, of course, ungraspable. It is enough to know that in a single cracking instant, we were endowed with a universe that was vast, at least 100 billion light-years across, according to the theory, but possibly any size up to infinite, and perfectly arrayed for the creation of stars, galaxies, and other complex systems. What is extraordinary from our point of view is how well it turned out for us. If the universe had formed just a tiny bit differently, if gravity were fractionally stronger or weaker, if the expansion had proceeded just a little more slowly or swiftly, then there might never have been stable elements to make you and me and the ground we stand on. Had gravity been a trifle stronger, the universe itself might have collapsed, like a badly erected tent, without precisely the right values to give it the necessary dimensions and density and component parts. Had it been weaker, however, nothing would have coalesced. The universe would have remained forever a dull, scattered void. This is one reason why some experts believe that there may have been many other Big Bangs, perhaps trillions and trillions of them, spread through the mighty span of eternity, and that the reason we exist in this particular one is that this is the one that we could exist in. As Edward P. Tryon of Columbia University once put it, in answer to the question of why it happened, I offer the modest proposal that our universe is simply one of those things which happen from time to time. To which adds Guth, although the creation of a universe might be very unlikely, Tryon emphasized that no one had counted the failed attempts. Martin Rees, Britain's Astronomer Royal, believes that there are many universes, possibly an infinite number, each with different attributes and different combinations, and that we simply live in one that combines things in the way that allows us to exist. He makes an analogy with a very large clothing store. If there is a large stock of clothing, you're not surprised to find a suit that fits. If there are many universes, each governed by a differing set of numbers, there will be one where there is a particular set of numbers suitable to life. We are in that one. Rees maintains that 6 numbers in particular govern our universe, and that if any of these values were changed even very slightly, things could not be as they are. For example, for the universe to exist as it does requires that hydrogen be converted to helium in a precise but comparatively stately manner, specifically in a way that converts 7/1000ths of its mass to energy. Lower that value very slightly, from 0.007% to 0.006%, say, and no transformation could take place. The universe would consist of hydrogen and nothing else. Raise the value very slightly to 0.008%, and bonding would be so wildly prolific that the hydrogen would long since have been exhausted. In either case, with the slightest tweaking of the numbers, the universe as we know and need it would not be here. I should say that everything is just right so far. In the long term, gravity may turn out to be a little too strong. One day it may halt the expansion of the universe and bring it collapsing in upon itself until it crushes itself down into another singularity, possibly to start the whole process over again. On the other hand, it may be too weak, in which case the universe will keep racing away forever until everything is so far apart that there is no chance of material interactions, so that the universe becomes a place that is very roomy, but inert and dead. The third option is that gravity is perfectly pitched. Critical density is the cosmologist's term for it, and that it will hold the universe together at just the right dimensions to allow things to go on indefinitely. Cosmologists in their lighter moments sometimes call this the Goldilocks effect, that everything is just right. For the record, these three possible universes are known respectively as closed, open, and flat. Now, the question that has occurred to all of us at some point is, what would happen if you traveled out to the edge of the universe and, as it were, put your head through the curtains? Where would your head be if it were no longer in the universe? What would you find beyond? The answer, disappointingly, is that you can never get to the edge of the universe. That's not because it would take too long to get there, though of course it would, but because even if you traveled outward and outward in a straight line indefinitely and pugnaciously, you would never arrive at an outer boundary. Instead, you would come back to where you began, at which point, presumably, you would rather lose heart in the exercise and give up. The reason for this is that the universe bends in a way we can't adequately imagine, in conformance with Einstein's theory of relativity, which we will get to in due course. For the moment, it is enough to know that we are not adrift in some large, ever-expanding bubble. Rather, space curves in a way that allows it to be boundless but finite. Space cannot even properly be said to be expanding, because, as the physicist and Nobel laureate Steven Weinberg notes, solar systems and galaxies are not expanding, and space itself is not expanding. Rather, the galaxies are rushing apart. It is all something of a challenge to intuition. Or, as the biologist J.B.S. Haldane once famously observed, the universe is not only queerer than we suppose, it is queerer than we can suppose. The analogy that is usually given for explaining the curvature of space is to try to imagine someone from a universe of flat surfaces who had never seen a sphere being brought to Earth. No matter how far he roamed across the planet's surface, he would never find an edge. He might eventually return to the spot where he had started, and would of course be utterly confounded to explain how that had happened. Well, we are in the same position in space as our puzzled flatlander, only we are flummoxed by a higher dimension. Just as there is no place where you can find the edge of the universe, so there is no place where you can stand at the center and say, this is where it all began, this is the centermost point of it all. We are all at the center of it all. Actually, we don't know that for sure. We can't prove it mathematically. Scientists just assume that we can't really be the center of the universe. Think what that would imply. But that the phenomenon must be the same for all observers in all places. Still, we don't actually know. For us, the universe goes only as far as light has traveled in the billions of years since the universe was formed. This visible universe, the universe we know and can talk about, is 1,000,000,000,000,000,000 miles across. But according to most theories, the universe at large, the meta-universe, as it is sometimes called, is vastly roomier still. According to Rees, the number of light years to the edge of this larger, unseen universe would be written not with 10 zeros, not even with 100, but with millions. In short, there's more space than you can imagine already without going to the trouble of trying to envision some additional beyond. For a long time, the Big Bang Theory had one gaping hole that troubled a lot of people, namely that it couldn't begin to explain how we got here. Although 98% of all the matter that exists was created with a Big Bang, that matter consisted exclusively of light gases, the helium, hydrogen, and lithium that we mentioned earlier. Not one particle of the heavy stuff, so vital to our own being, carbon, nitrogen, oxygen, and all the rest, emerged from the gaseous brew of creation. But, And here's the troubling point. To forge these heavy elements, you need the kind of heat and energy thrown off by a Big Bang. Yet, there has been only one Big Bang, and it didn't produce them. So where did they come from? Interestingly, the man who found the answer to that question was a cosmologist who heartily despised the Big Bang as a theory, and coined the term Big Bang sarcastically as a way of mocking it. We'll get to him shortly, but before we turn to the question of how we got here, it might be worth taking a few minutes to consider just where exactly here is. Chapter 2. Welcome to the Solar System. Astronomers these days can do the most amazing things. If someone struck a match on the moon, they could spot the flare. From the tiniest throbs and wobbles of distant stars, they can infer the size and character, and even potential habitability of planets much too remote to be seen. Planets so distant that it would take us 500,000 years in a spaceship to get there. With their radio telescopes, they can capture wisps of radiation so preposterously faint that the total amount of energy collected from outside the solar system by all of them together since collecting began in 1951 is less than the energy of a single snowflake striking the ground, in the words of Carl Sagan. In short, there isn't a great deal that goes on in the universe that astronomers can't find when they have a mind to. Which is why it is all the more remarkable to reflect that until 1978 no one had ever noticed that Pluto has a moon. In the summer of that year, a young astronomer named James Christie at the U.S. Naval Observatory in Flagstaff, Arizona, was making a routine examination of photographic images of Pluto when he saw that there was something there, something blurry and uncertain, but definitely other than Pluto. Consulting a colleague named Robert Harrington, he concluded that what he was looking at was a moon. And it wasn't just any moon. Relative to the planet, it was the biggest moon in the solar system. This was actually something of a blow to Pluto's status as a planet, which had never been terribly robust anyway. Since previously the space occupied by the moon and the space occupied by Pluto were thought to be one and the same, it meant that Pluto was much smaller than anyone had supposed, smaller even than Mercury. Indeed, 7 moons in the solar system, including our own, are larger. Now, a natural question is why it took so long for anyone to find a moon in our own solar system. The answer is that it is partly a matter of where astronomers point their instruments, and partly a matter of what their instruments are designed to detect, and partly it's just Pluto. Mostly it's where they point their instruments. In the words of the astronomer Clark Chapman, most people think that astronomers get out at night in observatories and scan the skies. That's not true. Almost all the telescopes we have in the world are designed to peer at very tiny little pieces of the sky, way off in the distance, to see a quasar or hunt for black holes or look at a distant galaxy. The only real network of telescopes that scans the skies has been designed and built by the military. We have been spoiled by artists' renderings into imagining a clarity of resolution that doesn't exist in actual astronomy. Pluto, in Christie's photograph, is faint and fuzzy, a piece of cosmic lint. And its moon is not the romantically backlit, crisply delineated companion orb you would get in a National Geographic painting, but rather just a tiny and extremely indistinct hint of additional fuzziness. Such was the fuzziness, in fact, that it took 7 years for anyone to spot the moon again, and thus independently confirm its existence. One nice touch about Christie's discovery was that it happened in Flagstaff, for it was there in 1930 that Pluto had been found in the first place. That seminal event in astronomy was largely to the credit of the astronomer Percival Lowell. Lowell, who came from one of the oldest and wealthiest Boston families, the one in the famous ditty about Boston being the home of the bean and the cod, where Lowell spoke only to Cabots, while Cabot spoke only to God, endowed the famous observatory that bears his name, but is most indelibly remembered for his belief that Mars was covered with canals, built by industrious Martians, for purposes of conveying water from polar regions to the dry but productive lands nearer the equator. Lowell's other abiding conviction was that there existed, somewhere out beyond Neptune, an undiscovered ninth planet, dubbed Planet X. Lowell based this belief on irregularities he detected in the orbits of Uranus and Neptune, and devoted the last years of his life to trying to find the gassy giant he was certain was out there. Unfortunately, he died suddenly in 1916. At least partly exhausted by his quest, and the search fell into abeyance while Lowell's heirs squabbled over his estate. However, in 1929, partly as a way of deflecting attention away from the Mars Canal saga, which by now had become a serious embarrassment, the Lowell Observatory directors decided to resume the search and, to that end, hired a young man from Kansas named Clyde Tombaugh. Tombaugh had no formal training as an astronomer, but he was diligent, and he was astute, and after a year's patient searching, he somehow spotted Pluto, a faint point of light in a glittery firmament. It was a miraculous find, and what made it all the more striking was that the observations on which Lowell had predicted the existence of a planet beyond Neptune proved to be comprehensively erroneous. Tombaugh could see at once that the new planet was nothing like the massive gas ball Lowell had postulated. But any reservations he or anyone else had about the character of the new planet were soon swept aside in the delirium that attended almost any big news story in that easily excited age. This was the first American-discovered planet, and no one was going to be distracted by the thought that it was really just a distant icy dot. It was named Pluto, at least partly because the first two letters made a monogram from Lowell's initials. Lowell was posthumously hailed everywhere as a genius of the first order, and Tombaugh was largely forgotten, except among planetary astronomers, who tend to revere him. A few astronomers continue to think that there may yet be a Planet X out there, a real whopper, perhaps as much as 10 times the size of Jupiter, but so far out as to be invisible to us. It would receive so little sunlight that it would have almost none to reflect. The idea is that it wouldn't be a conventional planet like Jupiter or Saturn. It's much too far away for that. We're talking perhaps 4.5 trillion miles. But more like a sun that never quite made it. Most star systems in the cosmos are binary, double-starred, which makes our solitary sun a slight oddity. As for Pluto itself, nobody is quite sure how big it is, what it is made of, what kind of atmosphere it has, or even what it really is. A lot of astronomers believe it isn't a planet at all, but merely the largest object so far found in a zone of galactic debris known as the Kuiper Belt. The Kuiper Belt was actually theorized by an astronomer named F.C. Leonard in 1930, but the name honors Gerard Kuiper, a Dutch native working in America who expanded the idea. The Kuiper Belt is the source of what are known as short-period comets, those that come past pretty regularly, of which the most famous is Halley's Comet. The more reclusive long-period comets, among them the recent visitors Hale-Bopp and Yakwataki, come from the much more distant Oort cloud, about which more presently. It is certainly true that Pluto doesn't act much like the other planets. Not only is it runty and obscure, it is so variable in its motions that no one can tell you exactly where Pluto will be a century hence. Whereas the other planets orbit on more or less the same plane, Pluto's orbital path is tipped, as it were, out of alignment, at an angle of 17 degrees, like the brim of a hat tilted rakishly on someone's head. Its orbit is so irregular that for substantial periods on each of its lonely circuits around the Sun, it is closer to us than Neptune is. For most of the 1980s and 1990s, Neptune was in fact the solar system's most far-flung planet. Only on 11 February 1999 did Pluto return to the outside lane, there to remain for the next 228 years. So if Pluto really is a planet, it is certainly an odd one. It is very tiny, just 1/4% as massive as Earth. If you set it down on top of the United States, it would cover not quite half the lower 48 states. This alone makes it extremely anomalous. It means that our planetary system consists of 4 rocky inner planets, 4 gassy outer giants, and a tiny solitary ice ball. Moreover, there is every reason to suppose that we may soon begin to find other, even larger icy spheres in the same portion of space. Then we will have problems. After Christie spotted Pluto's moon, astronomers began to regard that section of the cosmos more attentively, and as of early December 2002, had found over 600 additional trans-Neptunian objects, or Plutinos, as they are alternatively called. One, dubbed Varuna, is nearly as big as Pluto's moon. Astronomers now think there may be billions of these objects. The difficulty is that many of them are awfully dark. Typically, they have an albedo, or reflectiveness, of just 4%, about the same as a lump of charcoal. And of course, these lumps of charcoal are over 6 billion kilometers away. And how far is that, exactly? It's almost beyond imagining. Space, you see, is just enormous. Just enormous. Let's imagine, for purposes of edification and entertainment, that we're about to go on a journey by rocket ship. We won't go terribly far, just to the edge of our own solar system, but we need to get a fix on how big a place space is and what a small part of it we occupy. Now, the bad news, I'm afraid, is that we won't be home for supper. Even at the speed of light, 300,000 kilometers per second, it would take 7 hours to get to Pluto. But of course, we can't travel at anything like that speed. We'll have to go at the speed of a spaceship, and these are rather more lumbering. The best speeds yet achieved by any human object are those of the Voyager 1 and 2 spacecrafts, which are now flying away from us at about 56,000 kilometers an hour. The reason the Voyager craft were launched when they were, in August and September 1977, was that Jupiter, Saturn, Uranus, and Neptune were aligned in a way that happens only once every 175 years. This enabled the 2 Voyagers to use a gravity assist technique, in which the craft were successively flung from one gassy giant to the next in a kind of cosmic version of Crack the Whip. Even so, it took them 9 years to reach Uranus and a dozen to cross the orbit of Pluto. The good news is that if we wait until January 2006, which is when NASA's New Horizons spacecraft is tentatively scheduled to depart for Pluto, we can take advantage of favorable Jovian positioning, plus some advances in technology, and get there in only a decade or so. Though getting home again will take rather longer, I'm afraid. At all events, it's going to be a long trip. Now, the first thing you are likely to realize is that space is extremely well named and rather dismayingly uneventful. Our solar system may be the liveliest thing for trillions of miles, but all the visible stuff in it, the sun, the planets and their moons, the billion or so tumbling rocks of the asteroid belt, comets and other miscellaneous drifting detritus, fills less than a trillionth of the available space. You also quickly realize that none of the maps you have ever seen of the solar system was drawn remotely to scale. Most schoolroom charts show the planets coming one after the other at neighborly intervals. The outer giants actually cast shadows over each other in many illustrations. But this is a necessary deceit to get them all in the same piece of paper. Neptune in reality isn't just a little bit beyond Jupiter, it's way beyond Jupiter. 5 times further from Jupiter than Jupiter is from us. So far out that it receives only 3% as much sunlight as Jupiter. Such are the distances, in fact, that it isn't possible in any practical terms to draw the solar system to scale. Even if you added lots of fold-out pages to your textbooks or used a really long sheet of poster paper, you wouldn't come close. On a diagram of the solar system to scale, with the Earth reduced to about the diameter of a pea, Jupiter would be over 300 meters away, and Pluto would be 2.5 kilometers distant, and about the size of a bacterium, so you wouldn't be able to see it anyway. On the same scale, Proxima Centauri, our nearest star, would be 16,000 kilometers away. Even if you shrank down everything so that Jupiter was as small as the full stop at the end of a sentence and Pluto was no bigger than a molecule, Pluto would still be over 10 meters away. So the solar system is really quite enormous. By the time we reach Pluto, we have come so far that the Sun, our dear, warm, skin-tanning, life-giving Sun, has shrunk to the size of a pinhead. It is little more than a bright star. In such a lonely voyage you can begin to understand how even the most significant objects, Pluto's moon, for example, have escaped attention. In this respect, Pluto has hardly been alone. Until the Voyager expeditions, Neptune was thought to have 2 moons. Voyager found 6 more. When I was a boy, the solar system was thought to contain 30 moons. The total now is at least 90, about a third of which have been found in just the last 10 years. The point to remember, of course, when considering the universe at large, is that we don't actually know what is in our own solar system. Now, the other thing you will notice as we speed past Pluto is that we are speeding past Pluto. If you check your itinerary, you will see that this is a trip to the edge of our solar system, and I'm afraid we're not there yet. Pluto may be the last object marked on schoolroom charts, but the system doesn't end there. In fact, it isn't even close to ending there. We won't get to the solar system's edge until we have passed through the Oort cloud, a vast celestial realm of drifting comets, and we won't reach the Oort cloud for another, I'm so sorry about this, 10,000 years. Far from marking the outer edge of the solar system as those schoolroom maps so cavalierly imply, Pluto is barely 1/50,000th of the way. Of course, we have no prospect of such a journey. A trip of 386,000 kilometers to the moon still represents a very big undertaking for us. A manned mission to Mars, called for by the first President Bush in a moment of passing giddiness, was quietly dropped when someone worked out that it would cost $450 billion and probably result in the deaths of all the crew, their DNA torn to tatters by high-energy solar particles from which they could not be shielded. Based on what we know now, and can reasonably imagine, there is absolutely no prospect that any human being will ever visit the edge of our own solar system. Ever. It is just too far. As it is, even with a Hubble telescope, we can't see even into the Oort cloud, so we don't actually know that it is there. Its existence is probable, but entirely hypothetical. About all that can be said with confidence about the Oort cloud is that it starts somewhere beyond Pluto and stretches some 2 light-years out into the cosmos. The basic unit of measure in the solar system is the astronomical unit, or AU, representing the distance from the Sun to the Earth. Pluto is about 40 AUs from us, the heart of the Oort cloud about 50,000. In a word, it is remote. But let's pretend again that we have made it to the Oort cloud. The first thing you might notice is how very peaceful it is out here. We're a long way from anywhere now, so far from our own sun that it's not even the brightest star in the sky. It is a remarkable thought that that distant, tiny twinkle has enough gravity to hold all these comets in orbit. It's not a very strong bond, so the comets drift in a stately manner, moving at only about 220 miles an hour. From time to time, one of these lonely comets is nudged out of its normal orbit by some slight gravitational perturbation, a passing star, perhaps. Sometimes they are ejected into the emptiness of space, never to be seen again. But sometimes they fall into a long orbit around the sun. About 3 or 4 of these a year, known as long-period comets, pass through the inner solar system. Just occasionally, these stray visitors smack into something solid, like Earth. That's why we've come out here now, because the comet we have come to see has just begun a long fall towards the center of the solar system. It's headed for, of all places, Manson, Iowa. It's going to take a long time to get there, 3 or 4 million years at least. So we'll leave it for now, and return to it much later in the story. So that's your solar system. And what else is out there beyond the solar system? Well, nothing. And a great deal, depending on how you look at it. In the short term, it's nothing. The most perfect vacuum ever created by humans is not as empty as the emptiness of interstellar space. And there is a great deal of this nothingness until you get to the next bit of something. Our nearest neighbor in the cosmos, Proxima Centauri, which is part of the 3-star cluster known as Alpha Centauri, is 4.3 light-years away, a sissy skip in galactic terms, but still 100 million times further than a trip to the moon. To reach it by spaceship would take at least 25,000 years. And even if you made the trip, you still wouldn't be anywhere except at a lonely clutch of stars in the middle of a vast nowhere. To reach the next landmark of consequence, Sirius, would involve another 4.6 light-years of travel, and so it would go if you tried to star-hop your way across the cosmos. Just reaching the center of our own galaxy would take far longer than we have existed as beings. Space, let me repeat, is enormous. The average distance between stars out there is over 30 million kilometers. Even at speeds approaching those of light, these are fantastically challenging distances for any traveling individual. Of course, it's possible that alien beings travel billions of miles to amuse themselves by planting crop circles in Wiltshire or frightening the daylights out of some poor guy in a pickup truck on a lonely road in Arizona. They must have teenagers after all. But it does seem unlikely. Still, statistically, the probability that there are other thinking beings out there is good. Nobody knows how many stars there are in the Milky Way. Estimates range from 100 billion or so to perhaps 400 billion, and the Milky Way is just one of 140 billion or so other galaxies, many of them even larger than ours. In the 1960s, a professor at Cornell named Frank Drake, excited by such whopping numbers, worked out a famous equation designed to calculate the chances of advanced life existing in the cosmos, based on a series of diminishing probabilities. Under Drake's equation, you divide the number of stars in a selected portion of the universe by the number of stars that are likely to have planetary systems. Divide that by the number of planetary systems that could theoretically support life. Divide that by the number on which life, having arisen, advances to a state of intelligence, and so on. At each such division, the number shrinks colossally. Yet even with the most conservative inputs, the number of advanced civilizations just in the Milky Way always works out to be somewhere in the millions. What an interesting and exciting thought. We may be only one of millions of advanced civilizations. Unfortunately, space being spacious, the average distance between any two of these civilizations is reckoned to be at least 200 light-years. Which is a great deal more than merely saying it makes it sound. It means, for a start, that even if these beings know we are here and are somehow able to see us in their telescopes, they're watching light that left Earth 200 years ago. So they're not seeing you and me. They're watching the French Revolution, and Thomas Jefferson, and people in silk stockings and powdered wigs, people who don't know what an atom is or a gene, and who make their electricity by rubbing a rod of amber with a piece of fur and think that's quite a trick. Any message we receive from these observers is likely to begin, "Dear Sire," and congratulate us on the handsomeness of our horses and our mastery of whale oil. 200 light years is a distance so far beyond us as to be, well, just beyond us. So even if we are not really alone, in all practical terms, we are. Carl Sagan calculated the number of probable planets in the universe at as many as 10 billion trillion, a number vastly beyond imagining. But what is equally beyond imagining is the amount of space through which they are lightly scattered. If we were randomly inserted into the universe, Sagan wrote, the chances that you would be on or near a planet would be less than 1 in a billion trillion trillion. That's 10 to the 33rd, or 1 followed by 33 zeros. Worlds are precious. Which is why perhaps it is good news that in February 1999 the International Astronomical Union ruled officially that Pluto is a planet. The universe is a big and lonely place. We can do with all the neighbors we can get. We can get. Chapter 3. The Reverend Evans's Universe. When the skies are clear and the moon is not too bright, the Reverend Robert Evans, a quiet and cheerful man, lugs a bulky telescope onto the back sundeck of his home in the Blue Mountains of Australia, about 80 kilometres west of Sydney, and does an extraordinary thing. He looks deep into the past and finds dying stars. Looking into the past is, of course, the easy part. Glance at the night sky, and what you see is history, and lots of it. Not the stars as they are now, but as they were when their light left them. For all we know, the North Star, our faithful companion, might actually have burned out last January, or in 1854, or at any time since the early 14th century, and news of it just hasn't reached us yet. The best we can ever say, is that it was still burning on this date 680 years ago. Stars die all the time. What Bob Evans does better than anyone else who has ever tried is spot these moments of celestial farewell. By day, Evans is a kindly and now semi-retired minister in the Uniting Church in Australia, who does a bit of locum work and researches the history of 19th century religious movements. But by night, he is, in his unassuming way, a titan of the skies. He hunts supernovae. A supernova occurs when a giant star, one much bigger than our own sun, collapses and then spectacularly explodes, releasing in an instant the energy of 100 billion suns, burning for a time more brightly than all the stars in its galaxy. It's like 1 trillion hydrogen bombs going off at once, says Evans. If a supernova explosion happened within 500 light years of us, we would be goners, according to Evans. It would wreck the show, as he cheerfully puts it. But the universe is vast, and supernovae are normally much too far away to harm us. In fact, most are so unimaginably distant that their light reaches us as no more than the faintest twinkle. For the month or so that they are visible, all that distinguishes them from the other stars in the sky is that they occupy a point of space that wasn't filled before. It is these anomalous, very occasional pricks in the crowded dome of the night sky that the Reverend Evans finds. To understand what a feat this is, imagine a standard dining room table covered in a black tablecloth and throwing a handful of salt across it. The scattered grains can be thought of as a galaxy. Now imagine 1,500 more tables like the first one, enough to make a single line 2 miles long, each with a random array of salt across it. Now add 1 grain of salt to any table, and let Bob Evans walk among them. At a glance he will spot it. That grain of salt is the supernova. Evans's is a talent so exceptional that Oliver Sacks, in An Anthropologist on Mars, devotes a passage to him in a chapter on autistic savants, quickly adding that there is no suggestion that he is autistic. Evans, who has not met Sacks, laughs at the suggestion that he might be either autistic or a savant, but he is powerless to explain quite where his talent comes from. "I just seem to have a knack for memorizing star fields," he told me, with a frankly apologetic look, when I visited him and his wife Elaine in their picture-book bungalow on a tranquil edge of the village of Hazelbrook, out where Sydney finally ends and the boundless Australian bush begins. "I'm not particularly good at other things," he added. "I don't remember names well." "Or where he's put things," called Elaine from the kitchen. He nodded frankly again and grinned, then asked me if I'd like to see his telescope. I had imagined that Evans would have a proper observatory in his backyard, a scaled-down version of a Mount Wilson or Palomar, with a sliding domed roof and a mechanized chair that would be a pleasure to maneuver. In fact, he led me not outside, but to a crowded storeroom off the kitchen, where he keeps his books and papers, and where his telescope, a white cylinder that is about the size and shape of a household hot water tank, rests in a homemade swiveling plywood mount. When he wishes to observe, he carries them in 2 trips to a small sundeck off the kitchen. Between the overhang of the roof and the feathery tops of eucalyptus trees growing up from the slope below, he has only a letterbox view of the sky, but he says it is more than good enough for his purposes. And there, when the skies are clear and the moon is not too bright, he finds his supernovae. The term supernova was coined in the 1930s by a memorably odd astrophysicist named Fritz Zwicky. Born in Bulgaria and raised in Switzerland, Zwicky came to the California Institute of Technology in the 1920s, and there at once distinguished himself by his abrasive personality and erratic talents. He didn't seem to be outstandingly bright, and many of his colleagues considered him little more than an irritating buffoon. A fitness fanatic, he would often drop to the floor of the Caltech dining hall or some other public area and do one-armed push-ups to demonstrate his virility to anyone who seemed inclined to doubt it. He was notoriously aggressive, his manner eventually becoming so intimidating that his closest collaborator, a gentleman named Walter Bade, refused to be left alone with him. Among other things, Zwicky accused Bade, who was German, of being a Nazi, which he was not. On at least one occasion, Zwicky threatened to kill Bade, who worked up the hill at the Mount Wilson Observatory, if he saw him on the Caltech campus. But Zwicky was also capable of insights of the most startling brilliance. In the early 1930s, he turned his attention to a question that had long troubled astronomers: the appearance in the sky of occasional unexplained points of light, new stars. Improbably, he wondered if the neutron, the subatomic particle that had just been discovered in England by James Chadwick, and was thus both novel and rather fashionable, might be at the heart of things. It occurred to him that if a star collapsed to the sort of densities found in the core of atoms, the result would be an unimaginably compacted core. Atoms would literally be crushed together, their electrons forced into the nucleus, forming neutrons. You would have a neutron star. Imagine 1,000,000 really weighty cannonballs squeezed down to the size of a marble, and, well, you're still not even close. The core of a neutron star is so dense that a single spoonful of matter from it would weigh 90 billion kilograms. A spoonful! But there was more. Zwicky realized that after the collapse of such a star, there would be a huge amount of energy left over, enough to make the biggest bang in the universe. He called these resultant explosions supernovae. They would be, they are, the biggest events in creation. On the 15th of January 1934, the journal Physical Review published a very concise abstract of a presentation that had been conducted by Zwicky and Bade the previous month at Stanford University. Despite its extreme brevity, one paragraph of 24 lines, the abstract contained an enormous amount of new science. It provided the first reference to supernovae and to neutron stars, convincingly explained their method of formation, correctly calculated the scale of their explosiveness, and, as a kind of concluding bonus, connected supernova explosions to the production of a mysterious new phenomenon called cosmic rays, which had recently been found swarming through the universe. These ideas were revolutionary, to say the least. The existence of neutron stars wouldn't be confirmed for 34 years. The cosmic rays notion, though considered plausible, hasn't been verified yet. Altogether, the abstract was, in the words of Caltech astrophysicist Kip S. Thorne, one of the most prescient documents in the history of physics and astronomy. Interestingly, Zwicky had almost no understanding of why any of this would happen. According to Thorne, he did not understand the law of physics well enough to be able to substantiate his ideas. Zwicky's talent was for big ideas. Others, Bada mostly, were left to do the mathematical sweeping up. Zwicky was also the first to recognize that there wasn't nearly enough visible mass in the universe to hold galaxies together, and that there must be some other gravitational influence, what we now call dark matter. One thing he failed to see was that if a neutron star shrank enough, it would become so dense that even light couldn't escape its immense gravitational pull. You would have a black hole. Unfortunately, Zwicky was held in such disdain by most of his colleagues that his ideas attracted almost no notice. When 5 years later the great Robert Oppenheimer turned his attention to neutron stars in a landmark paper, he made not a single reference to any of Zwicky's work, even though Zwicky had been working for years on the same problem in an office just down the corridor. Zwicky's deductions concerning dark matter wouldn't attract serious attention for nearly 4 decades. We can only assume that he did a lot of push-ups in this period. Surprisingly little of the universe is visible to us when we incline our heads to the sky. Only about 6,000 stars are visible to the naked eye from Earth, and only about 2,000 can be seen from any one spot. With binoculars, the number of stars you can see from a single location rises to about 50,000, and with a small 2-inch telescope, it leaps to 300,000. With a 16-inch telescope, such as Evans uses, you begin to count not in stars, but in galaxies. From his deck, Evans supposes he can see between 50,000 and 100,000 galaxies, each containing tens of billions of stars. These are, of course, respectable numbers, but even with so much to take in, supernovae are extremely rare. A star can burn for billions of years, but it dies just once and quickly, and only a few dying stars explode. Most expire quietly like a campfire at dawn. In a typical galaxy consisting of 100 billion stars, a supernova will occur on average once every 200 or 300 years. Looking for a supernova, therefore, was a little like standing on the observation platform of the Empire State Building with a telescope and searching windows around Manhattan in the hope of finding, let us say, someone lighting a 21st birthday cake. So when a hopeful and softly spoken minister got in touch to ask if they had any usable field charts for hunting supernovae, the astronomical community thought he was out of his mind. At the time, Evans had a 10-inch telescope, a very respectable size for amateur stargazing, but hardly the sort of thing with which to do serious cosmology, and he was proposing to find one of the universe's rarer phenomena. In the whole of astronomical history, before Evans started looking in 1980, fewer than 60 supernovae had been found. At the time I visited him in August 2001, he had just recorded his 34th visual discovery. A 35th followed 3 months later, and a 36th in early 2003. Evans, however, had certain advantages. Most observers, like most people generally, are in the northern hemisphere, so he had a lot of sky largely to himself, especially at first. He also had speed and his uncanny memory. Large telescopes are cumbersome things, and much of their operational time is consumed in being maneuvered into position. Evans could swing his little 16-inch telescope around like a tail gunner in a dogfight, spending no more than a couple of seconds on any particular point in the sky. In consequence, he could observe perhaps 400 galaxies in an evening, while a large professional telescope would be lucky to do 50 or 60. Looking for supernovae is mostly a matter of not finding them. From 1980 to 1996, he averaged 2 discoveries a year, not a huge payoff for hundreds of nights of peering and peering. Once he found 3 in 15 days, but another time he went 3 years without finding any at all. "There is actually a certain value in not finding anything," he said. "It helps cosmologists to work out the rate at which galaxies are evolving. It's one of those rare areas where the absence of evidence is evidence." On a table beside the telescope were stacks of photos and papers relevant to his pursuits, and he showed me some of them now. If you have ever looked through popular astronomical publications, and at some time you must have, you will know that they are generally full of richly luminous color photos of distant nebulae and the like, fairy-lit clouds of celestial light of the most delicate and moving splendor. Evans's working images are nothing like that. They are just blurry, black-and-white photos with little points of haloed brightness. One he showed me depicted a swarm of stars in which lurked a trifling flare that I had to put close to my face to discern. This, Evans told me, was a star in a constellation called Fornax, from a galaxy known to astronomy as NGC 1365. NGC stands for New General Catalogue, where these things are recorded. Once it was a heavy book on someone's desk in Dublin. Today, needless to say, it's a database. For 60 million years, the light from this star's spectacular demise traveled unceasingly through space, until one night in August 2001 it arrived at Earth in the form of a puff of radiance, the tiniest brightening in the night sky. It was, of course, Robert Evans, on his eucalypt-scented hillside, who spotted it. "There's something satisfying, I think," Evans said, "about the idea of light traveling for millions of years through space, and just at the right moment as it reaches Earth, someone looks at the right bit of sky and sees it. It just seems right that an event of that magnitude should be witnessed." Supernovae do much more than simply impart a sense of wonder. They come in several types, one of them discovered by Evans. And of these, one in particular, known as the 1A supernova, is important to astronomy because these supernovae always explode in the same way with the same critical mass. For this reason, they can be used as standard candles, benchmarks by which to measure the brightness and hence relative distance of other stars, and thus to measure the expansion rate of the universe. In 1987, Saul Perlmutter at the Lawrence Berkeley Laboratory in California, needing more 1A supernovae than visual sightings were providing, set out to find a more systematic method of searching for them. Perlmutter devised a nifty system using sophisticated computers and charge-coupled devices, in essence, really good digital cameras. It automated supernova hunting. Telescopes could now take thousands of pictures and let a computer detect the telltale bright spots that marked a supernova explosion. In 5 years, with a new technique, Perlmutter and his colleagues at Berkeley found 42 supernovae. Now even amateurs are finding supernovae with charge-coupled devices. "With CCDs, you can aim a telescope at the sky and go watch television," Evans said with a touch of dismay. "It took all the romance out of it." I asked him if he was tempted to adopt the new technology. "Oh, no," he said. "I enjoy my way too much. Besides," he gave a nod at the photo of his latest supernova and smiled, "I can still beat them sometimes." The question that naturally occurs is, what would it be like if a star exploded nearby? Our nearest stellar neighbor, as we have seen, is Alpha Centauri, 4.3 light-years away. I had imagined that if there were an explosion there, we would have 4.3 years to watch the light of this magnificent event spreading across the sky, as if tipped from a giant can. What would it be like if we had 4 years and 4 months to watch an inescapable doom advancing towards us, knowing that when it finally arrived it would blow the skin right off our bones? Would people still go to work? Would farmers plant crops? Would anyone deliver them to the shops? Weeks later, back in the town in New Hampshire where I live, I put these questions to John Thorstenson, an astronomer at Dartmouth College. "Oh, no," he said, laughing. "The news of such an event travels out at the speed of light, but so does the destructiveness. So you'd learn about it and die from it in the same instant. But don't worry, because it's not going to happen." For the blast of a supernova explosion to kill you, he explained, you would have to be ridiculously close, probably within 10 light-years or so. The danger would be various types of radiation, cosmic rays, and so on. These would produce fabulous auroras, shimmering curtains of spooky light that would fill the whole sky. This would not be a good thing. Anything potent enough to put on such a show could well blow away the magnetosphere, the magnetic zone high above the Earth that normally protects us from ultraviolet rays and other cosmic assaults. Without the magnetosphere, anyone unfortunate enough to step into sunlight would pretty quickly take on the appearance of, let us say, an overcooked pizza. The reason we can be reasonably confident that such an event won't happen in our corner of the galaxy, Thorstenson said, is that it takes a particular kind of star to make a supernova in the first place. A candidate star must be 10 to 20 times as massive as our own sun, and we don't have anything of the requisite size that's that close. The universe is a mercifully big place. The nearest likely candidate, he added, is Betelgeuse, whose various sputterings have for years suggested that something interestingly unstable is going on there. But Betelgeuse is 50,000 light-years away. Only half a dozen times in recorded history have supernovae been close enough to be visible to the naked eye. One was a blast in 1054 that created the Crab Nebula. Another, in 1604, made a star bright enough to be seen during the day for over 3 weeks. The most recent was in 1987, when a supernova flared in a zone of the cosmos known as the Large Magellanic Cloud. But that was only barely visible, and only in the southern hemisphere, and it was a comfortably safe 169,000 light-years away. Supernovae are significant to us in one other decidedly central way. Without them, we wouldn't be here. You will recall the cosmological conundrum with which we ended the first chapter, that the Big Bang created lots of light gases but no heavy elements. Those came later, but for a very long time nobody could figure out how they came later. The problem was that you needed something really hot, hotter even than the middle of the hottest stars, to forge carbon and iron and the other elements without which we would be distressingly immaterial. Supernovae provided the explanation, and it was an English cosmologist almost as singular in manner as Fritz Zwicky who worked it out. He was a Yorkshireman named Fred Hoyle. Hoyle, who died in 2001, was described in an obituary in Nature as a cosmologist and controversialist, and both of those he most certainly was. He was, according to Nature's obituary, embroiled in controversy for most of his life, and put his name to much rubbish. He claimed, for instance, and without evidence, that the Natural History Museum's treasured fossil of an Archaeopteryx was a forgery, along the lines of the Piltdown hoax, causing much exasperation to the museum's paleontologists, who had to spend days fielding phone calls from journalists all over the world. He also believed that the Earth was seeded from space not only by life, but also by many of its diseases, such as influenza and bubonic plague, and suggested at one point that humans evolved projecting noses with the nostrils underneath as a way of keeping cosmic pathogens from falling into them. It was he who coined the term Big Bang in a moment of facetiousness for a radio broadcast in 1952. He pointed out that nothing in our understanding of physics could account for why everything gathered to a point would suddenly and dramatically begin to expand. Hoyle favored a steady-state theory, in which the universe was constantly expanding and continually creating new matter as it went. Hoyle also realized that if stars imploded, they would liberate huge amounts of heat, 100 million degrees or more, enough to begin to generate the heavier elements in a process known as nucleosynthesis. In 1957, working with others, Hoyle showed how the heavier elements were formed in supernova explosions. For this work, W.A. Fowler, one of his collaborators, received a Nobel Prize. Hoyle shamefully did not. According to Hoyle's theory, an exploding star would generate enough heat to create all the new elements and spray them into the cosmos, where they would form gaseous clouds, the interstellar medium, as it is known, that could eventually coalesce into new solar systems. With the new theories, it became possible at last to construct plausible scenarios for how we got here. What we now think we know is this. About 4.6 billion years ago, a great swirl of gas and dust, some 24 billion kilometers across, accumulated in space where we are now and began to aggregate. Virtually all of it, 99.9% of the mass of the solar system, went to make the sun. Out of the floating material that was left over, 2 microscopic grains floated close enough together to be joined by electrostatic forces. This was the moment of conception for our planet. All over the inchoate solar system, the same was happening. Colliding dust grains formed larger and larger clumps. Eventually, the clumps grew large enough to be called planetesimals. As these endlessly bumped and collided, they fractured or split or recombined in endless random permutations, but in every encounter there was a winner, and some of the winners grew big enough to dominate the orbit around which they traveled. It all happened remarkably quickly. To grow from a tiny cluster of grains to a baby planet some hundreds of kilometers across is thought to have taken only a few tens of thousands of years. In just 200 million years, probably less, the Earth was essentially formed, though still molten and subject to constant bombardment from all the debris that remained floating about. At this point, about 4.4 billion years ago, an object the size of Mars crashed into the Earth, blowing out enough material to form a companion sphere, the Moon. Within weeks, it is thought, the flung material had reassembled itself into a single clump, and within a year it had formed into the spherical rock that companions us yet. Most of the lunar material, it is thought, came from the Earth's crust, not its core, which is why the Moon has so little iron, while we have a lot. The theory, incidentally, is almost always presented as a recent one, but in fact it was first proposed in the 1940s by Reginald Daly of Harvard. The only recent thing about it is people paying any attention to it. When the Earth was only about a third of its eventual size, it was probably already beginning to form an atmosphere, mostly of carbon dioxide, nitrogen, methane, and sulfur. Hardly the sort of stuff that we would associate with life. And yet, from this noxious stew, life formed. Carbon dioxide is a powerful greenhouse gas. This was a good thing, because the sun was significantly dimmer back then. Had we not had the benefit of a greenhouse effect, the Earth might well have frozen over permanently, and life might never have got a toehold. But somehow life did. For the next 500 million years, the young Earth continued to be pelted relentlessly by comets, meteorites, and other galactic debris, which brought water to fill the oceans and the components necessary for the successful formation of life. It was a singularly hostile environment, and yet somehow life got going. Some tiny bag of chemicals twitched and became animate. We were on our way. 4 billion years later, people began to wonder how it had all happened, and it is there that our story next takes us. Next takes us. Next takes us. Next takes us. Part 2. The Size of the Earth. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Alexander Pope, epitaph intended for Sir Isaac Newton. Chapter 4. The Measure of Things. If you had to select the least convivial scientific field trip of all time, you could certainly do worse than the French Royal Academy of Sciences Peruvian expedition of 1735. Led by a hydrologist named Pierre Bouguer and a soldier-mathematician named Charles-Marie de la Condamine, it was a party of scientists and adventurers who traveled to Peru with the purpose of triangulating distances through the Andes. At the time, people had lately become infected with a powerful desire to understand the Earth, to determine how old it was and how massive, where it hung in space, and how it had come to be. The French party's goal was to help settle the question of the circumference of the planet by measuring the length of 1 degree of meridian, or 1/360th of the distance around the planet, along a line reaching from Yaroqui, near Quito, to just beyond Cuenca in what is now Ecuador, a distance of about 320 kilometers. Almost at once, things began to go wrong, sometimes spectacularly so. In Quito, the visitors somehow provoked the locals and were chased out of town by a mob armed with stones. Soon after, the expedition's doctor was murdered in a misunderstanding over a woman. The botanist became deranged. Others died of fevers and falls. The third most senior member of the party, a man named Pierre Gaudin, ran off with a 13-year-old girl and could not be induced to return. At one point, the group had to suspend work for 8 months, while La Condamine rode off to Lima to sort out a problem with their permits. Eventually, he and Bouguer stopped speaking and refused to work together. Everywhere the dwindling party went, it was met with the deepest suspicions from officials, who found it difficult to believe that a group of French scientists would travel halfway around the world to measure the world. That made no sense at all. 2.5 centuries later, it still seems a reasonable question. Why didn't the French make their measurements in France and save themselves all the bother and discomfort of their Andean adventure? The answer lies partly with the fact that the 18th century scientists, the French in particular, seldom did things simply if an absurdly demanding alternative was available, and partly with a practical problem that had first arisen with the English astronomer Edmund Halley many years before, long before Bouguer and La Condamine dreamed of going to South America, much less had a reason for doing so. Halley was an exceptional figure. In the course of a long and productive career, he was a sea captain, a cartographer, a professor of geometry at the University of Oxford, deputy controller of the Royal Mint, astronomer royal, and inventor of the deep-sea diving bell. He wrote authoritatively on magnetism, tides, and the motions of the planets, and fondly on the effects of opium. He invented the weather map, an actuarial table, proposed methods for working out the age of the Earth and its distance from the Sun, even devised a practical method for keeping fish fresh out of season. The one thing he didn't do was discover the comet that bears his name. He merely recognized that the comet he saw in 1682 was the same one that had been seen by others in 1456, 1531, and 1607. It didn't become Halley's comet until 1758, some 16 years after his death. For all his achievements, however, Halley's greatest contribution to human knowledge may simply have been to take part in a modest scientific wager with 2 other worthies of his day. Robert Hooke, who is perhaps best remembered now as the first person to describe a cell, and the great and stately Sir Christopher Wren, who was actually an astronomer first and an architect second, though that is not often generally remembered now. In 1683, Halley, Hooke, and Wren were dining in London when the conversation turned to the motions of celestial objects. It was known that planets were inclined to orbit in a particular kind of oval known as an ellipse, a very specific and precise curve, to quote Richard Feynman, but it wasn't understood why. Wren generously offered a prize worth 40 shillings, equivalent to a couple of weeks' pay, to whichever of the men could provide a solution. Hook, who was well known for taking credit for ideas that weren't necessarily his own, claimed that he had solved the problem already, but declined now to share it on the interesting and inventive grounds that it would rob others of the satisfaction of discovering the answer for themselves. He would instead conceal it for some time, that others might know how to value it. If he thought any more on the matter, he left no evidence of it. Halley, however, became consumed with finding the answer, to the point that the following year he travelled to Cambridge and boldly called upon the university's Lucasian professor of mathematics, Isaac Newton, in the hope that he could help. Newton was a decidedly odd figure, brilliant beyond measure, but solitary, joyless, prickly to the point of paranoia, famously distracted. Upon swinging his feet out of bed in the morning, he would reportedly sometimes sit for hours, immobilized by the sudden rush of thoughts to his head, and capable of the most riveting strangeness. He built his own laboratory, the first at Cambridge, but then engaged in the most bizarre experiments. Once he inserted a bodkin, a long needle of the sort used for sewing leather, into his eye socket, and rubbed it around betwixt my eye and the bone as near to the backside of my eye as I could, just to see what would happen. What happened, miraculously, was nothing, at least nothing lasting. On another occasion he stared at the sun for as long as he could bear to determine what effect it would have upon his vision. Again he escaped lasting damage, though he had to spend some days in a darkened room before his eyes forgave him. Set atop these odd beliefs and quirky traits, however, was the mind of a supreme genius, though even when working in conventional channels, he often showed a tendency to peculiarity. As a student frustrated by the limitations of conventional mathematics, he invented an entirely new form, the calculus, but then told no one about it for 27 years. In like manner, he did work in optics that transformed our understanding of light and laid the foundation for the science of spectroscopy, and again chose not to share the results for 3 decades. For all his brilliance, real science accounted for only a part of his interests. At least half his working life was given over to alchemy and wayward religious pursuits. These were not mere dabblings, but wholehearted devotions. He was a secret adherent of a dangerously heretical sect called Arianism, whose principal tenet was the belief that there had been no Holy Trinity, slightly ironic, since Newton's college at Cambridge was Trinity. He spent endless hours studying the floor plan of the lost temple of King Solomon in Jerusalem, teaching himself Hebrew in the process, the better to scan original texts, in the belief that it held mathematical clues to the dates of the second coming of Christ and the end of the world. His attachment to alchemy was no less ardent. In 1936, the economist John Maynard Keynes bought a trunk of Newton's papers at auction, and discovered with astonishment that they were overwhelmingly preoccupied not with optics or planetary motions, but with a single-minded quest to turn base metals into precious ones. An analysis of a strand of Newton's hair in the 1970s found it contained mercury, an element of interest to alchemists, hatters, and thermometer makers, but almost no one else, at a concentration some 40 times the natural level. It is perhaps little wonder that he had trouble remembering to get up in the morning. Quite what Halley expected to get from him when he made his unannounced visit in August 1684 we can only guess. But thanks to the later account of a Newton confidant, Abram de Moivre, we do have a record of one of science's most historic encounters. In 1684, Dr. Halley came to visit at Cambridge, and after they had some time together, the doctor asked him what he thought the curve would be that would be described by the planets, supposing the force of attraction towards the sun to be reciprocal to the square of their distance from it. This was a reference to a piece of mathematics known as the inverse square law, which Halley was convinced lay at the heart of the explanation, though he wasn't sure exactly how. Sir Isaac replied immediately that it would be an ellipse, The doctor, struck with joy and amazement, asked him how he knew it. "Why," saith he, "I have calculated it." Whereupon Dr. Halley asked him for his calculation without further delay. Sir Isaac looked among his papers, but could not find it. This was astounding, like someone saying he had found a cure for cancer, but couldn't remember where he had put the formula. Pressed by Halley, Newton agreed to redo the calculations and produce a paper. He did as promised, but then did much more. He retired for 2 years of intensive reflection and scribbling, and at length produced his masterwork, the Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, better known as the Principia. Once in a great while, a few times in history, a human mind produces an observation so acute and unexpected that people can't quite decide which is the more amazing, the fact or the thinking of it. The appearance of the Principia was one of those moments. It made Newton instantly famous. For the rest of his life he would be draped with plaudits and honours, becoming, among much else, the first person in Britain knighted for scientific achievement. Even the great German mathematician Gottfried von Leibniz, with whom Newton had a long, bitter fight over priority for the invention of the calculus, thought his contributions to mathematics equal to all the accumulated work that had preceded him. "Nearer the gods no mortal may approach," wrote Halley, in a sentiment that was endlessly echoed by his contemporaries and by many others since. Although the Principia has been called one of the most inaccessible books ever written, Newton intentionally made it difficult so that he wouldn't be pestered by mathematical smatterers, as he called them. It was a beacon to those who could follow it. It not only explained mathematically the orbits of heavenly bodies, but also identified the attractive force that got them moving in the first place, gravity. Suddenly, every motion in the universe made sense. At the Principia's heart were Newton's 3 laws of motion, which state very baldly that a thing moves in the direction in which it is pushed, that it will keep moving in a straight line until some other force acts to slow or deflect it, and that every action has an opposite and equal reaction, and his universal law of gravitation. This states that every object in the universe exerts a tug on every other. It may not seem like it, but as you sit here now, you are pulling everything around you, walls, ceiling, lamp, pet cat, towards you with your own little, indeed very little, gravitational field. And these things are also pulling on you. It was Newton who realized that the pull of any 2 objects is, to quote Feynman again, proportional to the mass of each and varies inversely as the square of the distance between them. Put another way, if you double the distance between 2 objects, the attraction between them becomes 4 times weaker. This can be expressed with the formula F equals G_mm over r squared, which is, of course, way beyond anything that most of us could make practical use of, but at least we can appreciate that it is elegantly compact. A couple of brief multiplications, a simple division, and bingo, you know your gravitational position wherever you go. It was the first really universal law of nature ever propounded by a human mind, which is why Newton is everywhere regarded with such profound esteem. The Principia's production was not without drama. To Halley's horror, just as work was nearing completion, Newton and Hooke fell into dispute over the priority for the inverse square law, and Newton refused to release the crucial 3rd volume, without which the first 2 made little sense. Only with some frantic shuttle diplomacy and the most liberal applications of flattery did Halley manage finally to extract the concluding volume from the erratic professor. Halley's traumas were not yet quite over. The Royal Society had promised to publish the work, but now pulled out, citing financial embarrassment. The year before, the Society had backed a costly flop called The History of Fishes, and suspected that the market for a book on mathematical principles would be less than clamorous. Halley, whose means were not great, paid for the book's publication out of his own pocket. Newton, as was his custom, contributed nothing. To make matters worse, Halley at this time had just accepted a position as the Society's clerk, and he was informed that the Society could no longer afford to provide him with a promised salary of £50 per annum. He was to be paid instead in copies of the History of Fishes. Newton's laws explain so many things: the slosh and roll of ocean tides, the motions of planets, why cannonballs trace a particular trajectory before thudding back to Earth, why we aren't flung into space as the planet spins beneath us at hundreds of kilometers an hour, that it took a while for all their implications to seep in. But one revelation became almost immediately controversial. This was the suggestion that the Earth is not quite round. According to Newton's theory, the centrifugal force of the Earth's spin should result in a slight flattening at the poles and a bulging at the equator, which would make the planet slightly oblate. That meant that the length of a degree of meridian wouldn't be the same in Italy as it was in Scotland. Specifically, the length would shorten as you moved away from the poles. This was not good news for those people whose measurements of the planet were based on the assumption that it was a perfect sphere, which was everyone. For half a century, people had been trying to work out the size of the Earth, mostly by making very exacting measurements. One of the first such attempts was by an English mathematician named Richard Norwood. As a young man, Norwood had traveled to Bermuda with a diving bell modeled on Halley's device, intending to make a fortune scooping pearls from the seabed. The scheme failed because there were no pearls, and anyway, Norwood's bell didn't work. But Norwood was not one to waste an experience. In the early 17th century, Bermuda was well known among ship's captains for being hard to locate. The problem was that the ocean was big, Bermuda small, and the navigational tools for dealing with this disparity hopelessly inadequate. There wasn't even yet an agreed length for a nautical mile. Over the breadth of an ocean, the smallest miscalculations would become magnified, so that ships often missed Bermuda-sized targets by dismayingly large margins. Norwood, whose first love was trigonometry and thus angles, decided to bring a little mathematical rigor to navigation, and to that end he determined to calculate the length of a degree. Starting with his back against the Tower of London, Norwood spent 2 devoted years marching 208 miles north to York, repeatedly stretching and measuring a length of chain as he went, all the while making the most meticulous adjustments for the rise and fall of the land and the meanderings of the road. The final step was to measure the angle of the sun at York at the same time of day and on the same day of the year as he had made his first measurement in London. From this he reasoned he could determine the length of 1 degree of the Earth's meridian, and thus calculate the distance around the whole. It was an almost ludicrously ambitious undertaking. A mistake of the slightest fraction of a degree would throw the whole thing out by miles. But in fact, as Norwood proudly declaimed, he was accurate to within a scantling, or more precisely, to within about 600 yards. In metric terms, his figure worked out at 110.72 kilometers per degree of arc. In 1637, Norwood's masterwork of navigation, The Seaman's Practice, was published, and found an immediate following. It went through 17 editions, and was still in print 25 years after his death. Norwood returned to Bermuda with his family, where he became a successful planter and devoted his leisure hours to his first love, trigonometry. He survived there for 38 years, and it would be pleasing to report that he passed this span in happiness and adulation. In fact, he didn't. On the crossing from England, his 2 young sons were placed in a cabin with the Reverend Nathaniel White, and somehow so successfully traumatized the young vicar that he devoted much of the rest of his career to persecuting Norwood in any small way he could think of. Norwood's 2 daughters brought their father additional pain by making poor marriages. One of the husbands, possibly incited by the vicar, continually laid small charges against Norwood in court, causing him much exasperation, and necessitating repeated trips across Bermuda to defend himself. Finally, in the 1650s, witchcraft trials came to Bermuda, and Norwood spent his final years in severe unease that his papers on trigonometry, with their arcane symbols, would be taken as communications with the devil, and that he would be treated to a dreadful execution. So little is known of Norwood that it may in fact be that he deserved his unhappy declining years. What is certainly true is that he got them. Meanwhile, the momentum for determining the Earth's circumference passed to France. There, the astronomer Jean Picard devised an impressively complicated method of triangulation involving quadrants, pendulum clocks, zenith sectors, and telescopes for observing the motions of the moons of Jupiter. After 2 years of trundling and triangulating his way across France, in 1669 he announced a more accurate measure of 110.46 kilometers for 1 degree of arc. This was a great source of pride for the French, but it was predicated on the assumption that the Earth was a perfect sphere, which Newton now said it was not. To complicate matters, after Picard's death, the father and son team of Giovanni and Jacques Cassini repeated Picard's experiments over a larger area, and came up with results that suggested that the Earth was fatter not at the equator, but at the poles. That Newton, in other words, was exactly wrong. It was this that prompted the Academy of Sciences to dispatch Bouguer and La Condamine to South America to take new measurements. They chose the Andes because they needed to measure near the equator, to determine if there really was a difference in sphericity there, and because they reasoned that mountains would give them good sightlines. In fact, the mountains of Peru were so constantly lost in cloud that the team often had to wait weeks for an hour's clear surveying. On top of that, they had selected one of the most nearly impossible terrains on Earth. Peruvians refer to their landscape as muy accidentado, much accidented, and this it most certainly is. Not only did the French have to scale some of the world's most challenging mountains that defeated even their mules, but to reach the mountains they had to ford wild rivers, hack their way through jungles, and cross miles of high, stony desert, nearly all of it uncharted and far from any source of supplies. But Bouguer and La Condamine were nothing if not tenacious, and they stuck to the task for 9.5 long, grim, sun-blistered years. Shortly before concluding the project, word reached them that a second French team, taking measurements in northern Scandinavia, and facing notable discomforts of their own, from squelching bogs to dangerous ice floes, had found that a degree was in fact longer near the poles, as Newton had promised. The Earth was 43 kilometers stouter when measured equatorially than when measured from top to bottom around the poles. Bouguer and La Condamine thus had spent nearly a decade working towards a result they didn't wish to find, only to learn now that they weren't even the first to find it. Listlessly, they completed their survey, which confirmed that the first French team was correct. Then, still not speaking, they returned to the coast and took separate ships home. Something else conjectured by Newton in the Principia was that a plumb line, hung near a mountain, would incline very slightly towards the mountain, affected by the mountain's gravitational mass as well as by the Earth's. This was more than a curious fact. If you measured the deflection accurately and worked out the mass of the mountain, you could calculate the universal gravitational constant, that is, the basic value of gravity, known as G, and along with it, the mass of the Earth. Bouguer and La Condamine had tried this on Peru's Mount Chimborazo, but had been defeated by both the technical difficulties and their own squabbling. And so the notion lay dormant for another 30 years until resurrected in England by Neville Maskelyne, the Astronomer Royal. In Davos-Abell's popular book Longitude, Maskelyne is presented as a ninny and villain for failing to appreciate the brilliance of the clockmaker John Harrison, and this may be so, but we are indebted to him in other ways not mentioned in her book. not least for his successful scheme to weigh the Earth. Maskelyne realized that the nub of the problem lay with finding a mountain of sufficiently regular shape to judge its mass. At his urging, the Royal Society agreed to engage a reliable figure to tour the British Isles to see if such a mountain could be found. Maskelyne knew just such a person, the astronomer and surveyor Charles Mason. Maskelyne and Mason had become friends 11 years earlier, while engaged in a project to measure an astronomical event of great importance, the passage of the planet Venus across the face of the Sun. The tireless Edmund Halley had suggested years before that if you measured one of these passages from selected points on the Earth, you could use the principles of triangulation to work out the distance from the Earth to the Sun, and thence to calibrate the distances to all the other bodies in the solar system. Unfortunately, transits of Venus, as they are known, are an irregular occurrence. They come in pairs, 8 years apart, but then are absent for a century or more, and there were none in Halley's lifetime. But the idea simmered, and when the next transit fell due in 1761, nearly 2 decades after Halley's death, the scientific world was ready. Indeed, more ready than it had been for an astronomical event before. With the instinct for ordeal that characterized the age, scientists set off from more than 100 locations around the globe, to Siberia, China, South Africa, Indonesia, and the woods of Wisconsin, among many others. France dispatched 32 observers, Britain 18 more, and still others set out from Sweden, Russia, Italy, Germany, Ireland, and elsewhere. It was history's first cooperative international scientific venture, and almost everywhere it ran into problems. Many observers were waylaid by war, sickness, or shipwreck. Others made their destinations, but opened their crates to find equipment broken or warped by tropical heat. Once again, the French seemed fated to provide the most memorably unlucky participants. Jean Chappe spent months traveling to Siberia by coach, boat, and sleigh, nursing his delicate instruments over every perilous bump, only to find the last vital stretch blocked by swollen rivers, the result of unusually heavy spring rains, which the locals were swift to blame on him after they saw him pointing strange instruments at the sky. Chappe managed to escape with his life, but with no useful measurements. Unluckier still was Guillaume de Gentil, whose experiences are wonderfully summarized by Timothy Ferris in Coming of Age in the Milky Way. Le Gentil set off from France a year ahead of time to observe the transit from India. But various setbacks left him still at sea on the day of the transit, just about the worst place to be, since steady measurements were impossible on a pitching ship. Undaunted, Le Gentil continued on to India to await the next transit in 1769. With 8 years to prepare, he erected a first-rate viewing station, tested and retested his instruments, and had everything in a state of perfect readiness. On the morning of the second transit, 4th June 1769, he awoke to a fine day. But just as Venus began its pass, a cloud slid in front of the sun and remained there for almost exactly the duration of the transit of 3 hours, 14 minutes, and 7 seconds. Stoically, Le Gentil packed up his instruments and set off for the nearest port. But en route he contracted dysentery and was laid up for nearly a year. Still weakened, he finally made it onto a ship. It was nearly wrecked in a hurricane off the African coast. When at last he reached home, 11.5 years after setting off, and having achieved nothing, he discovered that his relatives had had him declared dead in his absence, and had enthusiastically plundered his estate. In comparison, the disappointments experienced by Britain's 18 scattered observers were mild. Mason found himself paired with a young surveyor named Jeremiah Dixon, and apparently they got along well, for they formed a lasting partnership. Their instructions were to travel to Sumatra and chart the transit there, but after just one night at sea their ship was attacked by a French frigate. Although scientists were in an internationally cooperative mood, nations weren't. Mason and Dixon sent a note to the Royal Society observing that it seemed awfully dangerous on the high seas and wondering if perhaps the whole thing oughtn't to be called off. In reply, they received a swift and chilly rebuke, noting that they had already been paid, that the nation and scientific community were counting on them, and that their failure to proceed would result in the irretrievable loss of their reputations. Chastened, they sailed on, but en route word reached them that Sumatra had fallen to the French, and so they observed the transit inconclusively from the Cape of Good Hope. On the way home, they stopped on the lonely Atlantic outcrop of St. Helena, where they met Maskelyne, whose observations had been thwarted by cloud cover. Mason and Maskelyne formed a solid friendship and spent several happy and possibly even mildly useful weeks charting tidal flows. Soon afterwards, Maskelyne returned to England, where he became Astronomer Royal, and Mason and Dixon, now evidently more seasoned, set off for 4 long and often perilous years, surveying their way through 244 miles of dangerous American wilderness to settle a boundary dispute between the estates of William Penn and Lord Baltimore and the respective colonies of Pennsylvania and Maryland. The result was the famous Mason-Dixon line, which later took on symbolic importance as the dividing line between the slave and free states. Although the line was their principal task, they also contributed several astronomical surveys, including one of the century's most accurate measurements of a degree of meridian, an achievement that brought them far more acclaim in England than the settling of a boundary dispute between spoiled aristocrats. Back in Europe, Maskelyne and his counterparts in Germany and France were forced to the conclusion that the transit measurements of 1761 were essentially a failure. One of the problems, ironically, was that there were too many observations, which when brought together often proved contradictory and impossible to resolve. The successful charting of a Venusian transit fell instead to a little-known Yorkshire-born sea captain named James Cook, who watched the 1769 transit from a sunny hilltop in Tahiti, and then went on to chart and claim Australia for the British Crown. Upon his return, there was now enough information for the French astronomer Joseph Lalande to calculate that the mean distance from the Earth to the Sun was a little over 150 million kilometers. 2 further transits in the 19th century allowed astronomers to put the figure at 149.59 million kilometers, where it has remained ever since. The precise distance, we now know, is 149.597870691 million kilometers. The Earth, at last, had a position in space. As for Mason and Dixon, they returned to England as scientific heroes, and, for reasons unknown, dissolved their partnership. Considering the frequency with which they turn up at seminal events in 18th century science, remarkably little is known about either man. No likenesses exist, and few written references. Of Dixon, the Dictionary of National Biography notes intriguingly that he was, quote, said to have been born in a coal mine, unquote, but then leaves it to the reader's imagination to supply a plausible explanatory circumstance, and adds that he died at Durham in 1777. Apart from his name and long association with Mason, nothing more is known. Mason is only slightly less shadowy. We know that in 1772, at Maskelyne's behest, he accepted the commission to find a suitable mountain for the gravitational deflection experiment, at length reporting back that the mountain they needed was in the central Scottish Highlands, just above Loch Tay, and was called Schiehallion. Nothing, however, would induce him to spend a summer surveying it. He never returned to the field again. His next known movement was in 1786, when, abruptly and mysteriously, he turned up in Philadelphia with his wife and 8 children, apparently on the verge of destitution. He had not been back to America since completing a survey there 18 years earlier, and had no known reason for being there, nor any friends or patrons to greet him. A few weeks later, he was dead. With Mason refusing to survey the mountain, the job fell to Maskelyne. So, for 4 months in the summer of 1774, Maskelyne lived in a tent in a remote Scottish glen, and spent his days directing a team of surveyors who took hundreds of measurements from every possible position. To find the mass of the mountain from all these numbers required a great deal of tedious calculating, for which a mathematician named Charles Hutton was engaged. The surveyors had covered a map with scores of figures, each marking an elevation at some point on or around the mountain. It was essentially just a confusing mass of numbers. But Hutton noticed that if he used a pencil to connect points of equal height, it all became much more orderly. Indeed, one could instantly get a sense of the overall shape and slope of the mountain. He had invented contour lines. Extrapolating from his Schehallien measurements, Hutton calculated the mass of the Earth at 5,000 million tons, from which could reasonably be deduced the masses of all the other major bodies in the solar system, including the Sun. So, from this one experiment, we learned the masses of the Earth, the Sun, the Moon, the other planets and their moons, and got contour lines into the bargain. Not bad for a summer's work. Not everyone was satisfied with the results, however. The shortcoming of the Schehallien experiment was that it was not possible to get a truly accurate figure without knowing the actual density of the mountain. For convenience, Hutton had assumed that the mountain had the same density as ordinary stone, about 2.5 times that of water, but this was little more than an educated guess. One improbable-seeming person who turned his mind to the matter was a country parson named John Mitchell, who resided in the lonely Yorkshire village of Thornhill. Despite his remote and comparatively humble situation, Mitchell was one of the great scientific thinkers of the 18th century, and much esteemed for it. Among a great deal else, he perceived the wave-like nature of earthquakes, conducted much original research into magnetism and gravity, and, quite extraordinarily, envisaged the possibility of black holes 200 years before anyone else, a leap that not even Newton could make. When the German-born musician William Herschel decided his real interest in life was astronomy, it was Mitchell to whom he turned for instruction in making telescopes, a kindness for which planetary science has been in his debt ever since. But of all that Mitchell accomplished, nothing was more ingenious or had greater impact than a machine he designed and built for measuring the mass of the Earth. Unfortunately, he died before he could conduct the experiments, and both the idea and the necessary equipment were passed on to a brilliant but magnificently retiring London scientist named Henry Cavendish. Cavendish is a book in himself. Born into a life of sumptuous privilege, his grandfathers were dukes, respectively of Devonshire and Kent. He was the most gifted English scientist of his age, but also the strangest. He suffered, in the words of one of his few biographers, from shyness to a degree bordering on disease. Any human contact was for him a source of the deepest discomfort. Once he opened his door to find an Austrian admirer freshly arrived from Vienna on the front step. Excitedly, the Austrian began to babble out praise. For a few moments Cavendish received the compliments as if they were blows from a blunt object, and then, unable to take any more, fled down the path and out the gate, leaving the front door wide open. It was some hours before he could be coaxed back to the property. Even his housekeeper communicated with him by letter. Although he did sometimes venture into society, he was particularly devoted to the weekly scientific soirees of the great naturalist Sir Joseph Banks. It was always made clear to the other guests that Cavendish was on no account to be approached or even looked at. Those who sought his views were advised to wander into his vicinity as if by accident, and to talk, as it were, into vacancy. If their remarks were scientifically worthy, they might receive a mumbled reply, but more often than not they would hear a peeved squeak, his voice appears to have been high-pitched, and turn to find an actual vacancy, and the sight of Cavendish fleeing for a more peaceful corner. His wealth and solitary inclinations allowed him to turn his house in Clapham into a large laboratory where he could range undisturbed through every corner of the physical sciences, electricity, heat, gravity, gases, anything to do with the composition of matter. The second half of the 18th century was a time when people of a scientific bent grew intensely interested in the physical properties of fundamental things, gases and electricity in particular, and began seeing what they could do with them, often with more enthusiasm than sense. In America, Benjamin Franklin famously risked his life by flying a kite in an electrical storm. In France, a chemist named Pilatre de Rosier tested the flammability of hydrogen by gulping a mouthful and blowing across an open flame, proving at a stroke that hydrogen is indeed explosively combustible and that eyebrows are not necessarily a permanent feature of one's face. Cavendish, for his part, conducted experiments in which he subjected himself to graduated jolts of electrical current, diligently noting the increasing levels of agony until he could keep hold of his quill and sometimes his consciousness no longer. In the course of a long life, Cavendish made a string of signal discoveries. Among much else, he was the first person to isolate hydrogen, and the first to combine hydrogen and oxygen to form water. But almost nothing he did was entirely divorced from strangeness. To the continuing exasperation of his fellow scientists, he often alluded in published work to the results of experiments that he had not told anyone about. In his secretiveness, he didn't merely resemble Newton, but actively exceeded him. His experiments with electrical conductivity were a century ahead of their time, but unfortunately remained undiscovered until that century had passed. Indeed, the greater part of what he did wasn't known until the late 19th century, when the Cambridge physicist James Clerk Maxwell took on the task of editing Cavendish's papers, by which time credit for his discoveries had nearly always been given to others. Among much else, and without telling anyone, Cavendish discovered or anticipated the law of the conservation of energy, Ohm's law, Dalton's law of partial pressures, Richter's law of reciprocal proportions, Charles's law of gases, and the principles of electrical conductivity. That's just some of it. According to the science historian J.G. Crowther, he also foreshadowed, quote, the work of Kelvin and G.H. Darwin on the effect of tidal friction on slowing the rotation of the Earth, and Larmor's discovery, published in 1915, on the effect of local atmospheric cooling, the work of Pickering on freezing mixtures, and some of the works of Roosboom on heterogeneous equilibria, unquote. Finally, he left clues that led directly to the discovery of the group of elements known as the noble gases, some of which are so elusive that the last of them wasn't found until 1962. But our interest here is in Cavendish's last known experiment, when, in the late summer of 1797, at the age of 67, he turned his attention to the crates of equipment that had been left to him, evidently out of simple scientific respect, by John Michell. When assembled, Mitchell's apparatus looked like nothing so much as an 18th century version of a Nautilus weight-training machine. It incorporated weights, counterweights, pendulums, shafts, and torsion wires. At the heart of the machine were two 350-pound lead balls, which were suspended beside two smaller spheres. The idea was to measure the gravitational deflection of the smaller spheres by the larger ones, which would allow the first measurement of the elusive force known as the gravitational constant, and from which the weight, strictly speaking the mass, of the Earth could be deduced. Because gravity holds planets in orbit and makes falling objects land with a bang, we tend to think of it as a powerful force. But it isn't really. It is only powerful in a kind of collective sense, when one massive object, like the Sun, holds onto another massive object, like the Earth. At an elemental level, gravity is extraordinarily unrobust. Each time you pick up a book from a table or a coin from the floor, you effortlessly overcome the gravitational exertion of an entire planet. What Cavendish was trying to do was measure gravity at this extremely featherweight level. Delicacy was the key word. Not a whisper of disturbance could be allowed into the room containing the apparatus, so Cavendish took up a position in an adjoining room and made his observations with a telescope aimed through a peephole. The work was incredibly exacting, involving 17 delicate, interconnected measurements, which together took nearly a year to complete. When at last he had finished his calculations, Cavendish announced that the Earth weighed a little over 13,000 million pounds, or 6 billion trillion metric tons, to use the modern measure. Today, scientists have at their disposal machines so precise they can detect the weight of a single bacterium, and so sensitive that readings can be disturbed by someone yawning 75 feet away, but they have not significantly improved on Cavendish's measurements of 1797. The current best estimate for the Earth's weight is 5.9725 billion trillion tons, a difference of only about 1% from Cavendish's finding. Interestingly, all of this merely confirmed estimates made by Newton 110 years before Cavendish, without any experimental evidence at all. At all events, by the late 18th century, scientists knew very precisely the shape and dimensions of the Earth and its distance from the Sun and planets, and now Cavendish, without even leaving home, had given them its weight. So you might think that determining the age of the Earth would be relatively straightforward. After all, the necessary materials were literally at their feet. But no. Human beings would split the atom and invent television, nylon, and instant coffee before they could figure out the age of their own planet. To understand why, we must travel north to Scotland and begin with a brilliant and genial man of whom few have ever heard, who had just invented a new science called geology. 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 Chapter 5. The Stonebreakers. At just the time that Henry Cavendish was completing his experiments in London, 400 miles away in Edinburgh, another kind of concluding moment was about to take place with the death of James Hutton. This was bad news for Hutton, of course, but good news for science, as it cleared the way for a man named John Playfair to rewrite Hutton's work without fear of embarrassment. Hutton was by all accounts a man of the keenest insights and liveliest conversation, a delight in company, and without rival when it came to understanding the mysterious slow processes that shaped the earth. Unfortunately, it was beyond him to set down his notions in a form that anyone could begin to understand. He was, as one biographer observed with an all but audible sigh, almost entirely innocent of rhetorical accomplishments. Nearly every line he penned was an invitation to slumber. Here he is in his 1795 masterwork, A Theory of the Earth, with proofs and illustrations, discussing, well, something. The world which we inhabit is composed of the materials not of the earth which was the immediate predecessor of the present, but of the earth which, in ascending from the present, we consider as the third, and which had preceded the land that was above the surface of the sea, while our present land was yet beneath the water of the ocean. Yet almost single-handedly, and quite brilliantly, he created the science of geology and transformed our understanding of the earth. Hutton was born in 1726 into a prosperous Scottish family, and enjoyed the sort of material comfort that allowed him to pass much of his life in a genially expansive round of light work and intellectual betterment. He studied medicine, but found it not to his liking, and turned instead to farming, which he followed in a relaxed and scientific way on the family estate in Berwickshire. Tiring of field and flock, in 1768 he moved to Edinburgh, where he founded a successful business producing sal ammoniac from coal soot, and busied himself with various scientific pursuits. Edinburgh at that time was a centre of intellectual vigour, and Hutton luxuriated in its enriching possibilities. He became a leading member of a society called the Oyster Club, where he passed his evenings in the company of men such as the economist Adam Smith, the chemist Joseph Black, and the philosopher David Hume, as well as such occasional visiting sparks as Benjamin Franklin and James Watt. In the tradition of the day, Hutton took an interest in nearly everything, from mineralogy to metaphysics. He conducted experiments with chemicals, investigated methods of coal mining and canal building, toured salt mines, speculated on the mechanisms of heredity, collected fossils, and propounded theories on rain, the composition of air, and the laws of motion, among much else. But his particular interest was geology. Among the questions that attracted interest in that fanatically inquisitive age was one that had puzzled people for a very long time, namely, why ancient clamshells and other marine fossils were so often found on mountain tops. How on earth did they get there? Those who thought they had a solution fell into two opposing camps. One group, known as the Neptunists, were convinced that everything on the earth, including seashells in improbably lofty places, could be explained by rising and falling sea levels. They believed that mountains, hills, and other features were as old as the earth itself, and were changed only when water sloshed over them during periods of global flooding. Opposing them were the Plutonists, who noted that volcanoes and earthquakes, among other enlivening agents, continually changed the face of the planet, but clearly owed nothing to wayward seas. The Plutonists also raised awkward questions about where all the water went when it wasn't in flood. If there was enough of it at times to cover the Alps, then where, pray, was it during times of tranquility, such as now? Their belief was that the earth was subject to profound internal forces as well as surface ones. However, they couldn't convincingly explain how all those clamshells got up there. It was while puzzling over these matters that Hutton had a series of exceptional insights. From looking at his own farmland, he could see that soil was created by the erosion of rocks, and that particles of this soil were continually washed away and carried off by streams and rivers and redeposited elsewhere. He realized that if such a process were carried to its natural conclusion, then the earth would eventually be worn quite smooth. Yet everywhere around him there were hills. Clearly there had to be some additional process, some form of renewal and uplift that created new hills and mountains to keep the cycle going. The marine fossils on mountain tops, he decided, had not been deposited during floods, but had risen along with the mountains themselves. He also deduced that it was heat within the earth that created new rocks and continents and thrust up mountain chains. It is not too much to say that geologists wouldn't grasp the full implications of this thought until 200 years later, when finally they adopted the concept of plate tectonics. Above all, what Hutton's theories suggested was that the processes that shaped the earth required huge amounts of time, far more than anyone had ever dreamed. There were enough insights here to transform utterly our understanding of the planet. In 1785, Hutton worked his ideas up into a long paper, which was read at consecutive meetings of the Royal Society of Edinburgh. It attracted almost no notice at all. It's not hard to see why. Here, in part, is how he presented it to his audience. In the one case, the forming cause is in the body which is separated. For, after the body has been actuated by heat, it is by the reaction of the proper matter of the body that the chasm which constitutes the vein is formed. In the other case, again, the cause is extrinsic, in relation to the body in which the chasm is formed. There has been the most violent fracture and divulsion, but the cause is still to seek, and it appears not in the vein, for it is not every fracture and dislocation of the solid body of our earth in which minerals or the proper substances of mineral veins are found. Needless to say, almost no one in the audience had the faintest idea what he was talking about. Encouraged by his friends to expand his theory in the touching hope that he might somehow stumble onto clarity in a more expansive format, Hutton spent the next 10 years preparing his magnum opus, which was published in 2 volumes in 1795. Together the 2 books ran to nearly 1,000 pages, and were remarkably worse than even his most pessimistic friends had feared. Apart from anything else, nearly half the completed work now consisted of quotations from French sources, still in the original French. A third volume was so unenticing that it wasn't published until 1899, more than a century after Hutton's death, and the fourth and concluding volume was never published at all. Hutton's Theory of the Earth is a strong candidate for the least read, important book in science, or at least it would be if there weren't so many others. Even Charles Lyell, the greatest geologist of the following century and a man who read everything, admitted he couldn't get through it. Luckily, Hutton had a Boswell in the form of John Playfair, a professor of mathematics at the University of Edinburgh and a close friend, who not only could write silken prose, but thanks to many years at Hutton's elbow, actually understood what Hutton was trying to say, most of the time. In 1802, 5 years after Hutton's death, Playfair produced a simplified exposition of the Huttonian principles, entitled Illustrations of the Huttonian Theory of the Earth. The book was gratefully received by those who took an active interest in geology, which in 1802 was not a large number. That, however, was about to change. And how? In the winter of 1807, 13 like-minded souls in London got together at the Freemasons' Tavern at Longacre in Covent Garden to form a dining club to be called the Geological Society. The idea was to meet once a month, to swap geological notions over a glass or two of Madeira and a convivial dinner. The price of the meal was set at a deliberately hefty 15 shillings to discourage those whose qualifications were merely cerebral. It soon became apparent, however, that there was a demand for something more properly institutional, with a permanent headquarters, where people could gather to share and discuss new findings. In barely a decade, membership grew to 400, still all gentlemen, of course, and the Geological was threatening to eclipse the Royal as the premier scientific society in the country. The members met twice a month, from November until June, when virtually all of them went off to spend the summer doing field work. These weren't people with a pecuniary interest in minerals, you understand, or even academics for the most part, but simply gentlemen with a wealth and time to indulge a hobby at a more or less professional level. By 1830 there were 745 of them, and the world would never see the like again. It is hard to imagine now, but geology excited the 19th century, positively gripped it, in a way that no science ever had before, or would again. In 1839, when Roderick Murchison published The Silurian System, a plump and ponderous study of a type of rock called greywacke, it was an instant bestseller, racing through 4 editions, even though it cost 8 guineas a copy and was, in true Huttonian style, unreadable. As even a Murchison supporter conceded, it had a total want of literary attractiveness. And when in 1841 the great Charles Lyell traveled to America to give a series of lectures in Boston, sell-out audiences of 3,000 at a time packed into the Lowell Institute to hear his tranquilizing descriptions of marine zeolites and seismic perturbations in Campania. Throughout the modern thinking world, but especially in Britain, men of learning ventured into the countryside to do a little stone-breaking, as they called it. It was a pursuit taken seriously, and they tended to dress with appropriate gravity in top hats and dark suits, except for the Reverend William Buckland of Oxford, whose habit it was to do his field work in an academic gown. The field attracted many extraordinary figures, not least the aforementioned Murchison, who spent the first 30 or so years of his life galloping after foxes, converting aeronautically challenged birds into puffs of drifting feathers with buckshot, and showing no mental agility whatever beyond that needed to read the Times or play a hand of cards. Then he discovered an interest in rocks, and became, with rather astounding swiftness, a titan of geological thinking. Then there was Dr. James Parkinson, who was also an early socialist and author of many provocative pamphlets with titles like Revolution Without Bloodshed. In 1794 he was implicated in a faintly lunatic-sounding conspiracy called the Popgun Plot, in which it was planned to shoot King George III in the neck with a poisoned dart as he sat in his box at the theatre. Parkinson was hauled before the Privy Council for questioning and came within an ace of being dispatched in irons to Australia before the charges against him were quietly dropped. Adopting a more conservative approach to life, he developed an interest in geology and became one of the founding members of the Geological Society and the author of an important geological text, Organic Remains of a Former World, which remained in print for half a century. He never caused trouble again. Today, however, we remember him for his landmark study of the affliction then called the shaking palsy, but known ever since as Parkinson's disease. Parkinson had one other slight claim to fame. In 1785 he became possibly the only person in history to win a natural history museum in a raffle. The museum, in London's Leicester Square, had been founded by Sir Ashton Lever, who had driven himself bankrupt with his unrestrained collecting of natural wonders. Parkinson kept the museum until 1805, when he could no longer support it, and the collection was broken up and sold. Not quite as remarkable in character, but more influential than all the others combined, was Charles Lyell. Lyell was born in the year that Hutton died, and only 70 miles away, in the village of Kinnordy. Though Scottish by birth, he grew up in the far south of England, in the New Forest of Hampshire, because his mother was convinced that Scots were feckless drunks. As was generally the pattern with 19th-century gentlemen scientists, Lyell came from a background of comfortable wealth and intellectual vigor. His father, also named Charles, had the unusual distinction of being a leading authority on the poet Dante, and on mosses. Orthotricium Lyelli, which most visitors to the English countryside will at some time have sat on, is named for him. From his father, Lyell gained an interest in natural history, but it was at Oxford, where he fell under the spell of the Reverend William Buckland, he of the flowing gowns, that the young Lyell began his lifelong devotion to geology. Buckland was a bit of a charming oddity. He had some real achievements, but he is remembered at least as much for his eccentricities. He was particularly noted for a menagerie of wild animals, some large and dangerous, that were allowed to wander through his house and garden, and for his desire to eat his way through every animal in creation. Depending on whim and availability, guests to Buckland's house might be served baked guinea pig, mice in batter, roasted hedgehog, or boiled Southeast Asian sea slug. Buckland was able to find merit in them all, except the common garden mole, which he declared disgusting. Almost inevitably, he became the leading authority on coprolites, fossilized feces, and had a table made entirely out of his collection of specimens. Even when conducting serious science, his manner was generally singular. Once Mrs. Buckland found herself being shaken awake in the middle of the night, her husband crying in excitement, "My dear, I believe that Charatherium's footsteps are undoubtedly testudinal." Together they hurried to the kitchen in their nightclothes. Mrs. Buckland made a flour paste, which she spread across the table, while the Reverend Buckland fetched the family tortoise. Plunking it onto the paste, they goaded it forward and discovered to their delight that its footprints did indeed match those of the fossil Buckland had been studying. Charles Darwin thought Buckland a buffoon. That was the word he used, but Lyell appeared to find him inspiring and liked him well enough to go touring with him in Scotland in 1824. It was soon after this trip that Lyell decided to abandon a career in law and devote himself to geology full-time. Lyell was extremely short-sighted and went through most of his life with a pained squint, which gave him a troubled air. Eventually he would lose his sight altogether. His other slight peculiarity was the habit, when distracted by thought, of taking up improbable positions on furniture, lying across two chairs at once, or resting his head on the seat of a chair while standing up, to quote his friend Darwin. Often when lost in thought, he would slink so low in a chair that his buttocks would all but touch the floor. Lyell's only real job in life was as professor of geology at King's College in London from 1831 to 1833. It was just at this time that he produced The Principles of Geology, published in 3 volumes between 1830 and 1833, which in many ways consolidated and elaborated upon the thoughts first voiced by Hutton a generation earlier. Although Lyell never read Hutton in the original, he was a keen student of Playfair's reworked version. Between Hutton's day and Lyell's, there arose a new geological controversy which largely superseded but is often confused with the old Neptunian-Plutonian dispute. The new battle became an argument between catastrophism and uniformitarianism, unattractive terms for an important and very long-running dispute. Catastrophists, as you might expect from the name, believed that the earth was shaped by abrupt cataclysmic events, floods principally, which is why catastrophism and Neptunism are often wrongly bundled together. Catastrophism was particularly comforting to clerics like Buckland, because it allowed them to incorporate the biblical flood of Noah into serious scientific discussions. Uniformitarians, by contrast, believed that changes on Earth were gradual, and that nearly all Earth processes happened slowly over immense spans of time. Hutton was much more the father of the notion than Lyell, but it was Lyell most people read, and so he became in most people's minds, then and now, the father of modern geological thought. Lyell believed that the Earth's shifts were uniform and steady, that everything that had ever happened in the past could be explained by events still going on today. Lyell and his adherents didn't just disdain catastrophism, they detested it. Catastrophists believed that extinctions were part of a series in which animals were repeatedly wiped out and replaced with new sets, a belief that the naturalist T.H. Huxley mockingly likened to a succession of rubbers of whist, at the end of which the players upset the table and called for a new pack. It was too convenient a way to explain the unknown. Never was there a dogma more calculated to foster indolence and to blunt the keen edge of curiosity, sniffed Lyell. Lyell's oversights were not inconsiderable. He failed to explain convincingly how mountain ranges were formed, and overlooked glaciers as an agent of change. He refused to accept Agassiz's idea of ice ages, the refrigeration of the globe, as he dismissively termed it, and was confident that mammals would be found in the oldest fossiliferous beds. He rejected the notion that animals and plants suffered sudden annihilations, and believed that all the principal animal groups, mammals, reptiles, fish, and so on, had coexisted since the dawn of time. On all of these he would ultimately be proved wrong. Yet it would be nearly impossible to overstate Lyell's influence. The Principles of Geology went through 12 editions in his lifetime and contained notions that shaped geological thinking far into the 20th century. Darwin took a first edition with him on the Beagle voyage, and wrote afterwards that the great merit of the Principles was that it altered the whole tone of one's mind, and therefore that when seeing a thing never seen by Lyell, one yet saw it partially through his eyes. In short, he thought him nearly a god, as did many of his generation. It is a testament to the strength of Lyell's sway that in the 1980s, when geologists had to abandon just a part of his theory to accommodate the impact theory of extinctions, it nearly killed them. But that is another chapter. Meanwhile, geology had a great deal of sorting out to do, and not all of it went smoothly. From the outset, geologists tried to categorize rocks by the periods in which they were laid down, but there were often bitter disagreements about where to put the dividing lines, none more so than a long-running debate that became known as the Great Devonian Controversy. The issue arose when the Reverend Adam Sedgwick of Cambridge claimed for the Cambrian period a layer of rock that Roderick Murchison believed belonged rightly to the Silurian. The dispute raged for years and grew extremely heated. "De la Beche is a dirty dog," Murchison wrote to a friend in a typical outburst. Some sense of the strength of feeling can be gained by glancing through the chapter titles of Martin J.S. Rudwick's excellent and somber account of the issue, The Great Devonian Controversy. These begin innocuously enough with headings such as Arenas of Gentlemanly Debate and Unraveling the Greywacke, but then proceed on to The Greywacke Defended and Attacked, Reproofs and Recriminations, The Spread of Ugly Rumours, Weaver recants his heresy, putting a provincial in his place, and, in case there was any doubt that this was war, Murchison opens the Rhineland campaign. The fight was finally settled in 1879, with the simple expedient of coming up with a new period, the Ordovician, to be inserted between the Cambrian and the Silurian. Because the British were the most active in the early years of the discipline, British names are predominant in the geological lexicon. Devonian is, of course, from the English county of Devon. Cambrian comes from the Roman name for Wales, while Ordovician and Silurian recall ancient Welsh tribes, the Ordovices and Silures. But with the rise of geological prospecting elsewhere, names began to creep in from all over. Jurassic refers to the Jura Mountains on the border of France and Switzerland. Permian recalls the former Russian province of Perm in the Ural Mountains. For Cretaceous, from the Latin for chalk, we are indebted to a Belgian geologist with the perky name of J. Domalius Dalloy. Originally, geological history was divided into 4 spans of time: primary, secondary, tertiary, and quaternary. The system was too neat to last, and soon geologists were contributing additional divisions while eliminating others. Primary and secondary fell out of use altogether, while quaternary was discarded by some but kept by others. Today only tertiary remains as a common designation everywhere, even though it no longer represents a third period of anything. Lyell, in his Principles, introduced additional units known as epochs, or series, to cover the period since the age of the dinosaurs, among them Pleistocene, most recent, Pliocene, more recent, Miocene, moderately recent, and the rather endearingly vague Oligocene, but a little recent. Lyell originally intended to employ synchronous for his endings, giving us such crunchy designations as myosynchronous and pliosynchronous. The Reverend William Whewell, an influential man, objected on etymological grounds and suggested instead an eus pattern, producing Myonius, Plionius, and so on. The scene terminations were thus something of a compromise. Nowadays, and speaking very generally, geological time is divided into 4 great chunks known as eras: Precambrian, Paleozoic, from the Greek meaning old life, Mesozoic, middle life, and Cenozoic, recent life. These 4 eras are further divided into anywhere from 12 to 20 subgroups, usually called periods, though sometimes known as systems. Most of these are also reasonably well known: Cretaceous, Jurassic, Triassic, Silurian, and so on. Then come Lyell's epochs, the Pleistocene, Miocene, and so on, which apply only to the most recent but paleontologically busy 65 million years. And finally we have a mass of finer subdivisions known as stages or ages. Most of these are named, nearly always awkwardly, after places: Illinoisan, Desmoinian, Croaxian, Kimmeridgian, and so on, in like vein. Altogether, according to John McPhee, these number in the tens of dozens. Fortunately, unless you take up geology as a career, you are unlikely ever to hear any of them again. Further confusing the matter is that the stages or ages in North America have different names from the stages in Europe, and often only roughly intersect with them in time. Thus the North American Cincinnatian stage mostly corresponds with the Ashgilian stage in Europe, plus a tiny bit of the slightly earlier Caradocian stage. Also, all this changes from textbook to textbook, and from person to person, so that some authorities describe 7 recent epochs, while others are content with 4. In some books, too, you will find the tertiary and quaternary taken out, and replaced by periods of different lengths called the Paleogene and Neogene. Others divide the Precambrian into 2 eras, the very ancient Archean and the more recent Proterozoic. Sometimes, too, you will see the term Phanerozoic used to describe the span encompassing the Cenozoic, Mesozoic, and Paleozoic eras. Moreover, all this applies only to units of time. Rocks are divided into quite separate units known as systems, series, and stages. A distinction is also made between late and early referring to time and upper and lower referring to layers of rock. It can all get terribly confusing to non-specialists, but to a geologist these can be matters of passion. I have seen grown men grow incandescent with rage over this metaphorical millisecond in life's history. The British paleontologist Richard Fortey has written with regard to a long-running 20th century dispute over where the boundary lies between the Cambrian and Ordovician. At least today we can bring some sophisticated dating techniques to the table. For most of the 19th century, geologists could draw on nothing more than the most hopeful guesswork. The frustrating position then was that although they could place the various rocks and fossils in order by age, they had no idea how long any of those ages was. When Buckland speculated on the antiquity of an ichthyosaurus skeleton, he could do no better than suggest that it had lived somewhere between 10,000 and more than 10,000 times 10,000 years earlier. Although there was no reliable way of dating periods, there was no shortage of people willing to try. The most well-known early attempt was made in 1650, when Archbishop James Ussher of the Church of Ireland made a careful study of the Bible and other historical sources, and concluded in a hefty tome called Annals of the Old Testament that the earth had been created at midday on the 23rd of October 4004 BC, an assertion that has amused historians and textbook writers ever since. There is a persistent myth, incidentally, and one propounded in many serious books, that Ussher's views dominated scientific beliefs well into the 19th century, and that it was Lyell who put everyone straight. Stephen Jay Gould in Time's Arrow cites as a typical example this sentence from a popular book of the 1980s, quote, "Until Lyell published his book, most thinking people accepted the idea that the earth was young," unquote. In fact, no. As Martin J.S. Rudwick puts it, no geologist of any nationality whose work was taken seriously by other geologists advocated a timescale confined within the limits of a literalistic exegesis of Genesis. Even the Reverend Buckland, as pious a soul as the 19th century produced, noted that nowhere did the Bible suggest that God made heaven and earth on the first day, but merely in the beginning. That beginning, he reasoned, may have lasted millions upon millions of years. Everyone agreed that the earth was ancient. The question was simply, how ancient? One of the better early ideas at dating the planet came from the ever-reliable Edmund Halley, who in 1715 suggested that if you divided the total amount of salt in the world's seas by the amount added each year, you would get the number of years that the oceans had been in existence, which would give you a rough idea of Earth's age. The logic was appealing, but unfortunately no one knew how much salt was in the sea, or by how much it increased each year, which rendered the experiment impracticable. The first attempt at measurement that could be called remotely scientific was made by the Frenchman Georges-Louis Leclerc, Comte de Buffon, in the 1770s. It had long been known that the earth radiated appreciable amounts of heat. That was apparent to anyone who went down a coal mine. but there wasn't any way of estimating the rate of dissipation. Buffon's experiment consisted of heating spheres until they glowed white-hot and then estimating the rate of heat loss by touching them, presumably very lightly at first, as they cooled. From this he guessed the Earth's age to be somewhere between 75,000 and 168,000 years old. This was, of course, a wild underestimate. But it was a radical notion nonetheless, and Buffon found himself threatened with excommunication for expressing it. A practical man, he apologized at once for his thoughtless heresy, then cheerfully repeated the assertions throughout his subsequent writings. By the middle of the 19th century, most learned people thought the Earth was at least a few million years old, perhaps even some tens of millions years old, but probably not more than that. So it came as a surprise when in 1859, in On the Origin of Species, Charles Darwin announced that the geological processes that created the Weald, an area of southern England stretching across Kent, Surrey, and Sussex, had taken, by his calculations, 306,662,400 years to complete. The assertion was remarkable, partly for being so arrestingly specific, but even more for flying in the face of accepted wisdom about the age of the Earth. It proved so contentious that Darwin withdrew it from the third edition of the book. The problem at its heart remained, however. Darwin and his geological friends needed the Earth to be old, but no one could come up with a way to make it so. Unfortunately for Darwin and for progress, the question came to the attention of the great Lord Kelvin, who, though indubitably great, was then still just plain William Thomson. He wouldn't be elevated to the peerage until 1892, when he was 68 years old and nearing the end of his career, but I shall follow the convention here of using the name retroactively. Kelvin was one of the most extraordinary figures of the 19th century, indeed of any century. The German scientist Hermann von Helmholtz, no intellectual slouch himself, wrote that Kelvin had by far the greatest intelligence and lucidity and mobility of thought of any man he had ever met. "I felt quite wooden beside him sometimes," he added a bit dejectedly. The sentiment is understandable, for Kelvin really was a kind of Victorian Superman. He was born in 1824 in Belfast, the son of a professor of mathematics at the Royal Academical Institution, who soon afterwards transferred to Glasgow. There, Kelvin proved himself such a prodigy that he was admitted to Glasgow University at the exceedingly tender age of 10. By the time he had reached his early 20s, he had studied at institutions in London and Paris, graduated from Cambridge, where he won the university's top prizes for rowing and mathematics, and somehow found time to launch a musical society as well, been elected a Fellow of Peterhouse, and written in French and English a dozen papers in pure and applied mathematics of such dazzling originality that he had to publish them anonymously for fear of embarrassing his superiors. At the age of 22, he returned to Glasgow to take up a professorship in natural philosophy, a position he would hold for the next 53 years. In the course of a long career, he lived to 1907 and the age of 83, he wrote 661 papers, accumulated 69 patents, from which he grew abundantly wealthy, and gained renown in nearly every branch of the physical sciences. Among much else, he suggested the method that led directly to the invention of refrigeration, devised the scale of absolute temperature that still bears his name, invented the boosting devices that allowed telegrams to be sent across oceans, and made innumerable improvements to shipping and navigation, from the invention of a popular marine compass to the creation of the first depth sounder, and those were merely his practical achievements. His theoretical work in electromagnetism, thermodynamics, and the wave theory of light was equally revolutionary. He had really only one flaw, and that was an inability to calculate the correct age of the Earth. The question occupied much of the second half of his career, but he never came anywhere near getting it right. His first effort in 1862 for an article in a popular magazine called Macmillan's suggested that the Earth was 98 million years old, but cautiously allowed that the figure could be as low as 20 million years, or as high as 400 million. With remarkable prudence, he acknowledged that his calculations could be wrong if sources now unknown to us are prepared in the great storehouse of creation. But it was clear that he thought that unlikely. With the passage of time, Kelvin would become more forthright in his assertions and less correct. He continually revised his estimates downwards, from a maximum of 400 million years to 100 million years, then to 50 million years, and finally, in 1897, to a mere 24 million years. Kelvin wasn't being willful. It was simply that there was nothing in physics that could explain how a body the size of the sun could burn continuously for more than a few tens of millions of years at most without exhausting its fuel. Therefore it followed that the sun and its planets were relatively, but inescapably, youthful. The problem was that nearly all the fossil evidence contradicted this, and suddenly, in the 19th century, there was a lot of fossil evidence. 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 Chapter 6. Science Red in Tooth and Claw. In 1787, someone in New Jersey, exactly who now seems to be forgotten, found an enormous thigh bone sticking out of a stream bank at a place called Woodbury Creek. The bone clearly didn't belong to any species of creature still alive, certainly not in New Jersey. From what little is known now, it is thought to have belonged to a hadrosaur, a large, duck-billed dinosaur. At the time, dinosaurs were unknown. The bone was sent to Dr. Caspar Wister, the nation's leading anatomist, who described it at a meeting of the American Philosophical Society in Philadelphia that autumn. Unfortunately, Wister failed completely to recognize the bone's significance and merely made a few cautious and uninspired remarks to the effect that it was indeed a whopper. He thus missed the chance, half a century ahead of anyone else, to be the discoverer of dinosaurs. Indeed, the bone excited so little interest that it was put in a storeroom and eventually disappeared altogether. So the first dinosaur bone ever found was also the first to be lost. That the bone didn't attract greater interest is more than a little puzzling, for its appearance came at a time when America was in a froth of excitement about the remains of large, ancient animals. The cause of this froth was a strange assertion by the great French naturalist, the Comte de Buffon, he of the heated spheres from the previous chapter, that living things in the New World were inferior in nearly every way to those of the Old World. America, Buffon wrote in his vast and much-esteemed Histoire Naturelle, was a land where the water was stagnant, the soil unproductive, and the animals without size or vigor, their constitutions weakened by the noxious vapors that rose from its rotting swamps and sunless forests. In such an environment, even the native Indians lacked virility. "They have no beard or body hair," Buffon sagely confided, "and no ardor for the female. Their reproductive organs were small and feeble." Buffon's observations found surprisingly eager support among other writers, especially those whose conclusions were not complicated by actual familiarity with the country. A Dutchman named Corneille de Pau announced in a popular work called Recherches philosophiques sur les Américains that Native American males were not only reproductively unimposing, but so lacking in virility that they had milk in their breasts. Such views enjoyed an improbable durability, and could be found repeated or echoed in European texts until near the end of the 19th century. Not surprisingly, such aspersions were indignantly met in America. Thomas Jefferson incorporated a furious, and unless the context is understood quite bewildering, rebuttal in his Notes on the State of Virginia, and induced his New Hampshire friend General John Sullivan to send 20 soldiers into the northern woods to find a bull moose to present to Buffon as proof of the stature and majesty of American quadrupeds. It took the men 2 weeks to track down a suitable subject. The moose, when shot, unfortunately lacked the imposing horns that Jefferson had specified, but Sullivan thoughtfully included a rack of antlers from an elk or stag, with a suggestion that these be attached instead. Who, in France, after all, would know? Meanwhile, in Philadelphia, Wister's city, naturalists had begun to assemble the bones of a giant elephant-like creature, known at first as the Great American Incognitum, but later identified, not quite correctly, as a mammoth. The first of these bones had been discovered at a place called Big Bone Lick in Kentucky, but soon others were turning up all over. America, it appeared, had once been the home of a truly substantial creature, one that would surely disprove Buffon's foolish Gallic contentions. In their keenness to demonstrate the incognitum's bulk and ferocity, the American naturalists appear to have become slightly carried away. They overestimated its size by a factor of 6, and gave it frightening claws, which in fact came from a megalonyx, or giant ground sloth found nearby. Rather remarkably, they persuaded themselves that the animal had enjoyed the agility and ferocity of the tiger, and portrayed it in illustrations as pouncing with feline grace onto prey from boulders. When tusks were discovered, they were forced into the animal's head in any number of inventive ways. One restorer screwed the tusks in upside down, like the fangs of a saber-toothed cat, which gave it a satisfyingly aggressive aspect. Another arranged the tusks so that they curved backwards on the engaging theory that the creature had been aquatic and had used them to anchor itself to trees while dozing. The most pertinent consideration about the incognitum, however, was that it appeared to be extinct, a fact that Buffon cheerfully seized upon as proof of its incontestably degenerate nature. Buffon died in 1788, but the controversy rolled on. In 1795, a selection of bones made their way to Paris, where they were examined by the rising star of paleontology, the youthful and aristocratic Georges Cuvier. Cuvier was already dazzling people with his genius for taking heaps of disarticulated bones and whipping them into shapely forms. It was said that he could describe the look and nature of an animal from a single tooth or scrap of jaw, and often name the species and genus into the bargain. Realizing that no one in America had thought to write a formal description of the lumbering beast, Cuvier did so, and thus became its official discoverer. He called it a mastodon, which means, a touch unexpectedly, nipple teeth. Inspired by the controversy, in 1796 Cuvier wrote a landmark paper, Note on the Species of Living and Fossil Elephants, in which he put forward for the first time a formal theory of extinctions. His belief was that from time to time the Earth experienced global catastrophes, in which groups of creatures were wiped out. For religious people, including Cuvier himself, the idea raised uncomfortable implications, since it suggested an unaccountable casualness on the part of Providence. To what end would God create species only to wipe them out later? The notion was contrary to the belief in the great chain of being, which held that the world was carefully ordered and that every living thing within it had a place and purpose, and always had and always would. Jefferson, for one, couldn't abide the thought that whole species would ever be permitted to vanish, or come to that to evolve. So when it was put to him that there might be scientific and political value in sending a party to explore the interior of America beyond the Mississippi, he leaped at the idea, hoping the intrepid adventurers would find herds of healthy mastodons and other outsized creatures grazing on the bounteous plains. Jefferson's personal secretary and trusted friend Meriwether Lewis was chosen co-leader with William Clark and chief naturalist for the expedition. The person selected to advise him on what to look out for with regard to animals living and deceased was none other than Caspar Wister. In the same year, in fact the same month, that the aristocratic and celebrated Cuvier was propounding his extinction theories in Paris, on the other side of the English Channel, a rather more obscure Englishman was having an insight into the value of fossils that would also have lasting ramifications. William Smith was a young supervisor of construction on the Somerset Coal Canal. On the evening of the 5th of January, 1796, he was sitting in a coaching inn in Somerset when he jotted down the notion that would eventually make his reputation. To interpret rocks, there needs to be some means of correlation, a basis on which you can tell that those Carboniferous rocks from Devon are younger than these Cambrian rocks from Wales. Smith's insight was to realize that the answer lay with fossils. At every change in rock strata, certain species of fossils disappeared, while others carried on into subsequent levels. By noting which species appeared in which strata, you could work out the relative ages of rocks wherever they appeared. Drawing on his knowledge as a surveyor, Smith began at once to make a map of Britain's rock strata, which would be published after many trials in 1815, and would become a cornerstone of modern geology. The story is comprehensively covered in Simon Winchester's popular book, The Map That Changed the World. Unfortunately, having had his insight, Smith was curiously uninterested in understanding why rocks were laid down in the way they were. "I have left off puzzling about the origin of strata and content myself with knowing that it is so," he recorded. "The whys and wherefores cannot come within the province of a mineral surveyor." Smith's revelation regarding strata heightened the moral awkwardness concerning extinctions. To begin with, it confirmed that God had wiped out creatures not occasionally, but repeatedly. This made him seem not so much careless as peculiarly hostile. It also made it inconveniently necessary to explain how some species were wiped out, while others continued unimpeded into succeeding eons. Clearly there was more to extinctions than could be accounted for by a single Noachian deluge, as the biblical flood was known. Cuvier resolved the matter to his own satisfaction by suggesting that Genesis applied only to the most recent inundation. God, it appeared, hadn't wished to distract or alarm Moses with news of earlier irrelevant extinctions. So, by the early years of the 19th century, fossils had taken on a certain inescapable importance, which makes Wister's failure to see the significance of his dinosaur bone all the more unfortunate. Suddenly, in any case, bones were turning up all over. Several other opportunities arose for Americans to claim the discovery of dinosaurs, but all were wasted. In 1806, the Lewis and Clark expedition passed through the Hell Creek Formation in Montana, an area where fossil hunters would later literally trip over dinosaur bones, and even examined what was clearly a dinosaur bone embedded in rock, but failed to make anything of it. Other bones and fossilized footprints were found in the Connecticut River Valley of New England, after a farm boy named Plinus Moody spied ancient tracks on a rock ledge at South Hadley, Massachusetts. Some of these at least survive, notably the bones of an Ankylosaurus, which are in the collection of the Peabody Museum at Yale. Found in 1818, they were the first dinosaur bones to be examined and saved, but unfortunately weren't recognized for what they were until 1855. In that same year, 1818, Caspar Wister died, but he did gain a certain unexpected immortality when a botanist named Thomas Nuttall named a delightful climbing shrub after him. Some botanical purists still insist on pronouncing it Wistaria. By this time, however, paleontological momentum had moved to England. In 1812, at Lyme Regis on the Dorset coast, an extraordinary child named Mary Anning, aged 11, 12, or 13, depending on whose account you read, found a strange fossilized sea monster, 17 feet long, and now known as the Ichthyosaurus, embedded in the steep and dangerous cliffs along the English Channel. It was the start of a remarkable career. Anning would spend the next 35 years gathering fossils, which she sold to visitors. She is commonly held to be the source of the famous tongue-twister "She sells seashells on the seashore." She would also find the first plesiosaurus, another marine monster, and one of the first and best pterodactyls. Though none of these was technically a dinosaur, that wasn't terribly relevant at the time, since nobody then knew what a dinosaur was. It was enough to realize that the world had once held creatures strikingly unlike anything we might now find. It wasn't simply that Anning was good at spotting fossils, though she was unrivaled at that, but that she could extract them with the greatest delicacy and without damage. If you ever have the chance to visit the Hall of Ancient Marine Reptiles at the Natural History Museum in London, I urge you to take it, for there is no other way to appreciate the scale and beauty of what this young woman achieved, working virtually unaided with the most basic tools in nearly impossible conditions. The plesiosaur alone took her 10 years of patient excavation. Although untrained, Anning was also able to provide competent drawings and descriptions for scholars, but even with the advantage of her skills, significant finds were rare, and she passed most of her life in considerable poverty. It would be hard to think of a more overlooked person in the history of paleontology than Mary Anning, but in fact there was one who came painfully close. His name was Gideon Algernon Mantell, and he was a country doctor in Sussex. Mantell was a lanky assemblage of shortcomings. He was vain, self-absorbed, priggish, neglectful of his family, but never was there a more committed amateur paleontologist. He was also lucky to have a devoted and observant wife. In 1822, while he was making a house call on a patient in rural Sussex, Mrs. Mantell went for a stroll down a nearby lane, and in a pile of rubble that had been left to fill potholes, she found a curious object, a curved brown stone about the size of a small walnut. Knowing her husband's interest in fossils, and thinking it might be one, she took it to him. Mantell could see at once it was a fossilized tooth, and after a little study became certain that it was from an animal that was herbivorous, reptilian, extremely large, tens of feet long, and from the Cretaceous period. He was right on all counts. But these were bold conclusions, since nothing like it had been seen before, or even imagined. Aware that his finding would entirely upend what was understood about the past, and urged by his friend the Reverend William Buckland, he of the gowns and experimental appetite, to proceed with caution, Mantell devoted 3 painstaking years to seeking evidence to support his conclusions. He sent the tooth to Cuvier in Paris for an opinion, but the great Frenchman dismissed it as being from a hippopotamus. Cuvier later apologized handsomely for this uncharacteristic error. One day, while doing research at the Hunterian Museum in London, Mantell fell into conversation with a fellow researcher who told him the tooth looked very like those of animals he had been studying, South American iguanas. A hasty comparison confirmed the resemblance. And so Mantell's creature became the iguanodon, after a basking tropical lizard to which it was not in any manner related. Mantell prepared a paper for delivery to the Royal Society. Unfortunately, it emerged that another dinosaur had been found at a quarry in Oxfordshire, and had just been formally described by the Reverend Buckland, the very man who had urged him not to work in haste. It was the Megalosaurus, and the name was actually suggested to Buckland by his friend Dr. James Parkinson, the would-be radical, an eponym for Parkinson's disease. Buckland, it may be recalled, was foremost a geologist, and he showed it with his work on Megalosaurus. In his report for the Transactions of the Geological Society of London, he noted that the creature's teeth were not attached directly to the jawbone, as in lizards, but placed in sockets, in the manner of crocodiles. But having noticed this much, Buckland failed to realize what it meant, namely, that Megalosaurus was an entirely new type of creature. Still, although his report demonstrated little acuity or insight, it was the first published description of a dinosaur. And so it is to Buckland, rather than the far more deserving Mantell, that the credit goes for the discovery of this ancient line of beings. Unaware that disappointment was going to be a continuing feature of his life, Mantell continued hunting for fossils. He found another giant, the Hylaeosaurus, in 1833, and purchasing others from quarrymen and farmers, until he had probably the largest fossil collection in Britain. Mantell was an excellent doctor, an equally gifted bone hunter, but he was unable to support both his talents. As his collecting mania grew, he neglected his medical practice. Soon fossils filled nearly the whole of his house in Brighton and consumed much of his income. A good deal of the rest went to underwriting the publication of books that few cared to own. Illustrations of the Geology of Sussex, published in 1827, sold only 50 copies and left him £300 out of pocket, an uncomfortably substantial sum for the times. In some desperation, Mantell hit on the idea of turning his house into a museum and charging admission, then belatedly realized that such a mercenary act would ruin his standing as a gentleman, not to mention as a scientist, so he allowed people to visit the house for free. They came in their hundreds, week after week, disrupting both his practice and his home life. Eventually, he was forced to sell most of his collection to pay off his debts. Soon after, his wife left him, taking their 4 children with her. Remarkably, his troubles were only just beginning. In the district of Sydenham in South London, at a place called Crystal Palace Park, there stands a strange and forgotten sight. The world's first life-sized models of dinosaurs. Not many people travel there these days. But once, this was one of the most popular attractions in London. In effect, as Richard Fortey has noted, the world's first theme park. Quite a lot about the models is not strictly correct. The iguanodon's thumb has been placed on its nose as a kind of spike, and it stands on 4 sturdy legs, making it look like a rather stout and awkwardly overgrown dog. In life, the iguanodon did not crouch on all 4s, but was bipedal. Looking at them now, you would scarcely guess that these odd and lumbering beasts could cause great rancor and bitterness. But they did. Perhaps nothing in natural history has been at the center of fiercer and more enduring hatreds than the line of ancient beasts known as dinosaurs. At the time of the dinosaurs' construction, Sydenham was on the edge of London, and its spacious park was considered an ideal place to re-erect the famous Crystal Palace, the glass and cast-iron structure that had been the centerpiece of the Great Exhibition of 1851, and from which the new park naturally took its name. The dinosaurs, built of concrete, were a kind of bonus attraction. On New Year's Eve, 1853, a famous dinner for 21 prominent scientists was held inside the unfinished iguanodon. Gideon Mantell, the man who had found and identified the iguanodon, was not among them. The person at the head of the table was the greatest star of the young science of paleontology. His name was Richard Owen, and by this time he had already devoted several productive years to making Gideon Mantell's life hell. Owen had grown up in Lancaster, in the north of England, where he had trained as a doctor. He was a born anatomist and so devoted to his studies that he sometimes illicitly borrowed limbs, organs, and other parts from corpses and took them home for leisurely dissection. Once, while carrying a sack containing the head of a black African sailor that he had just removed, Owen slipped on a wet cobble and watched in horror as the head bounced away from him down the lane and through the open doorway of a cottage, where it came to rest in the front parlour. What the occupants had to say upon finding an unattached head rolling to a halt at their feet can only be imagined. One assumes that they had not formed any terribly advanced conclusions when, an instant later, a fraught-looking young man rushed in, wordlessly retrieved the head, and rushed out again. In 1825, aged just 21, Owen moved to London, and soon after was engaged by the Royal College of Surgeons to help organize their extensive but disordered collections of medical and anatomical specimens. Most of these had been left to the institution by John Hunter, a distinguished surgeon and tireless collector of medical curiosities, but had never been catalogued or organized, largely because the paperwork explaining the significance of each had gone missing soon after Hunter's death. Owen swiftly distinguished himself with his powers of organization and deduction. At the same time, he showed himself to be a peerless anatomist, with instincts for reconstruction almost on a par with the great Cuvier in Paris. He became such an expert on the anatomy of animals that he was granted first refusal on any animal that died at the London Zoological Gardens, and these he would invariably have delivered to his house for examination. Once his wife returned home to find a freshly deceased rhinoceros filling the front hallway. He quickly became a leading expert on all kinds of animals, living and extinct, from platypuses, echidnas, and other newly discovered marsupials, to the hapless dodo and the extinct giant birds called moas that had roamed New Zealand until eaten out of existence by the Maoris. He was the first to describe the Archaeopteryx after its discovery in Bavaria in 1861, and the first to write a formal epitaph for the dodo. Altogether, he produced some 600 anatomical papers, a prodigious output. But it was for his work with dinosaurs that Owen is remembered. He coined the term Dinosauria in 1841. It means terrible lizard, and was a curiously inapt name. Dinosaurs, as we now know, weren't all terrible. Some were no bigger than rabbits, and probably extremely retiring. And the one thing they most emphatically were not was lizards, which are actually of a much older, by 30 million years, lineage. Owen was well aware that the creatures were reptilian, and had at his disposal a perfectly good Greek word, herpeton, but for some reason chose not to use it. Another more excusable error, given the paucity of specimens at the time, was his failure to note that dinosaurs constitute not one, but two orders of reptiles, the bird-hipped ornithischians and the lizard-hipped saurischians. Owen was not an attractive person, in appearance or in temperament. A photograph from his late middle years shows him as gaunt and sinister, like the villain in a Victorian melodrama, with long, lank hair and bulging eyes, a face to frighten babies. In manner he was cold and imperious, and he was without scruple in the furtherance of his ambitions. He was the only person Charles Darwin was ever known to hate. Even Owen's son, who soon after killed himself, referred to his father's lamentable coldness of heart. His undoubted gifts as an anatomist allowed him to get away with the most barefaced dishonesties. In 1857, the naturalist T.H. Huxley was leafing through a new edition of Churchill's Medical Directory when he noticed that Owen was listed as Professor of Comparative Anatomy and Physiology at the Government School of Mines, which rather surprised Huxley, as that was the position he held. Upon inquiring how Churchill's had made such an elemental error, he was told that the information had been provided to them by Dr. Owen himself. A fellow naturalist named Hugh Falconer, meanwhile, caught Owen taking credit for one of his discoveries. Others accused him of borrowing specimens, then denying he had done so. Owen even fell into a bitter dispute with the Queen's dentist over the credit for a theory concerning the physiology of teeth. He did not hesitate to persecute those whom he disliked. Early in his career, Owen used his influence at the Zoological Society to blackball a young man named Robert Grant, whose only crime was to have shown promise as a fellow anatomist. Grant was astonished to discover that he was suddenly denied access to the anatomical specimens he needed to conduct his research. Unable to pursue his work, he sank into understandably dispirited obscurity. But no one suffered more from Owen's unkindly attentions than the hapless and increasingly tragic Gideon Mantell. After losing his wife, his children, his medical practice, and most of his fossil collection, Mantell moved to London. There, in 1841, the fateful year in which Owen would achieve his greatest glory for naming and identifying the dinosaurs, Mantell was involved in a terrible accident. While crossing Clapham Common in a carriage, he somehow fell from his seat, grew entangled in the reins, and was dragged at a gallop over rough ground by the panicked horses. The accident left him bent, crippled, and in chronic pain, with his spine damaged beyond repair. Capitalizing on Mantell's enfeebled state, Owen set about systematically expunging his contributions from the record, renaming species that Mantell had named years before and claiming credit for their discovery for himself. Mantell continued to try to do original research, but Owen used his influence at the Royal Society to ensure that most of his papers were rejected. In 1852, unable to bear any more pain or persecution, Mantell took his own life. His deformed spine was removed and sent to the Royal College of Surgeons, where, now here's an irony for you, it was placed in the care of Richard Owen, director of the college's Hunterian Museum. But the insults had not quite finished. Soon after Mantell's death, an arrestingly uncharitable obituary appeared in the Literary Gazette. In it, Mantell was characterized as a mediocre anatomist, whose modest contributions to paleontology were limited by a want of exact knowledge. The obituary even removed the discovery of the iguanodon from him and credited it instead to Cuvier and Owen, among others. Though the piece carried no byline, the style was Owen's, and no one in the world of the natural sciences doubted the authorship. By this stage, however, Owen's transgressions were beginning to catch up with him. His undoing began when a committee of the Royal Society, a committee of which he happened to be chairman, decided to award him its highest honor, the Royal Medal, for a paper he had written on an extinct mollusk called the belemnite. However, as Deborah Cadbury notes in her excellent history of the period, Terrible Lizard, this piece of work was not quite as original as it appeared. The belemnite, it turned out, had been discovered 4 years earlier by an amateur naturalist named Channing Pierce, and the discovery had been fully reported at a meeting of the Geological Society. Owen had been at that meeting, but failed to mention this when he presented a report of his own to the Royal Society, at which, not incidentally, he rechristened the creature Belemnites owenii in his own honor. Although Owen was allowed to keep the Royal Medal, the episode left a permanent tarnish on his reputation, even among his few remaining supporters. Eventually, Huxley managed to do to Owen what Owen had done to so many others. He had him voted off the councils of the Zoological and Royal Societies. To round off the retribution, Huxley became the new Hunterian professor at the Royal College of Surgeons. Owen would never again do important research, but the latter half of his career was devoted to one unexceptionable pursuit, for which we can all be grateful. In 1856 he became head of the Natural History section of the British Museum, in which capacity he became the driving force behind the creation of London's Natural History Museum. The grand and beloved Gothic heap in South Kensington, opened in 1880, is almost entirely a testament to his vision. Before Owen, museums were designed primarily for the use and edification of the elite, and even they found it difficult to gain access. In the early days of the British Museum, prospective visitors had to make a written application and undergo a brief interview to determine if they were fit to be admitted at all. They then had to return a second time to pick up a ticket, that is, assuming they had passed the interview, and finally come back a third time to view the museum's treasures. Even then, they were whisked through in groups and not allowed to linger. Owen's plan was to welcome everyone, even to the point of encouraging working men to visit in the evening, and to devote most of the museum's space to public displays. He even proposed, very radically, to put informative labels on each display so that people could appreciate what they were viewing. In this, somewhat unexpectedly, he was opposed by T.H. Huxley, who believed that museums should be primarily research institutes. By making the Natural History Museum an institution for everyone, Owen transformed our expectations of what museums are for. Still, his altruism toward his fellow man generally did not deflect him from more personal rivalries. One of his last official acts was to lobby against a proposal to erect a statue in memory of Charles Darwin. In this he failed, though he did achieve a certain belated inadvertent triumph. Today his own statue commands a masterful view from the staircase of the main hall in the Natural History Museum, while Darwin and T.H. Huxley are consigned somewhat obscurely to the museum coffee shop, where they stare gravely over people snacking on cups of tea and jam donuts. It would be reasonable to suppose that Richard Owen's petty rivalries marked the low point of 19th century paleontology, but in fact worse was to come, this time from overseas. In America, in the closing decades of the century, there arose a rivalry even more spectacularly venomous, if not quite as destructive. It was between two strange and ruthless men, Edward Drinker Cope and Othniel Charles Marsh. They had much in common. Both were spoiled, driven, self-centered, quarrelsome, jealous, mistrustful, and ever unhappy. Between them, they changed the world of paleontology. They began as friends and admirers, even naming fossil species after each other, and spent a pleasant week together in 1868. However, something then went wrong between them. Nobody is quite sure what. And by the following year they had developed an enmity that would grow into consuming hatred over the next 3 decades. It is probably safe to say that no two people in the natural sciences have ever despised each other more. Marsh, the elder of the two by 8 years, was a retiring and bookish fellow with a trim beard and dapper manner, who spent little time in the field and was seldom very good at finding things when he was there. On a visit to the famous dinosaur fields of Como Bluff, Wyoming, he failed to notice the bones that were, in the words of one historian, lying everywhere like logs. But he had the means to buy almost anything he wanted. Although he came from a modest background, his father was a farmer in upstate New York, his uncle was the supremely rich and extraordinarily indulgent financier George Peabody. When Marsh showed an interest in natural history, Peabody had a museum built for him at Yale, and provided funds sufficient for him to fill it with almost whatever took his fancy. Cope was born more directly into privilege. His father was a rich Philadelphia businessman, and was by far the more adventurous of the two. In the summer of 1876, in Montana, while George Armstrong Custer and his troops were being cut down at Little Bighorn, Cope was out hunting for bones nearby. When it was pointed out to him that this was probably not the most prudent time to be taking treasures from Indian lands, Cope thought for a minute and decided to press on anyway. He was having too good a season. At one point he ran into a party of suspicious Crow Indians, but he managed to win them over by repeatedly taking out and replacing his false teeth. For a decade or so, Marsh and Cope's mutual dislike primarily took the form of quiet sniping, but in 1877 it erupted into grandiose dimensions. In that year, a Colorado schoolteacher named Arthur Lakes found bones near Morrison while out hiking with a friend. Recognizing the bones as coming from a gigantic saurian, Lakes thoughtfully dispatched some samples to both Marsh and Cope. A delighted Cope sent Lakes $100 for his trouble and asked him not to tell anyone of his discovery, especially Marsh. Confused, Lakes now asked Marsh to pass the bones on to Cope. Marsh did so, but it was an affront that he would never forget. It also marked the start of a war between the two that became increasingly bitter, underhand, and often ridiculous. It sometimes stooped to one team's diggers throwing rocks at the other teams. Cope was caught at one point prizing open crates that belonged to Marsh. They insulted each other in print and poured scorn on each other's results. Seldom, perhaps never, has science been driven forward more swiftly and successfully by animosity. Over the next several years, the two men between them increased the number of known dinosaur species in America from 9 to almost 150. Nearly every dinosaur that the average person can name, Stegosaurus, Brontosaurus, Diplodocus, Triceratops, was found by one or the other of them. Unfortunately, they worked in such reckless haste that they often failed to note that a new discovery was something already known. Between them, they managed to discover a species called Uintatheres anceps no fewer than 22 times. It took years to sort out some of the classification messes they made. Some are not sorted out yet. Of the two, Cope's scientific legacy was much the more substantial. In a breathtakingly industrious career, he wrote some 1,400 learned papers and described almost 1,300 new species of fossil, of all types, not just dinosaurs. More than double Marsh's output in both cases. Cope might have done even more, but unfortunately he went into a rather precipitous descent in his later years. Having inherited a fortune in 1875, he invested unwisely in silver and lost everything. He ended up living in a single room in a Philadelphia boarding house, surrounded by books, papers, and bones. Marsh, by contrast, finished his days in a splendid mansion in New Haven. Cope died in 1897, Marsh 2 years later. In his final years, Cope developed one other interesting obsession. It became his earnest wish to be declared the type specimen for Homo sapiens, that is, to have his bones be the official set for the human race. Normally, the type specimen of a species is the first set of bones found. But since no first set of Homo sapiens bones exists, there was a vacancy, which Cope desired to fill. It was an odd and vain wish, but no one could think of any grounds to oppose it. To that end, Cope willed his bones to the Worcester Institute, a learned society in Philadelphia endowed by the descendants of the seemingly inescapable Caspar Worcester. Unfortunately, after his bones were prepared and assembled, it was found that they showed signs of incipient syphilis, hardly a feature one would wish to preserve in the type specimen for one's own race. So Cope's petition and his bones were quietly shelved. There is still no type specimen for modern humans. As for the other players in this drama, Owen died in 1892, a few years before Cope or Marsh. Buckland ended up losing his mind and finished his days a gibbering wreck in a lunatic asylum in Clapham, not far from where Mantell had suffered his crippling accident. Mantell's twisted spine remained on display at the Hunterian Museum for nearly a century, before being mercifully obliterated by a German bomb in the Blitz. What remained of Mantell's collection after his death passed on to his children, and much of it was taken to New Zealand by his son Walter, who emigrated there in 1840. Walter became a distinguished Kiwi, eventually attaining the office of Minister of Native Affairs. In 1865, he donated the prime specimens from his father's collection, including the famous iguanodon tooth, to the Colonial Museum, now the Museum of New Zealand, in Wellington, where they have remained ever since. The iguanodon tooth that started it all, arguably the most important tooth in paleontology, is no longer on display. Of course, dinosaur hunting didn't end with the deaths of the great 19th century fossil hunters. Indeed, to a surprising extent, it had only just begun. In 1898, the year that fell between the deaths of Cope and Marsh, a trove greater by far than anything found before was discovered, noticed really, at a place called Bone Cabin Quarry, only a few miles from Marsh's prime hunting ground at Como Bluff, Wyoming. There, hundreds and hundreds of fossil bones were to be found weathering out of the hills. They were so numerous, in fact, that someone had built a cabin out of them, hence the name. In just the first 2 seasons, 100,000 pounds of ancient bones were excavated from the site, and tens of thousands of pounds more came in each of the half-dozen years that followed. The upshot is that by the turn of the 20th century, paleontologists had literally tons of old bones to pick over. The problem was that they still didn't have any idea how old any of these bones were. Worse, the agreed ages for the Earth couldn't comfortably support the numbers of eons and ages and epochs that the past obviously contained. If the Earth were really only 20 million years old or so, as the great Lord Kelvin insisted, then whole orders of ancient creatures must have come into being and gone out again, practically in the same geological instant. It just made no sense. Other scientists besides Kelvin turned their minds to the problem and came up with results that only deepened the uncertainty. Samuel Houghton, a respected geologist at Trinity College in Dublin, announced an estimated age for the Earth of 2,300 million years. way beyond anything anybody else was suggesting. When this was drawn to his attention, he recalculated using the same data and put the figure at 153 million years. John Jolly, also of Trinity, decided to give Edmund Halley's ocean salts idea a whirl, but his method was based on so many faulty assumptions that he was hopelessly adrift. He calculated that the Earth was 89 million years old, an age that fitted neatly enough with Kelvin's assumptions, but unfortunately not with reality. Such was the confusion that by the close of the 19th century, depending on which text you consulted, you could learn that the number of years that stood between us and the dawn of complex life in the Cambrian period was 3 million, 18 million, 600 million, 794 million, or 2.4 billion, or some other number within that range. As late as 1910, one of the most respected estimates by the American George Becker put the Earth's age at perhaps as little as 55 million years. Just when matters seemed most intractably confused, along came another extraordinary figure with a novel approach. He was a bluff and brilliant New Zealand farm boy named Ernest Rutherford, and he produced pretty well irrefutable evidence that the Earth was at least many hundreds of millions of years old, probably rather more. Remarkably, his evidence was based on alchemy, natural, spontaneous, scientifically credible, and wholly non-occult, but alchemy nonetheless. Newton, it turned out, had not been so wrong after all. And exactly how that became evident is, of course, another story. Chapter 7. Elemental Matters. Chemistry, as an earnest and respectable science, is often said to date from 1661, when Robert Boyle of Oxford published The Sceptical Chemist, the first work to distinguish between chemists and alchemists, but it was a slow and often erratic transition. Into the 18th century, scholars could feel oddly comfortable in both camps, like the German Johann Becher, who produced a sober and unexceptionable work on mineralogy called Physica Subterranea, but who also was certain that given the right materials, he could make himself invisible. Perhaps nothing better typifies the strange and often accidental nature of chemical science in its early days than a discovery made by a German named Hennig Brand in 1675. Brand became convinced that gold could somehow be distilled from human urine. The similarity of color seems to have been a factor in his conclusion. He assembled 50 buckets of human urine, which he kept for months in his cellar. By various recondite processes, he converted the urine first into a noxious paste, and then into a translucent waxy substance. None of it yielded gold, of course, but a strange and interesting thing did happen. After a time, the substance began to glow. Moreover, when exposed to air, it often spontaneously burst into flame. The commercial potential for the stuff, which soon became known as phosphorus, from Greek and Latin roots meaning light-bearing, was not lost on eager business people, but the difficulties of manufacture made it too costly to exploit. An ounce of phosphorus retailed for 6 guineas, perhaps £300 in today's money, or more than gold. At first, soldiers were called on to provide the raw material, but such an arrangement was hardly conducive to industrial-scale production. In the 1750s, a Swedish chemist named Carl Scheele devised a way to manufacture phosphorus in bulk without the slop or smell of urine. It was largely because of this mastery of phosphorus that Sweden became, and remains, a leading producer of matches. Scheele was both an extraordinary and an extraordinarily luckless fellow. A humble pharmacist with little in the way of advanced apparatus, he discovered 8 elements: chlorine, fluorine, manganese, barium, molybdenum, tungsten, nitrogen, and oxygen, and got credit for none of them. In every case, His finds either were overlooked or made it into publication after someone else had made the same discovery independently. He also discovered many useful compounds, among them ammonia, glycerin, and tannic acid, and was the first to see the commercial potential of chlorine as a bleach, all breakthroughs that made other people extremely wealthy. Scheele's one notable shortcoming was a curious insistence on tasting a little of everything he worked with, including such notoriously disagreeable substances as mercury, prussic acid, another of his discoveries, and hydrocyanic acid, a compound so famously poisonous that 150 years later Erwin Schrödinger chose it as his toxin of choice in a famous thought experiment. Scheele's rashness eventually caught up with him. In 1786, aged just 43, he was found dead at his workbench, surrounded by an array of toxic chemicals, any one of which could have accounted for the stunned and terminal look on his face. Were the world just and Swedish-speaking, Scheele would have enjoyed universal acclaim. As it is, the plaudits have tended to go to more celebrated chemists, mostly from the English-speaking world. Scheele discovered oxygen in 1772, but for various heartbreakingly complicated reasons could not get his paper published in a timely manner. Credit went instead to Joseph Priestley, who discovered the same element independently, but latterly in the summer of 1774. Even more remarkable was Scheele's failure to receive credit for the discovery of chlorine. Nearly all textbooks still attribute chlorine's discovery to Humphrey Davy, who did indeed find it, but 36 years after Scheele. Although chemistry had come a long way in the century that separated Newton and Boyle from Scheele and Priestley and Henry Cavendish, it still had a long way to go. Right up to the closing years of the 18th century, and in Priestley's case a little beyond, scientists everywhere searched for, and sometimes believed they had actually found, things that just weren't there. Vitiated airs, dephlogisticated marine acids, floxes, calxes, terraqueous exhalations, and above all, phlogiston, the substance that was thought to be the active agent in combustion. Somewhere in all this, it was thought, there also resided a mysterious élan vital, the force that brought inanimate objects to life. No one knew where this ethereal essence lay, but two things seemed probable: that you could enliven it with a jolt of electricity, a notion Mary Shelley exploited to full effect in her novel Frankenstein, and that it existed in some substances but not others, which is why we ended up with two branches of chemistry: organic, for those substances that were thought to have it, and inorganic for those that did not. Someone of insight was needed to thrust chemistry into the modern age, and it was the French who provided him. His name was Antoine Laurent Lavoisier. Born in 1743, Lavoisier was a member of the minor nobility. His father had purchased a title for the family. In 1768, he bought a practicing share in a deeply despised institution called the Ferme Générale, or General Farm, which collected taxes and fees on behalf of the government. Although Lavoisier himself was by all accounts mild and fair-minded, the company he worked for was neither. For one thing, it did not tax the rich, but only the poor, and then often arbitrarily. For Lavoisier, the appeal of the institution was that it provided him with a wealth to follow his principal devotion, science. At his peak, his personal earnings reached 150,000 livres a year, perhaps 12 million pounds in today's money. 3 years after embarking on this lucrative career path, he married the 14-year-old daughter of one of his bosses. The marriage was a meeting of hearts and minds. Madame Lavoisier had an incisive intellect, and soon was working productively alongside her husband. Despite the demands of his job and busy social life, they managed on most days to put in 5 hours of science, 2 in the early morning and 3 in the evening, as well as the whole of Sunday, which they called their jour de bonheur, day of happiness. Somehow Lavoisier also found the time to be commissioner of gunpowder, supervised the building of a wall around Paris to deter smugglers, helped found the metric system, and co-author the handbook Méthode de nomenclature chimique, which became the Bible for agreeing the names of the elements. As a leading member of the Académie Royale des Sciences, he was also required to take an informed and active interest in whatever was topical: hypnotism, prison reform, the respiration of insects, the water supply of Paris. It was in such a capacity in 1780 that Lavoisier made some dismissive remarks about a new theory of combustion that had been submitted to the Academy by a hopeful young scientist. The theory was indeed wrong, but the scientist never forgave him. His name was Jean-Paul Marat. The one thing Lavoisier never did was discover an element. At a time when it seemed as if almost anybody with a beaker, a flame, and some interesting powders could discover something new, and when, not incidentally, some 2/3 of the elements were yet to be found, Lavoisier failed to uncover a single one. It certainly wasn't for want of beakers. Lavoisier had 13,000 of them, in what was, to an almost preposterous degree, the finest private laboratory in existence. Instead, he took the discoveries of others and made sense of them. He threw out phlogiston and mephitic airs. He identified oxygen and hydrogen for what they were and gave them both their modern names. In short, he helped to bring rigor, clarity, and method to chemistry. And his fancy equipment did, in fact, come in very handy. For years, he and Madame Lavoisier occupied themselves with extremely exacting studies requiring the finest measurements. They determined, for instance, that a rusting object doesn't lose weight, as everyone had long assumed, but gains weight, an extraordinary discovery. Somehow, as it rusted, the object was attracting elemental particles from the air. It was the first realization that matter can be transformed, but not eliminated. If you burned a book, for instance, its matter would be changed to ash and smoke, but the net amount of stuff in the universe would be the same. This became known as the conservation of mass, and it was a revolutionary concept. Unfortunately, it coincided with another type of revolution, the French one, and in this one, Lavoisier was entirely on the wrong side. Not only was he a member of the hated Ferme Générale, but he had enthusiastically built the wall that enclosed Paris, an edifice so loathed that it was the first thing attacked by the rebellious citizens. Capitalizing on this, in 1791, Marat, now a leading voice in the National Assembly, denounced Lavoisier and suggested that it was well past time for his hanging. Soon afterwards, the Ferme Générale was shut down. Not long after this, Marat was murdered in his bath by an aggrieved young woman named Charlotte Corday. But by this time it was too late for Lavoisier. In 1793, the reign of terror, already intense, ratcheted up to a higher gear. In October, Marie Antoinette was sent to the guillotine. The following month, as he and his wife were making tardy plans to slip away to Scotland, Lavoisier was arrested. In May, he and 31 fellow farmers-general were brought before the Revolutionary Tribunal, in a courtroom presided over by a bust of Marat. 8 were granted acquittals, but Lavoisier and the others were taken directly to the Place de la Révolution, now the Place de la Concorde, site of the busiest of French guillotines. Lavoisier watched his father-in-law beheaded, then stepped up and accepted his fate. Less than 3 months later, on the 27th of July, Robespierre himself was dispatched in the same way and in the same place, and the reign of terror swiftly ended. 100 years after his death, a statue of Lavoisier was erected in Paris, and much admired, until someone pointed out that it looked nothing like him. Under questioning, the sculptor admitted that he had used the head of the mathematician and philosopher, the Marquis de Condorcet. Apparently he had a spare, in the hope that no one would notice, or having noticed, would care. In the second regard he was correct. The statue of Lavoisier comme Condorcet was allowed to remain in place for another half-century until the Second World War, when one morning it was taken away and melted down for scrap. In the early 1800s, there arose in England a fashion for inhaling nitrous oxide, or laughing gas, after it was discovered that its use was attended by a highly pleasurable thrilling. For the next half-century, it would be the drug of choice for young people. One learned body, the Askesian Society, was for a time devoted to little else. Theatres put on laughing gas evenings, where volunteers could refresh themselves with a robust inhalation, and then entertain the audience with their comical staggerings. It wasn't until 1846 that anyone got around to finding a practical use for nitrous oxide as an anesthetic. Goodness knows how many tens of thousands of people suffered unnecessary agonies under the surgeon's knife because no one had thought of the gas's most obvious practical application. I mention this to make the point that chemistry, having come so far in the 18th century, rather lost its bearings in the first decades of the 19th, in much the way that geology would in the early years of the 20th. Partly it was to do with the limitations of equipment. There were, for instance, no centrifuges until the second half of the century, severely restricting many kinds of experiments. And partly it was social. Chemistry was, generally speaking, a science for business people, for those who worked with coal and potash and dyes, and not for gentlemen, who tended to be drawn to geology, natural history, and physics. This was slightly less true in continental Europe than in Britain, but only slightly. It is perhaps telling that one of the most important observations of the century, Brownian motion, which established the active nature of molecules, was made not by a chemist, but by a Scottish botanist, Robert Brown. What Brown noticed in 1827 was that tiny grains of pollen suspended in water remained indefinitely in motion, no matter how long he gave them to settle. The cause of this perpetual motion, namely the actions of invisible molecules, was long a mystery. Things might have been worse had it not been for a splendidly improbable character named Count von Rumford, who, despite the grandeur of his title, began life in Woburn, Massachusetts, in 1753, as plain Benjamin Thompson. Thompson was dashing and ambitious, handsome in feature and figure, occasionally courageous and exceedingly bright, but untroubled by anything so inconveniencing as a scruple. At 19 he married a rich widow 14 years his senior, but at the outbreak of revolution in the colonies he unwisely sided with the Loyalists, for a time spying on their behalf. In the fateful year of 1776, facing arrest for lukewarmness in the cause of liberty, he abandoned his wife and child and fled just ahead of a mob of anti-royalists armed with buckets of hot tar, bags of feathers, and an earnest desire to adorn him with both. He decamped first to England and then to Germany, where he served as a military adviser to the government of Bavaria, so impressing the authorities that in 1791 he was named Count von Rumford of the Holy Roman Empire. While in Munich he also designed and laid out the famous park known as the English Garden. In between these undertakings, he somehow found time to conduct a good deal of solid science. He became the world's foremost authority on thermodynamics, and the first to elucidate the principles of the convection of fluids and the circulation of ocean currents. He also invented several useful objects, including a drip coffee maker, thermal underwear, and a type of range still known as the Rumford fireplace. In 1805, during a sojourn in France, he wooed and married Madame Lavoisier, widow of Antoine Laurent. The marriage was not a success, and they soon parted. Rumford stayed on in France, where he died, universally esteemed by all but his former wives, in 1814. Our purpose in mentioning him here is that in 1799, during a comparatively brief interlude in London, he founded the Royal Institution, yet another of the many learned societies that popped into being all over Britain in the late 18th and early 19th centuries. For a time, it was almost the only institution of standing to actively promote the young science of chemistry, and that was thanks almost entirely to a brilliant young man named Humphrey Davy, who was appointed the institution's professor of chemistry shortly after its inception, and rapidly gained fame as an outstanding lecturer and productive experimentalist. Soon after taking up his position, Davy began to bang out new elements one after another: potassium, sodium, magnesium, calcium, strontium, and aluminum, or aluminium, depending on which branch of English you favor. The confusion over the aluminum-aluminium spelling arose because of some uncharacteristic indecisiveness on Davy's part. When he first isolated the element in 1808, he called it alumium. For some reason he thought better of that and changed it to aluminum 4 years later. Americans dutifully adopted the new term, but many British users disliked aluminum, pointing out that it disrupted the ium pattern established by sodium, calcium, and strontium, so they added a vowel and a syllable. Among his other achievements, Davy also invented the miner's safety helmet. Davy discovered so many elements, not so much because he was serially astute, as because he developed an ingenious technique of applying electricity to a molten substance, electrolysis, as it is known. Altogether, he discovered a dozen elements, a fifth of the known total of his day. Davy might have done far more, but unfortunately, as a young man, he developed an abiding attachment to the buoyant pleasures of nitrous oxide. He grew so attached to the gas that he drew on it, literally, 3 or 4 times a day. Eventually, in 1829, it is thought to have killed him. Fortunately, more sober types were at work elsewhere. In 1808, a dour Quaker named John Dalton became the first person to intimate the nature of an atom, progress that will be discussed more completely a little further on. And in 1811, an Italian with the splendidly operatic name of Lorenzo Romano Amadeo Carlo Avogadro, Count of Quarequa and Cerreto, made a discovery that would prove highly significant in the long term, namely that 2 equal volumes of gases of any type, if kept at the same pressure and temperature, will contain identical numbers of molecules. 2 things were notable about the appealingly simple Avogadro's principle, as it became known. First, it provided a basis for more accurately measuring the size and weight of atoms. Using Avogadro's mathematics, chemists were eventually able to work out, for instance, that a typical atom had a diameter of 0.00000008 centimeters, which is very little indeed. And second, almost no one knew about it for almost 50 years. Partly this was because Avogadro himself was a retiring fellow. He worked alone, corresponded very little with fellow scientists, published few papers, and attended no meetings. But also it was because there were no meetings to attend, and few chemical journals in which to publish. This is a fairly extraordinary fact. The Industrial Revolution was driven in large part by developments in chemistry, and yet, as an organized science, chemistry barely existed for decades. The Chemical Society of London was not founded until 1841, and didn't begin to produce a regular journal until 1848, by which time most learned societies in Britain, geological, geographical, zoological, horticultural, and Linnaean, for naturalists and botanists, were at least 20 years old, and in several cases much more. The rival Institute of Chemistry didn't come into being until 1877, a year after the founding of the American Chemical Society. Because chemistry was so slow to get organized, news of Avogadro's important breakthrough of 1811 didn't begin to become general until the first International Chemistry Congress in Karlsruhe in 1860. Because chemists worked for so long in isolation, conventions were slow to emerge. Until well into the second half of the century, the formula H2O2 might mean water to one chemist, but hydrogen peroxide to another. C2H4 could signify ethylene or marsh gas. There was hardly a molecule that was uniformly represented everywhere. Chemists also used a bewildering variety of symbols and abbreviations, often self-invented. Sweden's J.J. Berzelius brought a much-needed measure of order to matters by decreeing that the elements be abbreviated on the basis of their Greek or Latin names, which is why the abbreviation for iron is Fe, from the Latin ferrum, and for silver is Ag, from the Latin argentum. That so many of the other abbreviations accord with their English names, N for nitrogen, O for oxygen, H for hydrogen, and so on, reflects English's Latinate nature, not its exalted status. To indicate the number of atoms in a molecule, Berzelius employed a superscript notation as an H2O. Later, for no special reason, the fashion became to render the number as subscript. Despite the occasional tidyings up, chemistry by the second half of the 19th century was in something of a mess, which is why everybody was so pleased by the rise to prominence in 1869 of an odd and crazed-looking professor at the University of St. Petersburg named Dmitri Ivanovich Mendeleev. Mendeleev was born in 1834 at Tobolsk, in the far west of Siberia, into a well-educated, reasonably prosperous, and very large family. So large, in fact, that history has lost track of exactly how many Mendeleevs there were. Some sources say there were 14 children, some say 17. All agree, at any rate, that Dmitri was the youngest. Luck was not always with the Mendeleevs. When Dmitri was small, his father, the headmaster of a local school, went blind, and his mother had to go out to work. Clearly an extraordinary woman, she eventually became the manager of a successful glass factory. All went well until 1848, when the factory burned down and the family was reduced to penury. Determined to get her youngest child an education, the indomitable Mrs. Mendeleev hitchhiked with young Dmitri 4,000 miles to St. Petersburg, that's equivalent to traveling from London to Equatorial Guinea, and deposited him at the Institute of Pedagogy. Worn out by her efforts, she died soon after. Mendeleev dutifully completed his studies and eventually landed a position at the local university. There he was a competent but not terribly outstanding chemist, known more for his wild hair and beard, which he had trimmed just once a year, than for his gifts in the laboratory. However, in 1869, at the age of 35, he began to toy with a way to arrange the elements. At the time, elements were normally grouped in two ways, either by atomic weight, using Avogadro's principle, or by common properties, whether they were metals or gases, for instance. Mendeleev's breakthrough was to see that the two could be combined in a single table. As is often the way in science, the principle had actually been anticipated 3 years previously by an amateur chemist in England named John Newlands. He suggested that when elements were arranged by weight, they appeared to repeat certain properties, in a sense to harmonize, at every 8th place along the scale. Slightly unwisely, for this was an idea whose time had not quite yet come, Newlands called it the law of octaves, and likened the arrangement to the octaves on a piano keyboard. Perhaps there was something in Newlands' manner of presentation, but the idea was considered fundamentally preposterous and widely mocked. At gatherings, droller members of the audience would sometimes ask him if he could get his elements to play them a little tune. Discouraged, Newlands gave up pushing the idea and soon dropped out of sight altogether. Mendeleev used a slightly different approach, placing his elements into groups of 7, but employed fundamentally the same premise. Suddenly the idea seemed brilliant and wondrously perceptive. Because the properties repeated themselves periodically, the invention became known as the periodic table. Mendeleev was said to have been inspired by the card game known as solitaire in North America and patience elsewhere, wherein cards are arranged by suit horizontally and by number vertically. Using a broadly similar concept, he arranged the elements in horizontal rows called periods and vertical columns called groups. This instantly showed one set of relationships when read up and down, and another when read from side to side. Specifically, the vertical columns put together chemicals that have similar properties. Thus, copper sits on top of silver, and silver sits on top of gold because of their chemical affinities as metals, while helium, neon, and argon are in a column made up of gases. The actual formal determinant in the ordering is something called their electron valences, and if you want to understand them, you will have to enroll in evening classes. The horizontal rows, meanwhile, arrange the chemicals in ascending order by the number of protons in their nuclei, what is known as their atomic number. The structure of atoms and the significance of protons will come in a following chapter. For the moment, all that is necessary is to appreciate the organizing principle. Hydrogen has just one proton, and so it has an atomic number of 1 and comes first on the chart. Uranium has 92 protons, and so it comes near the end and has an atomic number of 92. In this sense, as Philip Ball has pointed out, chemistry really is just a matter of counting. Atomic number, incidentally, is not to be confused with atomic weight, which is the number of protons plus the number of neutrons in a given element. There was still a great deal that wasn't known or understood. Hydrogen is the most common element in the universe, and yet no one would guess as much for another 30 years. Helium, the second most abundant element, had only been found the year before. Its existence hadn't even been suspected before that. And then not on the Earth, but in the Sun, where it was found with a spectroscope during a solar eclipse, which is why it honors the Greek sun god Helios. It wouldn't be isolated until 1895. Even so, thanks to Mendeleev's invention, chemistry was now on a firm footing. For most of us, the periodic table is a thing of beauty in the abstract, but for chemists, it established an immediate orderliness and clarity that can hardly be overstated. Without a doubt, the periodic table of the chemical elements is the most elegant organizational chart ever devised, wrote Robert E. Krebs in The History and Use of Our Earth's Chemical Elements, and you can find similar sentiments in virtually every history of chemistry in print. Today we have 120 or so known elements, 92 naturally occurring ones, plus a couple of dozen that have been created in labs. The actual number is slightly contentious because the heavy synthesized elements exist for only millionths of seconds, and chemists sometimes argue over whether they have really been detected or not. In Mendeleev's day, just 63 elements were known, but part of his cleverness was to realize that the elements as then known didn't make a complete picture, that many pieces were missing. His table predicted with pleasing accuracy where new elements would slot in when they were found. No one knows, incidentally, how high the number of elements might go, though anything beyond 168 as an atomic weight is considered purely speculative. But what is certain is that anything that is found will fit neatly into Mendeleev's great scheme. The 19th century held one last important surprise for chemists. It began in 1896, when Henri Becquerel in Paris carelessly left a packet of uranium salts on a wrapped photographic plate in a drawer. When he took the plate out some time later, he was surprised to discover that the salts had burned an impression in it, just as if the plate had been exposed to light. The salts were emitting rays of some sort. Considering the importance of what he had found, Becquerel did a very strange thing. He turned the matter over to a graduate student for investigation. Fortunately, the student was a recent émigré from Poland named Marie Curie. Working with her new husband, Pierre, Curie found that certain kinds of rocks poured out constant and extraordinary amounts of energy, yet without diminishing in size or changing in any detectable way. What she and her husband couldn't know, what no one could know until Einstein explained things the following decade, was that the rocks were converting mass into energy in an exceedingly efficient way. Marie Curie dubbed the effect radioactivity. In the process of their work, the Curies also found 2 new elements, polonium, which they named after her native country, and radium. In 1903, the Curies and Becquerel were jointly awarded the Nobel Prize in Physics. Marie Curie would win a second prize in chemistry in 1911, the only person to win in both chemistry and physics. At McGill University in Montreal, the young New Zealand-born Ernest Rutherford became interested in the new radioactive materials. With a colleague named Frederick Soddy, he discovered that immense reserves of energy were bound up in these small amounts of matter, and that the radioactive decay of these reserves could account for most of the Earth's warmth. They also discovered that radioactive elements decayed into other elements, that one day you had an atom of uranium, say, and the next you had an atom of lead. This was truly extraordinary. It was alchemy, pure and simple. No one had ever imagined that such a thing could happen naturally and spontaneously. Ever the pragmatist, Rutherford was the first to see that there could be a valuable practical application in this. He noticed that in any sample of radioactive material, it always took the same amount of time for half the sample to decay, the celebrated half-life, and that this steady, reliable rate of decay could be used as a kind of clock. By calculating backwards from how much radiation a material had now and how swiftly it was decaying, you could work out its age. He tested a piece of pitchblende, the principal ore of uranium, and found it to be 700 million years old, very much older than the age most people were prepared to grant the Earth. In the spring of 1904, Rutherford travelled to London to give a lecture at the Royal Institution, the august organization founded by Count von Rumford only 105 years before, though that powdery and periwigged age now seemed a distant eon compared with the roll-up-your-sleeves robustness of the late Victorians. Rutherford was there to talk about his new disintegration theory of radioactivity, as part of which he brought out his piece of pitchblende. Tactfully, for the aging Kelvin was present, if not always fully awake, Rutherford noted that Kelvin himself had suggested that the discovery of some other source of heat would throw his calculations out. Rutherford had found that other source. Thanks to radioactivity, the Earth could be, and self-evidently was, much older than the 24 million years Kelvin's final calculations allowed. Kelvin beamed at Rutherford's respectful presentation, but was in fact unmoved. He never accepted the revised figures, and to his dying day believed his work on the age of the Earth his most astute and important contribution to science, far greater than his work on thermodynamics. As with most scientific revolutions, Rutherford's new findings were not universally welcomed. John Jolly of Dublin strenuously insisted well into the 1930s that the Earth was no more than 89 million years old, and was stopped only then by his own death. Others began to worry that Rutherford had now given them too much time. But even with radiometric dating, as decay measurements became known, it would be decades before we got within 1 billion years or so of the Earth's actual age. Science was on the right track, but still way out. Kelvin died in 1907. That year also saw the death of Dmitri Mendeleev. Like Kelvin, his productive work was far behind him, but his declining years were notably less serene. As he aged, Mendeleev became increasingly eccentric. He refused to acknowledge the existence of radiation, or the electron, or anything else much that was new and difficult. His final decades were spent mostly storming out of labs and lecture halls all across Europe. In 1955, element 101 was named Mendeleevium in his honor. Appropriately, notes Paul Strathern, it is an unstable element. Radiation, of course, went on, literally and in ways nobody expected. In the early 1900s, Pierre Curie began to experience clear signs of radiation sickness, notably dull aches in his bones and chronic feelings of malaise, which doubtless would have progressed unpleasantly. We shall never know for certain, because in 1906 he was fatally run over by a carriage while crossing a Paris street. Marie Curie spent the rest of her life working with distinction in the field, helping to found the celebrated Radium Institute at the University of Paris in 1914. Despite her 2 Nobel Prizes, she was never elected to the Academy of Sciences, in large part because, after the death of Pierre, she conducted an affair with a married physicist sufficiently indiscreet to scandalize even the French, or at least the old men who ran the Academy, which is perhaps another matter. For a long time it was assumed that anything so miraculously energetic as radioactivity must be beneficial. For years, manufacturers of toothpaste and laxatives put radioactive thorium in their products, and at least until the late 1920s, the Glen Springs Hotel in the Finger Lakes region of New York, and doubtless others as well, featured with pride the therapeutic effects of its radioactive mineral springs. It wasn't banned in consumer products until 1938. By this time, it was much too late for Madame Curie, who died of leukemia in 1934. Radiation, in fact, is so pernicious and long-lasting that even now her papers from the 1890s, even her cookbooks, are too dangerous to handle. Her lab books are kept in lead-lined boxes, and those who wish to see them must don protective clothing. Thanks to the devoted and unwittingly high-risk work of the first atomic scientists, by the early years of the 20th century, it was becoming clear that the Earth was unquestionably venerable, though another half-century of science would have to be done before anyone could confidently say quite how venerable. Science, meanwhile, was about to get a new age of its own, the atomic one. Part 3. A New Age Dawns. A physicist is the atom's way of thinking about atoms. Anonymous. Chapter 8. Einstein's Universe. As the 19th century drew to a close, scientists could reflect with satisfaction that they had pinned down most of the mysteries of the physical world. Electricity, magnetism, gases, optics, acoustics, kinetics, and statistical mechanics, to name just a few, had all fallen into order before them. They had discovered the X-ray, the cathode ray, the electron and radioactivity, invented the ohm, the watt, the Kelvin, the joule, the amp, and the little erg. If a thing could be oscillated, accelerated, perturbed, distilled, combined, weighed, or made gaseous, they had done it, and in the process produced a body of universal laws so weighty and majestic that we still tend to write them out in capitals. The electromagnetic field theory of light, Richter's law of reciprocal proportions, Charles's law of gases, the law of combining volumes, the Zeroth law, the valence concept, the laws of mass actions, and others beyond counting. The whole world clanged and chuffed with the machinery and instruments that their ingenuity had produced. Many wise people believed that there was nothing much left for science to do. In 1875, when a young German in Kiel named Max Planck was deciding whether to devote his life to mathematics or to physics, he was urged most heartily not to choose physics because the breakthroughs had all been made there. The coming century, he was assured, would be one of consolidation and refinement, not revolution. Planck didn't listen. He studied theoretical physics and threw himself body and soul into work on entropy, a process at the heart of thermodynamics, which seemed to hold much promise for an ambitious young man. In 1891 he produced his results, and learned to his dismay that the important work on entropy had, in fact, been done already, in this instance by a retiring scholar at Yale University named J. Willard Gibbs. Gibbs is perhaps the most brilliant person most people have never heard of. Modest to the point of near invisibility, he passed virtually the whole of his life, apart from 3 years spent studying in Europe, within a 3-block area bounded by his house and the Yale campus in New Haven, Connecticut. For his first 10 years at Yale, he didn't even bother to draw a salary. He had independent means. From 1871, when he joined the university as a professor, to his death in 1903, his courses attracted an average of slightly over 1 student a semester. His written work was difficult to follow and employed a private form of notation that many found incomprehensible. But buried among his arcane formulations were insights of the loftiest brilliance. In 1875-8, Gibbs produced a series of papers collectively titled On the Equilibrium of Heterogeneous Substances, which dazzlingly elucidated the thermodynamic principles of, well, nearly everything: gases, mixtures, surfaces, solids, phase changes, chemical reactions, electrochemical cells, sedimentation, and osmosis, to quote William H. Cropper. In essence, what Gibbs did was show that thermodynamics didn't apply simply to heat and energy at the sort of large and noisy scale of the steam engine, but was also present and influential at the atomic level of chemical reactions. Gibbs's equilibrium has been called the Principia of thermodynamics, but for reasons that defy speculation, Gibbs chose to publish these landmark observations in the Transactions of the Connecticut Academy of Arts and Sciences, a journal that managed to be obscure even in Connecticut, which is why Planck did not hear of him until too late. Undaunted, well, perhaps mildly daunted, Planck turned to other matters. We shall turn to these ourselves in a moment. But first we must make a slight but relevant detour to Cleveland, Ohio, and an institution then known as the Case School of Applied Science. There, in the 1880s, a physicist of early middle years named Albert Michelson, assisted by his friend the chemist Edward Morley, embarked on a series of experiments that produced curious and disturbing results that would have great ramifications for much of what followed. What Michelson and Morley did, without actually intending to, was undermine a long-standing belief in something called the luminiferous ether, a stable, invisible, weightless, frictionless, and, unfortunately, wholly imaginary medium that was thought to permeate the universe. Conceived by Descartes, embraced by Newton, and venerated by nearly everyone ever since, the ether held a position of absolute centrality in 19th century physics as a way of explaining how light traveled across the emptiness of space. It was especially needed in the 1800s because light and electromagnetism were now seen as waves, which is to say types of vibrations. Vibrations must occur in something, hence the need for and lasting devotion to an ether. As late as 1909, the great British physicist J.J. Thomson was insisting, "The ether is not a fantastic creation of the speculative philosopher. It is as essential to us as the air we breathe." This more than 4 years after it was pretty incontestably established that it didn't exist. People, in short, were really attached to the ether. If you needed to illustrate the idea of 19th century America as a land of opportunity, you could hardly improve on the life of Albert Michelson. Born in 1852 on the German-Polish border to a family of poor Jewish merchants, he came to the United States with his family as an infant and grew up in a mining camp in California's gold rush country where his father ran a dry goods business. Too poor to pay for college, he traveled to Washington, D.C., and took to loitering by the front door of the White House, so that he could fall in beside Ulysses S. Grant when the president emerged for his daily constitutional. It was clearly a more innocent age. In the course of these walks, Michelson so ingratiated himself with the president that Grant agreed to secure for him a free place at the U.S. Naval Academy. It was there that Michelson learned his physics. 10 years later, by now a professor at the Case School in Cleveland, Michelson became interested in trying to measure something called the ether drift, a kind of headwind produced by moving objects as they plowed through space. One of the predictions of Newtonian physics was that the speed of light as it pushed through the ether should vary with respect to an observer, depending on whether the observer was moving towards the source of light or away from it. But no one had figured out a way to measure this. It occurred to Michelson that for half the year the Earth is traveling towards the sun, and for half the year it is moving away from it, and he reasoned that if you took careful enough measurements at opposite seasons and compared light's travel time between the two, you would have your answer. Michelson talked Alexander Graham Bell, newly enriched inventor of the telephone, into providing the funds to build an ingenious and sensitive instrument of Michelson's own devising called an interferometer, which could measure the velocity of light with great precision. Then, assisted by the genial but shadowy Morley, Michelson embarked on years of fastidious measurements. The work was delicate and exhausting, and had to be suspended for a time to permit Michelson a brief but comprehensive nervous breakdown, but by 1887 they had their results. They were not at all what the two scientists had expected to find. As Caltech astrophysicist Kip S. Thorne has written, the speed of light turned out to be the same in all directions and at all seasons. It was the first hint in 200 years, and exactly 200 years in fact, that Newton's laws might not apply all the time everywhere. The Michelson-Morley outcome became, in the words of William H. Cropper, probably the most famous negative result in the history of physics. Michelson was awarded a Nobel Prize in physics for the work, the first American so honored, but not for 20 years. Meanwhile, the Michelson-Morley experiments would hover unpleasantly like a musty odor in the background of scientific thought. Remarkably, and despite his findings, when the 20th century dawned, Michelson counted himself among those who believed that the work of science was nearly at an end, with only a few turrets and pinnacles to be added, a few roof bosses to be carved, in the words of a writer in Nature. In fact, of course, the world was about to enter a century of science where many people wouldn't understand anything and none would understand everything. Scientists would soon find themselves adrift in a bewildering realm of particles and antiparticles, where things pop in and out of existence in spans of time that make nanoseconds look plodding and uneventful, where everything is strange. Science was moving from a world of macrophysics, where objects could be seen and held and measured, to one of microphysics, where events transpire with inconceivable swiftness on scales of magnitude far below the limits of imagining. We were about to enter the quantum age, and the first person to push on the door was the so far unfortunate Max Planck. In 1900, now a theoretical physicist at the University of Berlin, and at the somewhat advanced age of 42, Planck unveiled a new quantum theory, which posited that energy is not a continuous thing like flowing water, but comes in individualized packets, which he called quanta. This was a novel concept, and a good one. In the short term, it would help to provide a solution to the puzzle of the Michelson-Morley experiments, in that it demonstrated that light needn't be a wave after all. In the longer term, it would lay the foundation for the whole of modern physics. It was, at all events, the first clue that the world was about to change. But the landmark event, the dawn of a new age, came in 1905, when there appeared in the German physics journal Annalen der Physik a series of papers by a young Swiss bureaucrat who had no university affiliation, no access to a laboratory, and the regular use of no library greater than that of the National Patent Office in Bern, where he was employed as a technical examiner third class. An application to be promoted to technical examiner second class had recently been rejected. His name was Albert Einstein. And in that one eventful year he submitted to Annalen der Physik 5 papers, of which 3, according to C.P. Snow, were among the greatest in the history of physics. One examining the photoelectric effect by means of Planck's new quantum theory, one on the behavior of small particles in suspension what is known as Brownian motion, and one outlining a special theory of relativity. The first won its author a Nobel Prize and explained the nature of light, and also helped to make television possible, among other things. The second provided proof that atoms do indeed exist, a fact that had surprisingly been in some dispute. The third nearly changed the world. Einstein was born in Ulm in southern Germany in 1879, but grew up in Munich. Little in his early life suggested the greatness to come. Famously, he didn't learn to speak until he was 3. In the 1890s, his father's electrical business failing, the family moved to Milan, but Albert, by now a teenager, went to Switzerland to continue his education, though he failed his college entrance exams on the first try. In 1896, he gave up his German citizenship to avoid military conscription and entered the Zurich Polytechnic Institute on a 4-year course designed to churn out high school science teachers. He was a bright but not outstanding student. In 1900 he graduated, and within a few months was beginning to contribute papers to Annalen der Physik. His very first paper, on the physics of fluids and drinking straws of all things, appeared in the same issue as Planck's quantum theory. From 1902 to 1904 he produced a series of papers on statistical mechanics, only to discover that the quietly productive J. Willard Gibbs in Connecticut had done that work as well in his Elementary Principles of Statistical Mechanics of 1901. Albert had fallen in love with a fellow student, a Hungarian named Mileva Maric. In 1901 they had a child out of wedlock, a daughter, who was discreetly put up for adoption. Einstein never saw his child. 2 years later, he and Maric were married. In between these events, in 1902, Einstein took a job with the Swiss Patent Office, where he stayed for the next 7 years. He enjoyed the work. It was challenging enough to engage his mind, but not so challenging as to distract him from his physics. This was the background against which he produced the special theory of relativity in 1905. On the electrodynamics of moving bodies is one of the most extraordinary scientific papers ever published, as much for how it was presented as for what it said. It had no footnotes or citations, contained almost no mathematics, made no mention of any work that had influenced or preceded it, and acknowledged the help of just one individual, a colleague at the Patent Office named Michaela Besso. It was, wrote C.P. Snow, as if Einstein had reached the conclusions by pure thought, unaided, without listening to the opinions of others. To a surprisingly large extent, that is precisely what he had done. His famous equation E equals mc squared did not appear with the paper, but came in a brief supplement that followed a few months later. As you will recall from school days, E in the equation stands for energy, m for mass, and c squared for the speed of light squared. In simplest terms, what the equation says is that mass and energy have an equivalence. They are two forms of the same thing. Energy is liberated matter, matter is energy waiting to happen. Since c squared, the speed of light times itself, is a truly enormous number, what the equation is saying is that there is a huge amount, a really huge amount, of energy bound up in every material thing. You may not feel outstandingly robust, but if you are an average-sized adult, you will contain within your modest frame no less than 7 times 10 to the 18th joules of potential energy, enough to explode with a force of 30 very large hydrogen bombs, assuming you knew how to liberate it and really wish to make a point. Everything has this kind of energy trapped within it. We're just not very good at getting it out. Even a uranium bomb, the most energetic thing we have produced yet, releases less than 1% of the energy it could release if only we were more cunning. Among much else, Einstein's theory explained how radiation worked, how a lump of uranium could throw out constant streams of high-level energy without melting away like an ice cube. It could do it by converting mass to energy extremely efficiently, a la E=mc². It explained how stars could burn for billions of years without racing through their fuel, ditto. At a stroke, in a simple formula, Einstein endowed geologists and astronomers with a luxury of billions of years. Above all, the special theory showed that the speed of light was constant and supreme. Nothing could overtake it. It brought light, no pun intended exactly, to the very heart of our understanding of the nature of the universe. Not incidentally, it also solved the problem of the luminiferous ether by making it clear that it didn't exist. Einstein gave us a universe that didn't need it. Physicists, as a rule, are not over-attentive to the pronouncements of Swiss patent office clerks, and so, despite the abundance of useful tidings they offered, Einstein's papers attracted little notice. Having just solved several of the deepest mysteries of the universe, Einstein applied for a job as a university lecturer and was rejected, and then for one as a high school teacher and was rejected there as well. So he went back to his job as an examiner third class, but of course he kept thinking. He hadn't even come close to finishing yet. When the poet Paul Valéry once asked Einstein if he kept a notebook to record his ideas, Einstein looked at him with mild but genuine surprise. "Oh, that's not necessary," he replied. "It's so seldom I have one." I need hardly point out that when he did get one, it tended to be good. Einstein's next idea was one of the greatest that anyone has ever had, indeed, the very greatest, according to Bohr's, Motz, and Weaver, in their thoughtful history of atomic science. "As the creation of a single mind," they write, "it is undoubtedly the highest intellectual achievement of humanity." Which is, of course, as good as a compliment can get. In 1907 or so, it has sometimes been written, Albert Einstein saw a workman fall off a roof and began to think about gravity. Alas, like many good stories, this one appears to be apocryphal. According to Einstein himself, he was simply sitting in a chair when the problem of gravity occurred to him. Actually, what occurred to Einstein was something more like the beginning of a solution to the problem of gravity, since it had been evident to him from the outset that one thing missing from the special theory was gravity. What was special about the special theory was that it dealt with things moving in an essentially unimpeded state. But what happened when a thing in motion, light above all, encountered an obstacle such as gravity? It was a question that would occupy his thoughts for most of the next decade and lead to the publication in early 1917 of a paper entitled Cosmological Considerations on the General Theory of Relativity. The special theory of relativity of 1905 was a profound and important piece of work, of course, but as C.P. Snow once observed, if Einstein hadn't thought of it when he did, someone else would have, probably within 5 years. It was an idea waiting to happen. But the general theory was something else altogether. Without it, wrote Snow in 1979, it is likely that we should still be waiting for the theory today. With his pipe, genially self-effacing manner, and electrified hair, Einstein was too splendid a figure to remain permanently obscure, and in 1919, the war over, the world suddenly discovered him. Almost at once, his theories of relativity developed a reputation for being impossible for an ordinary person to grasp. Matters were not helped, as David Bodanis points out in his superb book E=mc², when the New York Times decided to do a story, and, for reasons that can never fail to excite wonder, sent the paper's golfing correspondent, one Henry Crouch, to conduct the interview. Crouch was hopelessly out of his depth, and got nearly everything wrong. Among the more lasting errors in his report was the assertion that Einstein had found a publisher daring enough to publish a book that only 12 men in all the world could comprehend. There was no such book, no such publisher, no such circle of learned men, but the notion stuck anyway. Soon the number of people who could grasp relativity had been reduced even further in the popular imagination, and the scientific establishment, it must be said, did little to disturb the myth. When a journalist asked the British astronomer Sir Arthur Eddington if it was true that he was one of only 3 people in the world who could understand Einstein's relativity theories, Eddington considered deeply for a moment and replied, "I'm trying to think who the 3rd person is." In fact, the problem with relativity wasn't that it involved a lot of differential equations, Lorentz transformations, and other complicated mathematics, though it did, even Einstein needed help with some of it, but that it was just so thoroughly non-intuitive. In essence, what relativity says is that space and time are not absolute, but relative, both to the observer and to the thing being observed, and the faster one moves, the more pronounced these effects become. We can never accelerate ourselves to the speed of light, and the harder we try and the faster we go, the more distorted we will become relative to an outside observer. Almost at once, popularizers of science tried to come up with ways to make these concepts accessible to a general audience. One of the more successful attempts, commercially at least, was the ABC of relativity by the mathematician and philosopher Bertrand Russell. In it, Russell employed an image that has been used many times since. He asked the reader to envisage a train 100 yards long, moving at 60% of the speed of light. To someone standing on a platform watching it pass, the train would appear to be only 80 yards long, and everything on it would be similarly compressed. If we could hear the passengers on the train speak, their voices would sound slurred and sluggish, like a record played at too slow a speed, and their movements would appear similarly ponderous. Even the clocks on the train would seem to be running at only 4/5 of their normal speed. However, and here's the thing, people on the train would have no sense of these distortions. To them, everything on the train would seem quite normal. It would be us on the platform who looked weirdly compressed and slowed down. It is all to do, you see, with your position relative to the moving object. This effect actually happens every time you move. Fly across the United States and you will step from the plane a quinzillionth of a second or something younger than those you left behind. Even in walking across the room, you will very slightly alter your own experience of time and space. It has been calculated that a baseball, thrown at 160 kilometers an hour, will pick up 0.00000000002 grams of mass on its way to home plate. So the effects of relativity are real and have been measured. The problem is that such changes are much too small to make the tiniest detectable difference to us. But for other things in the universe, light, gravity, the universe itself, these are matters of consequence. So if the ideas of relativity seem weird, it is only because we don't experience these sorts of interactions in normal life. However, to turn to Bodanis again, we all commonly encounter other kinds of relativity. For instance, with regard to sound. If you're in a park and someone is playing annoying music, you know that if you move to a more distant spot, the music will seem quieter. That's not because the music is quieter, of course, but simply that your position relative to it has changed. To something too small or sluggish to duplicate this experience, a snail, say, the idea that a boombox could seem to 2 observers to produce 2 different volumes of music simultaneously might seem incredible. The most challenging and non-intuitive of all the concepts in the general theory of relativity is the idea that time is part of space. Our instinct is to regard time as eternal, absolute, immutable, to believe that nothing can disturb its steady tick. In fact, according to Einstein, time is variable and ever-changing. It even has shape. It is bound up, inextricably interconnected, in Stephen Hawking's expression, with the three dimensions of space in a curious dimension known as space-time. Space-time is usually explained by asking you to imagine something flat but pliant, a mattress, say, or a sheet of stretched rubber, on which is resting a heavy, round object, such as an iron ball. The weight of the iron ball causes the material on which it is sitting to stretch and sag slightly. This is roughly analogous to the effect that a massive object such as the sun, the iron ball, has on space-time, the material. It stretches and curves and warps it. Now, if you roll a smaller ball across the sheet, it tries to go in a straight line as required by Newton's laws of motion, but as it nears the massive object and the slope of the sagging fabric, it rolls downwards, ineluctably drawn to the more massive object. This is gravity, a product of the bending of space-time. Every object that has mass creates a little depression in the fabric of the cosmos. Thus, the universe, as Dennis Overby has put it, is the ultimate sagging mattress. Gravity on this view is no longer so much a thing as an outcome, not a force, but a byproduct of the warping of space-time, in the words of the physicist Michio Kaku, who goes on, "In some sense, gravity does not exist. What moves the planets and stars is the distortion of space and time." Of course, the sagging mattress analogy can take us only so far, because it doesn't incorporate the effect of time. But then our brains can only take us so far, because it is so nearly impossible to envision a dimension comprising 3 parts space to 1 part time, all interwoven like the threads in a plaid fabric. At all events, I think we can agree that this was an awfully big thought for a young man staring out of the window of a patent office in the capital of Switzerland. Among much else, Einstein's general theory of relativity suggested that the universe must be either expanding or contracting. But Einstein was not a cosmologist, and he accepted the prevailing wisdom that the universe was fixed and eternal. More or less reflexively, he dropped into his equations something called the cosmological constant, which arbitrarily counterbalanced the effects of gravity, serving as a kind of mathematical pause button. Books on the history of science always forgive Einstein this lapse, but it was actually a fairly appalling piece of science, and he knew it. He called it the biggest blunder of my life. Coincidentally, at about the time that Einstein was affixing a cosmological constant to his theory, at the Lowell Observatory in Arizona, an astronomer with a cheerily intergalactic name of Vesto Slipher, who was in fact from Indiana, was taking spectrographic readings of distant stars and discovering that they appeared to be moving away from us. The universe wasn't static. The stars Slipher looked at showed unmistakable signs of a Doppler shift, the same mechanism behind that distinctive stretched-out yum sound cars make as they flash past on a racetrack. The phenomenon also applies to light, and in the case of receding galaxies it is known as a red shift, because light moving away from us shifts towards the red end of the spectrum. Approaching light shifts to blue. Slipher was the first to notice this effect with light and to realize its potential importance for understanding the motions of the cosmos. Unfortunately, no one much noticed him. The Lowell Observatory, you will recall, was a bit of an oddity, thanks to Percival Lowell's obsession with Martian canals, which in the 1910s made it, in every sense, an outpost of astronomical endeavor. Slipher was unaware of Einstein's theory of relativity, and the world was equally unaware of Slipher, so his finding had no impact. Glory instead would pass to a large, massive ego named Edwin Hubble. Hubble was born in 1889, 10 years after Einstein, in a small Missouri town on the edge of the Ozarks, and grew up there, and in Wheaton, Illinois, a suburb of Chicago. His father was a successful insurance executive, so life was always comfortable. And Edwin enjoyed a wealth of physical endowments, too. He was a strong and gifted athlete, charming, smart, and immensely good-looking, handsome almost to a fault, in the description of William H. Cropper, an Adonis, in the words of another admirer. According to his own accounts, he also managed to fit into his life more or less constant acts of valor, rescuing drowning swimmers, leading frightened men to safety across the battlefields of France, embarrassing world champion boxers with knockdown punches in exhibition bouts. It all seemed too good to be true. It was. For all his gifts, Hubble was also an inveterate liar. This was more than a little odd, for Hubble's life was filled from an early age with a level of genuine distinction that was at times almost ludicrously golden. At a single high school track meeting in 1906, he won the pole vault, shot put, discus, hammer throw, standing high jump, and running high jump, and was on the winning mile relay team, that is, 7 first places in one meeting, and came third in the long jump. In the same year, he set a state record for the high jump in Illinois. As a scholar, he was equally proficient, and had no trouble gaining admission to study physics and astronomy at the University of Chicago, where, coincidentally, the head of the department was now Albert Mitchelson. There he was selected to be one of the first Rhodes Scholars at Oxford. 3 years of English life evidently turned his head, for he returned to Wheaton in 1913, wearing an Inverness cape, smoking a pipe, and talking with a peculiarly orotund accent, not quite British, but not quite not, that would remain with him for life. Though he later claimed to have passed most of the second decade of the century practicing law in Kentucky, in fact, he worked as a high school teacher and basketball coach in New Albany, Indiana, before belatedly attaining his doctorate and passing briefly through the Army. He arrived in France 1 month before the armistice, and almost certainly never heard a shot fired in anger. In 1919, now aged 30, he moved to California and took up a position at the Mount Wilson Observatory near Los Angeles. Swiftly and more than a little unexpectedly, he became the most outstanding astronomer of the 20th century. It is worth pausing for a moment to consider just how little was known of the cosmos at this time. Astronomers today believe there are perhaps 140 billion galaxies in the visible universe. That's a huge number, much bigger than merely saying it would lead you to suppose. If galaxies were frozen peas, it would be enough to fill a large auditorium, the old Boston Garden, say, or the Royal Albert Hall. An astrophysicist named Bruce Gregory has actually computed this. In 1919, when Hubble first put his head to the eyepiece, the number of these galaxies that were known to us was exactly 1, the Milky Way. Everything else was thought to be either part of the Milky Way itself or one of many distant peripheral puffs of gas. Hubble quickly demonstrated how wrong that belief was. Over the next decade, Hubble tackled 2 of the most fundamental questions of the universe: how old is it, and how big? To answer both, it is necessary to know 2 things: how far away certain galaxies are, and how fast they are flying away from us, what is known as their recessional velocity. The redshift gives the speed at which galaxies are retiring, but doesn't tell us how far away they are to begin with. For that, you need what are known as standard candles, stars whose brightness can be reliably calculated and used as benchmarks to measure the brightness and hence relative distance of other stars. Hubble's luck was to come along soon after an ingenious woman named Henrietta Swan Leavitt had figured out a way to find these stars. Leavitt worked at the Harvard College Observatory as a computer, as they were known. Computers spent their lives studying photographic plates of stars and making computations, hence the name. It was little more than drudgery by another name, but it was as close as women could get to real astronomy at Harvard, or indeed pretty much anywhere in those days. The system, however unfair, did have certain unexpected benefits. It meant that half the finest minds available were directed to work that would otherwise have attracted little reflective attention, and it ensured that women ended up with an appreciation of the fine structure of the cosmos that often eluded their male counterparts. One Harvard computer, Annie Jump Cannon, used her repetitive acquaintance with the stars to devise a system of stellar classification so practical that it is still in use today. Leavitt's contribution was even more profound. She noticed that a type of star known as a Cepheid variable, after the constellation Cepheus, where the first was identified, pulsated with a regular rhythm, a kind of stellar heartbeat. Cepheids are quite rare, but at least one of them is well known to most of us. Polaris, the pole star, is a Cepheid. We now know that Cepheids throb as they do because they are elderly stars that have moved past their main sequence phase, in the parlance of astronomers, and become red giants. The chemistry of red giants is a little weighty for our purposes here. It requires an appreciation for the properties of singly ionized helium atoms among quite a lot else. But put simply, it means that they burn their remaining fuel in a way that produces a very rhythmic, very reliable brightening and dimming. Leavitt's genius was to realize that by comparing the relative magnitudes of Cepheids at different points in the sky, you could work out where they were in relation to each other. They could be used as standard candles, a term she coined and still in universal use. The method provided only relative distances, not absolute distances, but even so it was the first time that anyone had come up with a usable way to measure the large-scale universe. Just to put these insights into perspective, it is perhaps worth noting that at the time Leavitt and Cannon were inferring fundamental properties of the cosmos from dim smudges of distant stars on photographic plates, the Harvard astronomer William H. Pickering, who could of course peer into a first-class telescope as often as he wanted, was developing his seminal theory that dark patches on the moon were caused by swarms of seasonally migrating insects. Combining Leavitt's cosmic yardstick with Vesto Slipher's handy red shifts, Hubble began to measure selected points in space with a fresh eye. In 1923, he showed that a puff of distant gossamer in the Andromeda constellation, known as M31, wasn't a gas cloud at all, but a blaze of stars, a galaxy in its own right, 100,000 light-years across and at least 900,000 light-years away. The universe was vaster, vastly vaster than anyone had ever supposed. In 1924, Hubble produced a landmark paper, Cepheids in Spiral Nebulae. Nebulae, from the Latin for clouds, was his word for galaxies, showing that the universe consisted not just of the Milky Way, but of lots of independent galaxies, island universes, many of them bigger than the Milky Way and much more distant. This finding alone would have ensured Hubble's reputation, but he now turned to the question of working out just how much vaster the universe was, and made an even more striking discovery. Hubble began to measure the spectra of distant galaxies, the business that Slipher had begun in Arizona. Using Mount Wilson's new 100-inch Hooker telescope and some clever inferences, by the early 1930s he had worked out that all the galaxies in the sky, except for our own local cluster, are moving away from us. Moreover, their speed and distance were neatly proportional. The further away the galaxy, the faster it was moving. This was truly startling. The universe was expanding swiftly and evenly in all directions. It didn't take a huge amount of imagination to read backwards from this and realize that it must therefore have started from some central point. Far from being the stable, fixed, eternal void that everyone had always assumed, this was a universe that had a beginning. It might therefore also have an end. The wonder, as Stephen Hawking has noted, is that no one had hit on the idea of the expanding universe before. A static universe, as should have been obvious to Newton and every thinking astronomer since, would collapse in upon itself. There was also the problem that if stars had been burning indefinitely in a static universe, they'd have made the whole intolerably hot, certainly much too hot for the likes of us. An expanding universe resolved much of this at a stroke. Hubble was a much better observer than a thinker, and didn't immediately appreciate the full implications of what he had found. Partly this was because he was woefully ignorant of Einstein's general theory of relativity. This was quite remarkable, because for one thing, Einstein and his theory were world-famous by now. Moreover, in 1929, Albert Michelson, now in his twilight years but still one of the world's most alert and esteemed scientists, accepted a position at Mount Wilson to measure the velocity of light with his trusty interferometer, and must surely have at least mentioned to him the applicability of Einstein's theory to his own findings. At all events, Hubble failed to make theoretical hay when the chance was there. Instead, it was left to a Belgian priest-scholar with a Ph.D. from MIT, named Georges Lemaitre, to bring together the two strands in his own fireworks theory, which suggested that the universe began as a geometrical point, a primeval atom, which burst into glory and had been moving apart ever since. It was an idea that very neatly anticipated the modern conception of the Big Bang, but was so far ahead of its time that Lemaitre seldom gets more than the sentence or two that we have given him here. The world would need additional decades, and the inadvertent discovery of cosmic background radiation by Penzias and Wilson at their hissing antenna in New Jersey, before the Big Bang would begin to move from interesting idea to established theory. Neither Hubble nor Einstein would be much of a part of that big story. Though no one would have guessed it at the time, both men had done about as much as they were ever going to do. In 1936, Hubble produced a popular book called The Realm of the Nebulae, which explained in flattering style his own considerable achievements. Here at last he showed that he had acquainted himself with Einstein's theory, up to a point, anyway. He gave it 4 pages out of about 200. Hubble died of a heart attack in 1953. One last small oddity awaited him. For reasons cloaked in mystery, his wife declined to have a funeral, and never revealed what she did with his body. Half a century later, the whereabouts of the century's greatest astronomer remain unknown. For a memorial, you must look to the sky, and the Hubble Space Telescope, launched in 1990 and named in his honor. Chapter 9. The Mighty Atom. While Einstein and Hubble were productively unraveling the large-scale structure of the cosmos, others were struggling to understand something closer to hand, but in its way just as remote, the tiny and ever-mysterious atom. The great Caltech physicist Richard Feynman once observed that if you had to reduce scientific history to one important statement, it would be, all things are made of atoms. They are everywhere, and they constitute everything. Look around you. It is all atoms. Not just the solid things like walls and tables and sofas, but the air in between. And they are there in numbers that you really cannot conceive. The basic working arrangement of atoms is the molecule, from the Latin for little mass. A molecule is simply 2 or more atoms working together in a more or less stable arrangement. Add 2 atoms of hydrogen to one of oxygen, and you have a molecule of water. Chemists tend to think in terms of molecules rather than elements, in much the way that writers tend to think in terms of words and not letters, so it is molecules they count, and these are numerous, to say the least. At sea level, at a temperature of 0 degrees Celsius, 1 cubic centimeter of air, that is, a space about the size of a sugar cube, will contain 45 billion molecules, and they are in every single cubic centimeter you see around you. Think how many cubic centimeters there are in the world outside your window, how many sugar cubes it would take to fill that view. Then think how many it would take to build a universe. Atoms, in short, are very abundant. They are also fantastically durable. Because they are so long-lived, atoms really get around. Every atom you possess has almost certainly passed through several stars and been part of millions of organisms on its way to becoming you. We are each so atomically numerous and so vigorously recycled at death that a significant number of our atoms, up to 1 billion for each of us, it has been suggested, probably once belonged to Shakespeare. 1 billion more each came from Buddha and Genghis Khan and Beethoven and any other historical figure you care to name. The personages have to be historical, apparently, as it takes the atoms some decades to become thoroughly redistributed. However much you may wish it, you are not yet one with Elvis Presley. So we are all reincarnations, though short-lived ones. When we die, our atoms will disassemble and move off to find new uses elsewhere, as part of a leaf, or other human being, or drop of dew. Atoms themselves, however, go on practically forever. Nobody actually knows how long an atom can survive, but according to Martin Rees, it is probably about 10 to the 35th years, a number so big that even I am happy to express it in mathematical notation. Above all, atoms are tiny, very tiny indeed. 500,000 of them, lined up shoulder to shoulder, could hide behind a human hair. On such a scale, an individual atom is essentially impossible to imagine. But we can, of course, try. Start with a millimeter. Now imagine that divided into 1,000 equal widths. Each of those widths is a micron. This is the scale of microorganisms. A typical paramecium, for instance, a tiny single-celled freshwater creature, is about 2 microns wide, 0.002 millimeters, which is really very small. If you wanted to see with your naked eye a paramecium swimming in a drop of water, you would have to enlarge the drop until it was some 12 meters across. However, if you wanted to see the atoms in the same drop, you would have to make the drop 24 kilometers across. Atoms, in other words, exist on a scale of minuteness of another order altogether. To get down to the scale of atoms, you would need to take each one of those micron slices and shave it into 10,000 finer widths. That's the scale of an atom, 1/10,000,000th of a millimeter. It is a degree of slenderness way beyond the capacity of our imaginations, but you can get some idea of the proportions if you bear in mind that one atom is to a millimeter, as the thickness of a sheet of paper is to the height of the Empire State Building. It is, of course, the abundance and extreme durability of atoms that make them so useful, and the tininess that makes them so hard to detect and understand. The realization that atoms are these three things, small, numerous, and practically indestructible, and that all things are made from them, first occurred not to Antoine Laurent Lavoisier, as you might expect, or even to Henry Cavendish or Humphrey Davy, but rather to a spare and lightly educated English Quaker named John Dalton, whom we first encountered in Chapter 7. Dalton was born in 1766 on the edge of the Lake District, near Cockermouth, to a family of poor and devout Quaker weavers. 4 years later, the poet William Wordsworth would also join the world at Cockermouth. He was an exceptionally bright student, so very bright indeed that at the improbably youthful age of 12 he was put in charge of the local Quaker school. This perhaps says as much about the school as about Dalton's precocity, but perhaps not. We know from his diaries that at about this time he was reading Newton's Principia in the original Latin, and other works of a similarly challenging nature. At 15, still schoolmastering, he took a job in the nearby town of Kendal, and a decade after that he moved to Manchester, whence he scarcely stirred for the remaining 50 years of his life. In Manchester he became something of an intellectual whirlwind, producing books and papers on subjects ranging from meteorology to grammar. Color blindness, a condition from which he suffered, was for a long time called Daltonism because of his studies. But it was a plump book called A New System of Chemical Philosophy, published in 1808, that established his reputation. There, in a short chapter of just 5 pages, out of the book's more than 900, people of learning first encountered atoms in something approaching their modern conception. Dalton's simple insight was that at the root of all matter are exceedingly tiny, irreducible particles. We might as well attempt to introduce a new planet into the solar system or annihilate one already in existence as to create or destroy a particle of hydrogen, he wrote. Neither the idea of atoms nor the term itself was exactly new. Both had been developed by the ancient Greeks. Dalton's contribution was to consider the relative sizes and characters of these atoms and how they fit together. He knew, for instance, that hydrogen was the lightest element, so he gave it an atomic weight of 1. He believed also that water consisted of 7 parts of oxygen to 1 of hydrogen, and so he gave oxygen an atomic weight of 7. By such means was he able to arrive at the relative weights of the known elements. He wasn't always terribly accurate. Oxygen's atomic weight is actually 16, not 7. But the principle was sound and formed the basis for all of modern chemistry and much of the rest of modern science. The work made Dalton famous, albeit in a low-key English Quaker sort of way. In 1826, the French chemist P.J. Pelletier traveled to Manchester to meet the atomic hero. Pelletier expected to find him attached to some grand institution, so he was astounded to discover him teaching elementary arithmetic to boys in a small school on a back street. According to the scientific historian E.J. Holmyard, a confused Pelletier, upon beholding the great man, stammered, "Est-ce que j'ai l'honneur de m'adresser à Monsieur Dalton?" For he could hardly believe his eyes that this was the chemist of European fame, teaching a boy his first 4 rules. "Yes," said the matter-of-fact Quaker, "wilt thou sit down whilst I put this lad right about his arithmetic?" Although Dalton tried to avoid all honours, he was elected to the Royal Society against his wishes, showered with medals, and given a handsome government pension. When he died in 1844, 40,000 people viewed the coffin, and the funeral cortege stretched for 2 miles. His entry in the Dictionary of National Biography is one of the longest, rivaled in length among 19th-century men of science only by those of Darwin and Lyell. For a century after Dalton made his proposal, it remained entirely hypothetical, and a few eminent scientists, notably the Viennese physicist Ernst Mach, for whom is named the speed of sound, doubted the existence of atoms at all. "Atoms cannot be perceived by the senses, they are things of thought," he wrote. Such was the skepticism with which the existence of atoms was viewed in the German-speaking world in particular, that it was said to have played a part in the suicide of the great theoretical physicist and atomic enthusiast Ludwig Boltzmann in 1906. It was Einstein who provided the first incontrovertible evidence of atoms' existence with his paper on Brownian motion in 1905. But this attracted little attention, and in any case Einstein was soon to become consumed with his work on general relativity. So the first real hero of the atomic age, if not the first personage on the scene, was Ernest Rutherford. Rutherford was born in 1871 in the back blocks of New Zealand to parents who had emigrated from Scotland to raise a little flax and a lot of children, to paraphrase Stephen Weinberg. Growing up in a remote part of a remote country, he was about as far from the mainstream of science as it was possible to be. But in 1895 he won a scholarship that took him to the Cavendish Laboratory at Cambridge University, which was about to become the hottest place in the world to do physics. Physicists are notoriously scornful of scientists from other fields. When the great Austrian physicist Wolfgang Pauli's wife left him for a chemist, he was staggered with disbelief. "Had she taken a bullfighter, I would have understood," he remarked in wonder to a friend. "But a chemist!" It was a feeling Rutherford would have understood. "All science is either physics or stamp collecting," he once said, in a line that has been used many times since. There is a certain engaging irony, therefore, that his award of the Nobel Prize in 1908 was in chemistry, not physics. Rutherford was a lucky man, lucky to be a genius, but even luckier to live at a time when physics and chemistry were so exciting and so compatible, his own sentiments notwithstanding. Never again would they quite so comfortably overlap. For all his success, Rutherford was not an especially brilliant man, and was actually pretty terrible at mathematics. Often during lectures he would get so lost in his own equations that he would give up halfway through and tell the students to work it out for themselves. According to his longtime colleague James Chadwick, discoverer of the neutron, he wasn't even particularly clever at experimentation. He was simply tenacious and open-minded. For brilliance, he substituted shrewdness and a kind of daring. His mind, in the words of one biographer, was always operating out towards the frontiers, as far as he could see, and that was a great deal further than most other men. Confronted with an intractable problem, he was prepared to work at it harder and longer than most people, and to be more receptive to unorthodox explanations. His greatest breakthrough came because he was prepared to spend immensely tedious hours sitting at a screen counting alpha particle scintillations, as they were known, the sort of work that would normally have been farmed out. He was one of the first, possibly the very first, to see that the power inherent in the atom could, if harnessed, make bombs powerful enough to make this old world vanish in smoke. Physically, he was big and booming, with a voice that made the timid shrink. Once, when told that Rutherford was about to make a radio broadcast across the Atlantic, a colleague dryly asked, "Why use radio?" He also had a huge amount of good-natured confidence. When someone remarked to him that he seemed always to be at the crest of a wave, he responded, "Well, after all, I made the wave, didn't I?" C.P. Snow recalled how, in a Cambridge tailor's, he overheard Rutherford remark, "Every day I grow in girth, and in mentality." But both girth and fame were far ahead of him in 1895 when he fetched up at the Cavendish. It was a singularly eventful period in science. In the year of Rutherford's arrival in Cambridge, Wilhelm Röntgen discovered X-rays at the University of Würzburg in Germany. The next year, Henri Becquerel discovered radioactivity. And the Cavendish itself was about to embark on a long period of greatness. In 1897, J.J. Thomson and colleagues would discover the electron there. In 1911, C.T.R. Wilson would produce the first particle detector there, as we shall see. And in 1932, James Chadwick would discover the neutron there. Further still in the future, in 1953, James Watson and Francis Crick would discover the structure of DNA at the Cavendish. In the beginning, Rutherford worked on radio waves, and with some distinction. He managed to transmit a crisp signal more than a mile, a very reasonable achievement for the time. But he gave it up when he was persuaded by a senior colleague that radio had little future. On the whole, however, Rutherford didn't thrive at the Cavendish, and after 3 years there, feeling he was going nowhere, he took a post at McGill University in Montreal, where he began his long and steady rise to greatness. By the time he received his Nobel Prize for investigations into the disintegration of the elements and the chemistry of radioactive substances, according to the official citation, he had moved on to Manchester University, and it was there, in fact, that he would do his most important work in determining the structure and nature of the atom. By the early 20th century, it was known that atoms were made of parts. Thomson's discovery of the electron had established that, but it wasn't known how many parts there were, or how they fitted together, or what shape they took. Some physicists thought that atoms might be cube-shaped, because cubes can be packed together so neatly without any wasted space. The more general view, however, was that an atom was more like a currant bun, or a plum pudding, a dense, solid object that carried a positive charge, but that was studded with negatively charged electrons, like the currents in a current bun. In 1910, Rutherford, assisted by his student Hans Geiger, who would later invent the radiation detector that bears his name, fired ionized helium atoms, or alpha particles, at a sheet of gold foil. To Rutherford's astonishment, some of the particles bounced back. It was as if, he said, he had fired a 15-inch shell at a sheet of paper, and it rebounded into his lap. This was just not supposed to happen. After considerable reflection, he realized there could be only one possible explanation. The particles that bounced back were striking something small and dense at the heart of the atom, while the other particles sailed through unimpeded. An atom, Rutherford realized, was mostly empty space, with a very dense nucleus at the center. This was a most gratifying discovery, but it presented one immediate problem. By all the laws of conventional physics, atoms shouldn't therefore exist. Let us pause for a moment and consider the structure of the atom as we know it now. Every atom is made from three kinds of elementary particles: protons, which have a positive electrical charge, electrons, which have a negative electrical charge, and neutrons, which have no charge. Protons and neutrons are packed into the nucleus, while electrons spin around outside. The number of protons is what gives an atom its chemical identity. An atom with one proton is an atom of hydrogen. One with two protons is helium. With three protons, lithium, and so on up the scale. Each time you add a proton, you get a new element. Because the number of protons in an atom is always balanced by an equal number of electrons, you will sometimes see it written that it is the number of electrons that defines an element. It comes to the same thing. The way it was explained to me is that protons give an atom its identity, electrons its personality. Neutrons don't influence an atom's identity, but they do add to its mass. The number of neutrons is generally about the same as the number of protons, but they can vary up and down slightly. Add or subtract a neutron or two, and you get an isotope. The terms you hear in reference to dating techniques in archaeology refer to isotopes, carbon-14, for instance, which is an atom of carbon with 6 protons and 8 neutrons, the 14 being the sum of the two. Neutrons and protons occupy the atom's nucleus. The nucleus of an atom is tiny, only 1/1,000,000th of a billionth of the full volume of the atom, but fantastically dense, since it contains virtually all the atom's mass. As Cropper has put it, if an atom were expanded to the size of a cathedral, the nucleus would be only about the size of a fly, but a fly many thousands of times heavier than the cathedral. It was this spaciousness, this resounding unexpected roominess, that had Rutherford scratching his head in 1910. It is still a fairly astounding notion to consider that atoms are mostly empty space, and that the solidity we experience all around us is an illusion. When two objects come together in the real world, billiard balls are most often used for illustration, they don't actually strike each other. Rather, as Timothy Ferris explains, the negatively charged fields of the two balls repel each other. Were it not for their electrical charges, they could, like galaxies, pass right through each other unscathed. When you sit in a chair, you are actually not sitting there, but levitating above it, at a height of 1 angstrom, 100 millionth of a centimeter, your electrons and its electrons implacably opposed to any closer intimacy. The picture of an atom that nearly everyone has in mind is of an electron or two flying around a nucleus, like planets orbiting a sun. This image was created in 1904, based on little more than clever guesswork, by a Japanese physicist named Hantaro Nagaoka. It is completely wrong, but durable just the same. As Isaac Asimov liked to note, it inspired generations of science fiction writers to create stories of worlds within worlds, in which atoms become tiny inhabited solar systems, or our own solar system turns out to be merely a mote in some much larger scheme. Even now, CERN, the European Organization for Nuclear Research, uses Nagaoka's image as a logo on its website. In fact, as physicists were soon to realize, electrons are not like orbiting planets at all, but more like the blades of a spinning fan, managing to fill every bit of space in their orbit simultaneously, but with the crucial difference that the blades of a fan only seem to be everywhere at once. Electrons are. Needless to say, very little of this was understood in 1910 or for many years afterwards. Rutherford's finding presented some large and immediate problems, not least that no electron should be able to orbit a nucleus without crashing. Conventional electrodynamic theory demanded that a flying electron should run out of energy very quickly, in only an instant or so, and spiral into the nucleus, with disastrous consequences for both. There was also the problem of how protons, with their positive charges, could bundle together inside the nucleus without blowing themselves and the rest of the atom apart. Clearly, whatever was going on down there in the world of the very small was not governed by the laws that applied in the macro world, where our expectations reside. As physicists began to delve into this subatomic realm, they realized that it wasn't merely different from anything we knew, but different from anything ever imagined. Because atomic behavior is so unlike ordinary experience, Richard Feynman once observed, it is very difficult to get used to, and it appears peculiar and mysterious to everyone, both to the novice and to the experienced physicist. When Feynman made that comment, physicists had had half a century to adjust to the strangeness of atomic behavior. So think how it must have felt to Rutherford and his colleagues in the early 1910s, when it was all brand new. One of the people working with Rutherford was a mild and affable young Dane named Niels Bohr. In 1913, while puzzling over the structure of the atom, Bohr had an idea so exciting that he postponed his honeymoon to write what became a landmark paper. Because physicists couldn't see anything so small as an atom, they had to try to work out its structure from how it behaved when they did things to it, as Rutherford had done by firing alpha particles at foil. Sometimes, not surprisingly, the results of these experiments were puzzling. One puzzle that had been around for a long time was to do with spectrum readings of the wavelengths of hydrogen. These produced patterns showing that hydrogen atoms emitted energy at certain wavelengths but not others. It was rather as if someone under surveillance kept turning up at particular locations but was never observed traveling between them. No one could understand why this should be. It was while puzzling over this problem that Bohr was struck by a solution and dashed off his famous paper. Called On the Constitutions of Atoms and Molecules, the paper explained how electrons could keep from falling into the nucleus by suggesting that they could occupy only certain well-defined orbits. According to the new theory, an electron moving between orbits would disappear from one and reappear instantaneously in another without visiting the space between. This idea, the famous quantum leap, is of course utterly strange, but it was too good not to be true. It not only kept electrons from spiraling catastrophically into the nucleus, it also explained hydrogen's bewildering wavelengths. The electrons only appeared in certain orbits because they only existed in certain orbits. It was a dazzling insight, and it won Bohr the 1922 Nobel Prize in Physics, the year after Einstein received his. Meanwhile, the tireless Rutherford, now back at Cambridge, having succeeded J.J. Thomson as head of the Cavendish Laboratory, came up with a model that explained why the nuclei didn't blow up. He saw that the positive charge of the protons must be offset by some type of neutralizing particles, which he called neutrons. The idea was simple and appealing, but not easy to prove. Rutherford's associate, James Chadwick, devoted 11 intensive years to hunting for neutrons before finally succeeding in 1932. He, too, was awarded a Nobel Prize in Physics in 1935. As Bors and his colleagues point out in their history of the subject, the delay in discovery was probably a very good thing, as mastery of the neutron was essential to the development of the atomic bomb. Because neutrons have no charge, they aren't repelled by the electrical fields at the heart of an atom, and thus could be fired like tiny torpedoes into an atomic nucleus, setting off the destructive process known as fission. Had the neutron been isolated in the 1920s, they note, it is very likely the atomic bomb would have been developed first in Europe, undoubtedly by the Germans. As it was, the Europeans had their hands full trying to understand the strange behavior of the electron. The principal problem they faced was that the electron sometimes behaved like a particle and sometimes like a wave. This impossible duality drove physicists nearly mad. For the next decade, all across Europe, they furiously thought and scribbled and offered competing hypotheses. In France, Prince Louis-Victor de Broglie, the scion of a ducal family, found that certain anomalies in the behavior of electrons disappeared when one regarded them as waves. The observation excited the attention of the Austrian Erwin Schrödinger, who made some deft refinements and devised a handy system called wave mechanics. At almost the same time, the German physicist Werner Heisenberg came up with a competing theory called matrix mechanics. This was so mathematically complex that hardly anyone really understood it, including Heisenberg himself. "I do not even know what a matrix is," Heisenberg despaired to a friend at one point, but it did seem to solve certain problems that Schrödinger's waves failed to explain. The upshot is that physics had two theories, based on conflicting premises that produced the same results. It was an impossible situation. Finally, in 1926, Heisenberg came up with a celebrated compromise, producing a new discipline that came to be known as quantum mechanics. At the heart of it was Heisenberg's uncertainty principle, which states that the electron is a particle, but a particle that can be described in terms of waves. The uncertainty around which the theory is built is that we can know the path an electron takes as it moves through a space, or we can know where it is at a given instant, but we cannot know both. Any attempt to measure one will unavoidably disturb the other. This isn't a matter of simply needing more precise instruments. It is an immutable property of the universe. What this means in practice is that you can never predict where an electron will be at any given moment. You can only list its probability of being there. In a sense, as Dennis Overby has put it, an electron doesn't exist until it is observed. Or, put slightly differently, until it is observed, an electron must be regarded as being at once everywhere and nowhere. If this seems confusing, you may take some comfort in knowing that it was confusing to physicists, too. Overby notes, Bohr once commented that a person who wasn't outraged on first hearing about quantum theory didn't understand what had been said. Heisenberg, when asked how one could envision an atom, replied, "Don't try." So the atom turned out to be quite unlike the image that most people had created. The electron doesn't fly around the nucleus like a planet around its sun, but instead takes on the more amorphous aspect of a cloud. The shell of an atom isn't some hard, shiny casing, as illustrations sometimes encourage us to suppose, but simply the outermost of these fuzzy electron clouds. The cloud itself is essentially just a zone of statistical probability, marking the area beyond which the electron only very seldom strays. Thus, an atom, if you could see it, would look more like a very fuzzy tennis ball than a hard-edged metallic sphere, but not much like either, or indeed like anything you've ever seen. We are, after all, dealing here with a world very different from the one we see around us. It seemed as if there was no end of strangeness. For the first time, as James Trefil has put it, scientists had encountered an area of the universe that our brains just aren't wired to understand. Or as Feynman expressed it, things on a small scale behave nothing like things on a large scale. As physicists delved deeper, they realized they had found a world not only where electrons could jump from one orbit to another without traveling across any intervening space, but where matter could pop into existence from nothing at all, provided, in the words of Alan Lightman of MIT, it disappears again with sufficient haste. Perhaps the most arresting of quantum improbabilities is the idea arising from Wolfgang Pauli's exclusion principle of 1925 that certain pairs of subatomic particles, even when separated by the most considerable distances, can each instantly know what the other is doing. Particles have a quality known as spin, and according to quantum theory, the moment you determine the spin of one particle, its sister particle, no matter how distant away, will immediately begin spinning in the opposite direction and at the same rate. It is as if, in the words of the science writer Lawrence Joseph, you had two identical pool balls, one in Ohio and the other in Fiji, and that the instant you sent one spinning, the other would immediately spin in a contrary direction at precisely the same speed. Remarkably, the phenomenon was proved in 1997 when physicists at the University of Geneva sent photons 7 miles in opposite directions and demonstrated that interfering with one provoked an instantaneous response in the other. Things reached such a pitch that at one conference Bohr remarked of a new theory that the question was not whether it was crazy, but whether it was crazy enough. To illustrate the non-intuitive nature of the quantum world, Schrödinger offered a famous thought experiment in which a hypothetical cat was placed in a box with one atom of a radioactive substance attached to a vial of hydrocyanic acid. If the particle degraded within an hour, it would trigger a mechanism that would break the vial and poison the cat. If not, the cat would live. But we could not know which was the case, so there was no choice scientifically but to regard the cat as 100% alive and 100% dead at the same time. This means, as Stephen Hawking has observed with a touch of understandable excitement, that one cannot predict future events exactly if one cannot even measure the present state of the universe precisely. Because of its oddities, many physicists disliked quantum theory, or at least certain aspects of it, and none more so than Einstein. This was more than a little ironic, since it was he, in his Annus Mirabilis of 1905, who had so persuasively explained how photons of light could sometimes behave like particles and sometimes like waves, the notion at the very heart of the new physics. "Quantum theory is very worthy of regard," he observed politely, but he really didn't like it. "God doesn't play dice," he said. Einstein couldn't bear the notion that God could create a universe in which some things were forever unknowable. Moreover, the idea of action at a distance, that one particle could instantaneously influence another trillions of miles away, was a stark violation of the special theory of relativity. Nothing could outrace the speed of light. And yet here were physicists insisting that somehow, at the subatomic level, information could. No one, incidentally, has ever explained how the particles achieve this feat. Scientists have dealt with this problem, according to the physicist Yakir Aharonov, by not thinking about it. Above all, there was the problem that quantum physics introduced a level of untidiness that hadn't previously existed. Suddenly you needed two sets of laws to explain the behavior of the universe, quantum theory for the world of the very small, and relativity for the larger universe beyond. The gravity of relativity theory was brilliant at explaining why planets orbited suns, or why galaxies tended to cluster, but turned out to have no influence at all at the particle level. To explain what kept atoms together, other forces were needed. And in the 1930s two were discovered, the strong nuclear force and the weak nuclear force. The strong force binds atoms together. It's what allows protons to bed down together in the nucleus. The weak force engages in more miscellaneous tasks, mostly to do with controlling the rates of certain sorts of radioactive decay. The weak nuclear force, despite its name, is 10 billion times stronger than gravity, and the strong nuclear force is more powerful still, vastly so, in fact. But their influence extends to only the tiniest distances. The grip of the strong force reaches out only to about 100,000th of the diameter of an atom. That's why the nuclei of atoms are so compacted and dense, and why elements with big, crowded nuclei tend to be so unstable. The strong force just can't hold on to all the protons. The upshot of all this is that physics ended up with two bodies of laws, one for the world of the very small, one for the universe at large, leading quite separate lives. Einstein disliked that, too. He devoted the rest of his life to searching for a way to tie up these loose ends by finding a grand unified theory, and always failed. From time to time he thought he had it, but it always unraveled on him in the end. As time passed, he became increasingly marginalized and even a little pitied. Almost without exception, wrote Snow, his colleagues thought and still think that he wasted the second half of his life. Elsewhere, however, real progress was being made. By the mid-1940s, scientists had reached a point where they understood the atom at an extremely profound level, as they all too effectively demonstrated in August 1945 by exploding a pair of atomic bombs over Japan. By this point, physicists could be excused for thinking that they had just about conquered the atom. In fact, everything in particle physics was about to get a whole lot more complicated. But before we take up that slightly exhausting story, we must bring another strand of our history up to date by considering an important and salutary tale of avarice, deceit, bad science, several needless deaths, and the final determination of the age of the earth. Chapter 10. Getting the Lead Out. In the late 1940s, a graduate student at the University of Chicago named Claire Patterson, who was, first name notwithstanding, an Iowa farm boy by origin, was using a new method of lead isotope measurement to try to get a definitive age for the Earth at last. Unfortunately, all his rock samples became contaminated, usually wildly so. Most contained something like 200 times the levels of lead that would normally be expected to occur. Many years would pass before Patterson realized that the reason for this lay with a regrettable Ohio inventor named Thomas Midgley, Jr. Midgley was an engineer by training, and the world would no doubt have been a safer place if he had stayed so. Instead, he developed an interest in the industrial applications of chemistry. In 1921, while working for the General Motors Research Corporation in Dayton, Ohio, he investigated a compound called tetraethyl lead, also known confusingly as lead tetraethyl, and discovered that it significantly reduced the juddering condition known as engine knock. Even though lead was widely known to be dangerous, by the early years of the 20th century it could be found in all manner of consumer products. Food came in cans sealed with lead solder. Water was often stored in lead-lined tanks. Lead arsenate was sprayed onto fruit as a pesticide. Lead even came as part of the composition of toothpaste tubes. Hardly a product existed that didn't bring a little lead into consumers' lives. However, nothing gave it a greater and more lasting intimacy than its addition to motor fuel. Lead is a neurotoxin. Get too much of it and you can irreparably damage the brain and central nervous system. Among the many symptoms associated with overexposure are blindness, insomnia, kidney failure, hearing loss, cancer, palsies, and convulsions. In its most acute form, it produces abrupt and terrifying hallucinations, disturbing to victims and onlookers alike, which generally then give way to coma and death. You really don't want to get too much lead into your system. On the other hand, lead was easy to extract and work, and almost embarrassingly profitable to produce industrially, and tetraethyl lead did indubitably stop engines from knocking. So, in 1923, three of America's largest corporations, General Motors, DuPont, and Standard Oil of New Jersey, formed a joint enterprise called the Ethyl Gasoline Corporation, later shortened to simply Ethyl Corporation, with a view to making as much tetraethyl lead as the world was willing to buy, and that proved to be a very great deal. They called their additive ethyl because it sounded friendlier and less toxic than lead, and introduced it for public consumption in more ways than most people realized on the 1st of February 1923. Almost at once, production workers began to exhibit the staggered gait and confused faculties that mark the recently poisoned. Also, almost at once, the Ethyl Corporation embarked on a policy of calm but unyielding denial that would serve it well for decades. As Sharon Birch McGrain notes in her absorbing history of industrial chemistry, Prometheans in the Lab, when employees at one plant developed irreversible delusions, a spokesman blandly informed reporters, "These men probably went insane because they worked too hard." Altogether, at least 15 workers died in the early days of production of leaded gasoline, and untold numbers of others became ill, often violently so. The exact numbers are unknown, because the company nearly always managed to hush up news of embarrassing leakages, spills, and poisonings. At times, however, suppressing the news became impossible. Most notably in 1924, when, in a matter of days, 5 production workers died, and 35 more were turned into permanent staggering wrecks at a single, ill-ventilated facility. As rumors circulated about the dangers of the new product, Ethyl's ebullient inventor, Thomas Midgley, decided to hold a demonstration for reporters to allay their concerns. As he chatted away about the company's commitment to safety, he poured tetraethyl lead over his hands, then held a beaker of it to his nose for 60 seconds, claiming all the while that he could repeat the procedure daily without harm. In fact, Midgley knew only too well the perils of lead poisoning. He had himself been made seriously ill from overexposure a few months earlier, and now, except when reassuring journalists, never went near the stuff if he could help it. Buoyed up by the success of leaded petrol, Midgley now turned to another technological problem of the age. Refrigerators in the 1920s were often appallingly risky because they used insidious and dangerous gases that sometimes seeped out. One leak from a refrigerator at a hospital in Cleveland, Ohio, in 1929 killed more than 100 people. Midgley set out to create a gas that was stable, non-flammable, non-corrosive, and safe to breathe. With an instinct for the regrettable that was almost uncanny, he invented chlorofluorocarbons, or CFCs. Seldom has an industrial product been more swiftly or unfortunately embraced. CFCs went into production in the early 1930s and found 1,000 applications in everything from car air conditioners to deodorant sprays, before it was noticed half a century later that they were devouring the ozone in the stratosphere. As you will be aware, this was not a good thing. Ozone is a form of oxygen in which each molecule bears 3 atoms of oxygen instead of the normal 2. It is a bit of a chemical oddity, in that at ground level it is a pollutant, while way up in the stratosphere it is beneficial, since it soaks up dangerous ultraviolet radiation. Beneficial ozone is not terribly abundant, however. If it were distributed evenly throughout the stratosphere, it would form a layer just 2 millimeters or so thick. That is why it is so easily disturbed. Chlorofluorocarbons are also not very abundant. They constitute only about 1 part per billion of the atmosphere as a whole, but they are extravagantly destructive. A single kilogram of CFCs can capture and annihilate 70,000 kilograms of atmospheric ozone. CFCs also hang around for a long time, about a century on average, wreaking havoc all the while. And they are great heat sponges. A single CFC molecule is about 10,000 times more efficient at exacerbating greenhouse effects than a molecule of carbon dioxide, and carbon dioxide is, of course, no slouch itself as a greenhouse gas. In short, chlorofluorocarbons may ultimately prove to be just about the worst invention of the 20th century. Midgley never knew this because he died long before anyone realized how destructive CFCs were. His death was itself memorably unusual. After becoming crippled with polio, Midgley invented a contraption involving a series of motorized pulleys that automatically raised or turned him in bed. In 1944, he became entangled in the cords as the machine went into action and was strangled. If you were interested in finding out the ages of things, the University of Chicago in the 1940s was the place to be. Willard Libby was in the process of inventing radiocarbon dating, allowing scientists to get an accurate reading of the age of bones and other organic remains, something they had never been able to do before. Up to this time, the oldest reliable dates went back no further than the First Dynasty in Egypt, about 3000 BC. No one could confidently say, for instance, when the last ice sheets had retreated, or at what time in the past the Cro-Magnon people had decorated the caves of Lascaux in France. Libby's idea was so useful that he would be awarded a Nobel Prize for it in 1960. It was based on the realization that all living things have within them an isotope of carbon called carbon-14, which begins to decay at a measurable rate the instant they die. Carbon-14 has a half-life, that is, the time it takes for half of any sample to disappear, of about 5,600 years. So, by working out how much of a given sample of carbon had decayed, Libby could get a good fix on the age of an object, though only up to a point. After 8 half-lives, only 0.39% of the original radioactive carbon remains, which is too little to make a reliable measurement. So radiocarbon dating works only for objects up to 40,000 or so years old. Curiously, just as the technique was becoming widespread, certain flaws within it became apparent. To begin with, it was discovered that one of the basic components of Libby's formula, known as the decay constant, was out by about 3%. By this time, however, thousands of measurements had been taken throughout the world. Rather than restate every one, scientists decided to keep the inaccurate constant. Thus, Tim Flannery notes, every raw radiocarbon date you read today is given as too young by around 3%. The problems didn't quite stop there. It was also quickly discovered that carbon-14 samples can be easily contaminated with carbon from other sources. A tiny scrap of vegetable matter, for instance, that has been collected with a sample and not noticed. For younger samples, those under 20,000 years or so, slight contamination does not always matter so much. But for older samples, it can be a serious problem because so few remaining atoms are being counted. In the first instance, to borrow from Flannery, it is like miscounting by $1 when counting to 1,000. In the second, it is more like miscounting by $1 when you only have $2 to count. Libby's method was also based on the assumption that the amount of carbon-14 in the atmosphere and the rate at which it has been absorbed by living things has been consistent throughout history. In fact, it hasn't been. We now know that the volume of atmospheric carbon-14 varies depending on how well or not the Earth's magnetism is deflecting cosmic rays, and that can vary significantly over time. This means that some carbon-14 dates are more dubious than others. Among the more dubious are dates just around the time that people first came to the Americas, which is one of the reasons the matter is so perennially in dispute. Finally, and perhaps a little unexpectedly, readings can be thrown out by seemingly unrelated external factors, such as the diets of those whose bones are being tested. One recent case involved the long-running debate over whether syphilis originated in the New World or the Old. Archaeologists in Hull found that monks in a monastery graveyard had suffered from syphilis, but the initial conclusion that the monks had done so before Columbus's voyage was cast into doubt by the realization that they had eaten a lot of fish, which could make their bones appear to be older than in fact they were. The monks may well have had syphilis, but how it got to them and when remained tantalizingly unresolved. Because of the accumulated shortcomings of carbon-14, scientists devised other methods of dating ancient materials, among them thermoluminescence, which measures electrons trapped in clays, and electron spin resonance, which involves bombarding a sample with electromagnetic waves and measuring the vibrations of the electrons. But even the best of these could not date anything older than about 200,000 years, and they couldn't date inorganic materials like rocks at all, which is, of course, what you need to do if you wish to determine the age of your planet. The problems of dating rocks were such that at one point almost everyone in the world had given up on them. Had it not been for a determined English professor named Arthur Holmes, the quest might well have fallen into abeyance altogether. Holmes was heroic, as much for the obstacles he overcame as for the results he achieved. By the 1920s, when he was in the prime of his career, geology had slipped out of fashion. Physics was the new excitement of the age, and had become severely underfunded, particularly in Britain, its spiritual birthplace. At Durham University, Holmes was for many years the entire geology department. Often he had to borrow or patch together equipment in order to pursue his radiometric dating of rocks. At one point, his calculations were effectively held up for a year while he waited for the university to provide him with a simple adding machine. Occasionally, he had to drop out of academic life altogether to earn enough to support his family. For a time, he ran a curio shop in Newcastle upon Tyne. And sometimes he could not even afford the £5 annual membership fee for the Geological Society. The technique Holmes used in his work was theoretically straightforward, and arose directly from the process first observed by Ernest Rutherford in 1904, by which some atoms decay from one element into another at a rate predictable enough that you can use them as clocks. If you know how long it takes for potassium-40 to become argon-40, and you measure the amounts of each in a sample, you can work out how old a material is. Holmes's contribution was to measure the decay rate of uranium into lead to calculate the age of rocks, and thus, he hoped, of the Earth. But there were many technical difficulties to overcome. Holmes also needed, or at least would very much have appreciated, sophisticated gadgetry of a sort that could make very fine measurements from tiny samples, and as we have seen, it was all he could do to get a simple adding machine. So it was quite an achievement when in 1946 he was able to announce with some confidence that the Earth was at least 3 billion years old, and possibly rather more. Unfortunately, he now met yet another formidable impediment to acceptance, the conservativeness of his fellow scientists. Although happy to praise his methodology, many maintained that he had found not the age of the Earth, but merely the age of the materials from which the Earth had been formed. It was just at this time that Harrison Brown of the University of Chicago developed a new method for counting lead isotopes in igneous rocks, which is to say those that were created through heating as opposed to the laying down of sediments. Realizing that the work would be exceedingly tedious, he assigned it to young Claire Patterson as his dissertation project. Famously, he promised Patterson that determining the age of the Earth with his new method would be duck soup. In fact, it would take years. Patterson began work on the project in 1948. Compared with Thomas Midgley's colorful contributions to the March of Progress, Patterson's discovery of the age of the Earth feels more than a touch anticlimactic. For 7 years, first at the University of Chicago and then at the California Institute of Technology, where he moved in 1952, he worked in a sterile lab making very precise measurements of the lead-uranium ratios in carefully selected samples of old rock. The problem with measuring the age of the Earth was that you needed rocks that were extremely ancient, containing lead and uranium-bearing crystals that were about as old as the planet itself. Anything much younger would obviously give you misleadingly youthful dates, but really ancient rocks are only rarely found on Earth. In the late 1940s, no one altogether understood why this should be. Indeed, and rather extraordinarily, we would be well into the space age before anyone could plausibly account for where all the Earth's old rocks went. The answer was plate tectonics, which we shall of course get to. Patterson, meanwhile, was left to try to make sense of things with very limited materials. Eventually, and ingeniously, it occurred to him that he could circumvent the rock shortage by using rocks from beyond Earth. He turned to meteorites. The assumption he made, rather a large one but correct as it turned out, was that many meteorites are essentially leftover building materials from the early days of the solar system, and thus have managed to preserve a more or less pristine interior chemistry. Measure the age of these wandering rocks, and you would have the age also, near enough, of the Earth. As always, however, nothing was quite as straightforward as such a breezy description makes it sound. Meteorites are not abundant, and meteoritic samples not especially easy to get hold of. Moreover, Brown's measurement technique proved finicky in the extreme and needed much refinement. Above all, there was the problem that Patterson's samples were continuously and unaccountably contaminated with large doses of atmospheric lead whenever they were exposed to air. It was this that eventually led him to create a sterile laboratory, the world's first, according to at least one account. It took Patterson 7 years of patient work just to find and measure suitable samples for final testing. In the spring of 1953, he took his specimens to the Argonne National Laboratory in Illinois, where he was granted time on a late-model mass spectrograph, a machine capable of detecting and measuring the minute quantities of uranium and lead locked up in ancient crystals. When at last he had his results, Patterson was so excited that he drove straight to his boyhood home in Iowa and had his mother check him into a hospital because he thought he was having a heart attack. Soon afterwards, at a meeting in Wisconsin, Patterson announced a definitive age for the Earth of 4,550 million years, plus or minus 70 million years, a figure that stands unchanged 50 years later, as McGrain admiringly notes. After 200 years of attempts, the Earth finally had an age. Almost at once, Patterson turned his attention to the question of all that lead in the atmosphere. He was astounded to find that what little was known about the effects of lead on humans was almost invariably wrong or misleading. And not surprisingly, since for 40 years every study of lead's effects had been funded exclusively by manufacturers of lead additives. In one such study, a doctor who had no specialized training in chemical pathology undertook a 5-year program in which volunteers were asked to breathe in or swallow lead in elevated quantities. Then their urine and feces were tested. Unfortunately, as the doctor appears not to have known, lead is not excreted as a waste product. Rather, it accumulates in the bones and blood. That's what makes it so dangerous. And neither blood nor bone was tested. In consequence, lead was given a clean bill of health. Patterson quickly established that we had a lot of lead in the atmosphere, still do, in fact, since lead never goes away, and that about 90% of it appeared to come from car exhaust pipes. But he couldn't prove it. What he needed was a way to compare lead levels in the atmosphere now with the levels that existed before 1923, when tetraethyl lead began to be commercially produced. It occurred to him that ice cores could provide the answer. It was known that snowfall in places like Greenland accumulates into discrete annual layers, because seasonal temperature differences produce slight changes in coloration from winter to summer. By counting back through these layers and measuring the amount of lead in each, he could work out global atmospheric lead concentrations at any time for hundreds or even thousands of years. The notion became the foundation of ice core studies, on which much modern climatological work is based. What Patterson found was that before 1923 there was almost no lead in the atmosphere, and that since that time lead levels had climbed steadily and dangerously. He now made it his life's quest to get lead taken out of petrol. To that end, he became a constant and often vocal critic of the lead industry and its interests. It would prove to be a hellish campaign. Ethel was a powerful global corporation with many friends in high places. Among its directors had been Supreme Court Justice Lewis Powell and Gilbert Grosvenor of the National Geographic Society. Patterson suddenly found research funding withdrawn or difficult to acquire. The American Petroleum Institute canceled a research contract with him, as did the United States Public Health Service, a supposedly neutral government body. As Patterson increasingly became a liability to his institution, the Caltech trustees were repeatedly pressed by lead industry officials to shut him up or let him go. According to Jamie Lincoln Kittman, writing in The Nation in 2000, Ethel executives allegedly offered to endow a chair at Caltech if Patterson was sent packing. Absurdly, he was excluded from a 1971 National Research Council panel appointed to investigate the dangers of atmospheric lead poisoning, even though he was by then unquestionably America's leading expert on atmospheric lead. To his great credit, Patterson never wavered. Eventually, his efforts led to the introduction of the Clean Air Act of 1970. And finally to the removal from sale of all leaded petrol in the United States in 1986. Almost immediately, lead levels in the blood of Americans fell by 80%. But because lead is forever, Americans alive today each have about 625 times more lead in their blood than people did a century ago. The amount of lead in the atmosphere also continues to grow, quite legally, by about 100,000 tons a year, mostly from mining, smelting, and industrial activities. The United States also banned lead in indoor paint, 44 years after most of Europe, as McGrain notes. Remarkably, considering its startling toxicity, lead solder was not removed from American food containers until 1993. As for the Ethel Corporation, it's still going strong, though GM, Standard Oil, and DuPont no longer have stakes in the company. They sold out to a company called Albemarle Paper in 1962. According to McGrain, as late as February 2001, Ethel continued to contend that research has failed to show that leaded gasoline poses a threat to human health or the environment. On its website, a history of the company makes no mention of lead, or indeed of Thomas Midgley, but simply refers to the original product as containing a certain combination of chemicals. Ethel no longer makes leaded petrol, although according to its 2001 company accounts, tetraethyl lead, or TEL as it calls it, still accounted for $25.1 million in sales in 2000 out of overall sales of $795 million. Up from $24.1 million in 1999, but down from $117 million in 1998. The company stated in its report its determination to maximize the cash generated by TEL as its usage continues to phase down around the world. Ethel markets TEL worldwide through an agreement with Associated Octel Limited of England. As for the other scourge left to us by Thomas Midgley, chlorofluorocarbons, they were banned in 1974 in the United States, but they are tenacious little devils, and any that were loosed into the atmosphere before then in deodorants or hairsprays, for instance, will almost certainly be around and devouring ozone long after you and I have shuffled off. Worse, we are still introducing huge amounts of CFCs into the atmosphere every year. According to Wayne Biddle, over 27 million kilograms of the stuff, worth $1.5 billion, still finds its way onto the market every year. So who is making it? We are. That is to say, many large corporations are still making it at their plants overseas. It will not be banned in third world countries until 2010. Claire Patterson died in 1995. He didn't win a Nobel Prize for his work. Geologists never do. Nor, more puzzlingly, did he gain any fame, or even much attention from half a century of consistent and increasingly selfless achievement. A good case could be made that he was the most influential geologist of the 20th century. Yet who has ever heard of Claire Patterson? Most geology textbooks don't mention him. Two recent popular books on the history of the dating of the Earth actually managed to misspell his name. In early 2001, a reviewer of one of these books in the journal Nature made the additional, rather astounding error of thinking Patterson was a woman. At all events, thanks to the work of Claire Patterson, by 1953 the Earth at last had an age everyone could agree on. The only problem now was that it was older than the universe that contained it. Tained it. Tained it. Tained it. Chapter 11. Muster Marks Quarks. In 1911, a British scientist named C.T.R. Wilson was studying cloud formations by tramping regularly to the summit of Ben Nevis, a famously damp Scottish mountain, when it occurred to him that there must be an easier way. Back in the Cavendish lab in Cambridge, he built an artificial cloud chamber, a simple device in which he could cool and moisten the air, creating a reasonable model of a cloud in laboratory conditions. The device worked very well, but had an additional, unexpected benefit. When he accelerated an alpha particle through the chamber to seed his make-believe clouds, it left a visible trail, like the contrails of a passing airliner. He had just invented the particle detector. It provided convincing evidence that subatomic particles did indeed exist. Eventually, two other Cavendish scientists invented a more powerful proton beam device, while in California, Ernest Lawrence at Berkeley produced his famous and impressive cyclotron, or atom smasher, as such devices were long excitingly known. All of these contraptions worked, and indeed still work, on more or less the same principle, the idea being to accelerate a proton or other charged particle to an extremely high speed along a track, sometimes circular, sometimes linear, then bang it into another particle and see what flies off. That's why they were called atom smashers. It wasn't science at its subtlest, but it was generally effective. As physicists built bigger and more ambitious machines, they began to find, or postulate, particles or particle families seemingly without number. Muons, pions, hyperons, mesons, k-mesons, Higgs bosons, intermediate vector bosons, baryons, tachyons. Even physicists began to grow a little uncomfortable. "Young man," Enrico Fermi replied when a student asked him the name of a particular particle, "if I could remember the names of these particles, I would have been a botanist." Today, accelerators have names that sound like something Flash Gordon would use in battle. The superproton synchrotron, the large electron-positron collider, the large hadron collider, the relativistic heavy ion collider. Using huge amounts of energy, some operate only at night so that people in neighboring towns don't have to witness their lights fading when the apparatus is fired up, they can whip particles into such a state of liveliness that a single electron can do 47,000 laps around a 7-kilometer tunnel in under a second. Fears have been raised that in their enthusiasm, scientists might inadvertently create a black hole, or even something called strange quarks, which could theoretically interact with other subatomic particles and propagate uncontrollably. If you are reading this, that hasn't happened. Finding particles takes a certain amount of concentration. They are not just tiny and swift, but often also tantalizingly evanescent. Particles can come into being and be gone again in as little as 10 to the minus 24th seconds. Even the most sluggish of unstable particles hang around for no more than 10 to the minus 7th seconds. Some particles are almost ludicrously slippery. Every second, the Earth is visited by 10,000 trillion tiny, all but massless neutrinos, mostly shot out by the nuclear broilings of the Sun, and virtually all of them pass right through the planet and everything that is on it, including you and me, as if it weren't there. To trap just a few of them, scientists need tanks holding up to 57,000 cubic meters of heavy water, that is, water with a relative abundance of deuterium in it, in underground chambers, old mines usually, where they can't be interfered with by other types of radiation. Very occasionally, a passing neutrino will bang into one of the atomic nuclei in the water and produce a little puff of energy. Scientists count the puffs, and by such means take us very slightly closer to understanding the fundamental properties of the universe. In 1998, Japanese observers reported that neutrinos do have mass, but not a great deal, about 1/10,000,000th that of an electron. What it really takes to find particles these days is money, and lots of it. There is a curious inverse relationship in modern physics between the tininess of the thing being sought and the scale of the facilities required to do the searching. CERN, the European Organization for Nuclear Research, is like a little city. Straddling the border of France and Switzerland, it employs 3,000 people and occupies a site that is measured in square kilometers. CERN boasts a string of magnets that weigh more than the Eiffel Tower, and an underground tunnel some 26 kilometers around. Breaking up atoms, as James Trefil has noted, is easy. You do it each time you switch on a fluorescent light. Breaking up atomic nuclei, however, requires quite a lot of money and a generous supply of electricity. Getting down to the level of quarks, the particles that make up particles, requires still more. Trillions of volts of electricity and the budget of a small Central American state. CERN's new Large Hadron Collider, scheduled to begin operations in 2005, will achieve 14 trillion volts of energy and cost something over $1.5 billion to construct. But these numbers are as nothing compared with what could have been achieved by, and spent upon, the vast and now unfortunately never-to-be superconducting super collider, which began construction near Waxahachie, Texas in the 1980s, before experiencing a super collision of its own with the United States Congress. The intention of the collider was to let scientists probe the ultimate nature of matter, as it is always put, by recreating as nearly as possible the conditions in the universe during its first 10,000 billionths of a second. The plan was to fling particles through a tunnel 84 kilometers long, achieving a truly staggering 99 trillion volts of energy. It was a grand scheme, but would have cost $8 billion to build, a figure that eventually rose to $10 billion, and hundreds of millions of dollars a year to run. In perhaps the finest example in history of pouring money into a hole in the ground, Congress spent $2 billion on the project, then canceled it in 1993 after 22 kilometers of tunnel had been dug. So Texas now boasts the most expensive hole in the universe. The site is, I am told by my friend Jeff Gwynn of the Fort Worth Star-Telegram, essentially a vast cleared field dotted along the circumference by a series of disappointed small towns. Since the Super Collider debacle, particle physicists have set their sights a little lower. But even comparatively modest projects can be quite breathtakingly costly when compared with, well, almost anything. A proposed neutrino observatory at the old Homestake Mine in Lead, South Dakota, would cost $500 million to build, this in a mine that is already dug, before even looking at the annual running costs. There would also be $281 million of general conversion costs. A particle accelerator at Fermilab in Illinois, meanwhile, cost $260 million merely to refit. Particle physics, in short, is a hugely expensive enterprise, but it is a productive one. Today the particle count is well over 150, with a further 100 or so suspected, but unfortunately, in the words of Richard Feynman, it is very difficult to understand the relationships of all these particles and what nature wants them for, or what the connections are from one to another. Inevitably, each time we manage to unlock a box, we find that there is another locked box inside. Some people think there are particles called tachyons, which can travel faster than the speed of light. Others long to find gravitons, the seat of gravity. At what point we reach the irreducible bottom is not easy to say. Carl Sagan in Cosmos raised the possibility that if you traveled downwards into an electron, you might find that it contained a universe of its own. Recalling all those science fiction stories of the 1950s, within it, organized into the local equivalent of galaxies and smaller structures, are an immense number of other, much tinier, elementary particles, which are themselves universes at the next level, and so on forever. An infinite downward regression, universes within universes, endlessly. And upward as well. For most of us, it is a world that surpasses understanding. To read even an elementary guide to particle physics nowadays, you must find your way through lexical thickets such as this. The charged pion and antipion decay respectively into a muon plus antineutrino and an antimuon plus neutrino with an average lifetime of 2.603 times 10 to the minus 8th seconds. The neutral pion decays into 2 photons with an average lifetime of about 0.8 times 10 to the minus 16th seconds, and the muon and antimuon decay respectively into... And so it runs on, and this from a book for the general reader by one of the normally most lucid of interpreters, Steven Weinberg. In the 1960s, in an attempt to bring just a little simplicity to matters, the Caltech physicist Murray Gell-Mann invented a new class of particles, essentially, in the words of Steven Weinberg, to restore some economy to the multitude of hadrons, a collective term used by physicists for protons, neutrons, and other particles governed by the strong nuclear force. Gell-Mann's theory was that all hadrons were made up of still smaller, even more fundamental particles. His colleague Richard Feynman wanted to call these new basic particles partons, as in Dolly, but was overruled. Instead, they became known as quarks. Gell-Mann took the name from a line in Finnegan's Wake, 3 quarks for Muster Mark. Discriminating physicists rhyme the word with storks, not larks, even though the latter is almost certainly the pronunciation Joyce had in mind. The fundamental simplicity of quarks was not long-lived. As they became better understood, it was necessary to introduce subdivisions. Although quarks are much too small to have color or taste or any other physical characteristics we would recognize, they became clumped into 6 categories: up, down, strange, charm, top, and bottom, which physicists oddly refer to as their flavors, and these are further divided into the colors red, green, and blue. One suspects that it was not altogether coincidental that these terms were first applied in California during the age of psychedelia. Eventually, out of all this emerged what is called the Standard Model, which is essentially a sort of parts kit for the subatomic world. The Standard Model consists of 6 quarks, 6 leptons, 5 known bosons, and a postulated 6th, the Higgs boson, named for a Scottish scientist, Peter Higgs, plus 3 of the 4 physical forces, the strong and weak nuclear forces, and electromagnetism. The arrangement essentially is that among the basic building blocks of matter are quarks. These are held together by particles called gluons, and together quarks and gluons form protons and neutrons, the stuff of the atom's nucleus. Leptons are the source of electrons and neutrinos. Quarks and leptons together are called fermions. Bosons, named for the Indian physicist S.N. Bose, are particles that produce and carry forces, and include photons and gluons. The Higgs boson may or may not actually exist. It was invented simply as a way of endowing particles with mass. It is all, as you can see, just a little unwieldy, but it is the simplest model that can explain all that happens in the world of particles. Most particle physicists feel, as Leon Lederman remarked in a 1985 television documentary, that the Standard Model lacks elegance and simplicity. "It is too complicated. It has too many arbitrary parameters," Lederman said. "We don't really see the Creator twiddling 20 knobs to set 20 parameters to create the universe as we know it." Physics is really nothing more than a search for ultimate simplicity. But so far, all we have is a kind of elegant messiness, or as Lederman put it, There is a deep feeling that the picture is not beautiful. The Standard Model is not only ungainly, but incomplete. For one thing, it has nothing at all to say about gravity. Search through the Standard Model as you will, and you won't find anything to explain why, when you place a hat on a table, it doesn't float up to the ceiling. Nor, as we've just noted, can it explain mass. In order to give particles any mass at all, we have to introduce the notional Higgs boson. Whether it actually exists is a matter for 21st century physics. As Feynman cheerfully observed, "So we are stuck with a theory, and we do not know whether it is right or wrong. But we do know that it is a little wrong, or at least incomplete." In an attempt to draw everything together, physicists have come up with something called superstring theory. This postulates that all those little things like quarks and leptons that we had previously thought of as particles are actually strings, vibrating strands of energy that oscillate in 11 dimensions, consisting of the 3 we know already, plus time, and 7 other dimensions that are, well, unknowable to us. The strings are very tiny, tiny enough to pass for point particles. By introducing extra dimensions, superstring theory enables physicists to pull together quantum laws and gravitational ones into one comparatively tidy package. But it also means that anything scientists say about the theory begins to sound worryingly like the sort of thoughts that would make you edge away if conveyed to you by a stranger on a park bench. Here, for example, is the physicist Michio Kaku explaining the structure of the universe from a superstring perspective. The heterotic string consists of a closed string that has 2 types of vibrations, clockwise and counterclockwise, which are treated differently. The clockwise vibrations live in a 10-dimensional space. The counterclockwise live in a 26-dimensional space, of which 16 dimensions have been compactified. We recall that in Kaluza's original 5-dimensional, the 5th dimension was compactified by being wrapped up into a circle. And so it goes, for some 350 pages. String theory has further spawned something called M-theory, which incorporates surfaces known as membranes, or simply brains, to the hipper souls of the world of physics. This, I'm afraid, is the stop on the knowledge highway where most of us must get off. Here is a sentence from the New York Times explaining this as simply as possible to a general audience. The ekpyrotic process begins far in the indefinite past with a pair of flat, empty brains sitting parallel to each other in a warped 5-dimensional space. The 2 brains, which form the walls of the 5th dimension, could have popped out of nothingness as a quantum fluctuation in the even more distant past, and then drifted apart. No arguing with that. No understanding it either. Ekpyrotic, incidentally, comes from the Greek word for conflagration. Matters in physics have now reached such a pitch that, as Paul Davies noted in Nature, it is almost impossible for the non-scientist to discriminate between the legitimately weird and the outright crackpot. The question came interestingly to a head in the autumn of 2002, when 2 French physicists, twin brothers Igor and Grichka Bogdanov, produced a theory of ambitious density involving such concepts as imaginary time and the Kubo-Schwinger-Martin condition, and purporting to describe the nothingness that was the universe before the Big Bang, a period that was always assumed to be unknowable, since it predated the birth of physics and its properties. Almost at once, the Bogdanov theory excited debate among physicists as to whether it was twaddle, a work of genius, or a hoax. Scientifically, it's clearly more or less complete nonsense, Columbia University physicist Peter Woit told the New York Times. But these days, that doesn't much distinguish it from a lot of the rest of the literature. Karl Popper, whom Steven Weinberg has called the dean of modern philosophers of science, once suggested that there may not in fact be an ultimate theory for physics, that rather every explanation may require a further explanation, producing an infinite chain of more and more fundamental principles. A rival possibility is that such knowledge may simply be beyond us. So far, fortunately, writes Weinberg in Dreams of a Final Theory, we do not seem to be coming to the end of our intellectual resources. Almost certainly this is an area that will see further developments of thought. And almost certainly again, these thoughts will be beyond most of us. While physicists in the middle decades of the 20th century were looking perplexedly into the world of the very small, astronomers were finding no less arresting an incompleteness of understanding in the universe at large. When we last met Edwin Hubble, he had determined that nearly all the galaxies in our field of view are flying away from us, and that the speed and distance of this retreat are neatly proportional. The further away the galaxy, the faster it is moving. Hubble realized that this could be expressed with a simple equation. HO equals V over D, where HO is the constant, V is the recessional velocity of a flying galaxy, and D its distance away from us. HO has been known ever since as the Hubble constant, and the whole as Hubble's law. Using his formula, Hubble calculated that the universe was about 2 billion years old, which was a little awkward, because even by the late 1920s, it was increasingly evident that many things within the universe, including probably the Earth itself, were older than that. Refining this figure has been an ongoing preoccupation of cosmology. Almost the only thing constant about the Hubble constant has been the amount of disagreement over what value to give it. In 1956, astronomers discovered that Cepheid variables were more variable than they had thought. They came in 2 varieties, not 1. This allowed them to rework their calculations and come up with a new age for the universe of between 7 billion and 20 billion years. Not terribly precise, but at least old enough at last to embrace the formation of the Earth. In the years that followed, there erupted a dispute that would run and run between Alan Sandage, heir to Hubble at Mount Wilson, and Gérard de Vaucouleurs, a French-born astronomer based at the University of Texas. Sandage, after years of careful calculations, arrived at a value for the Hubble constant of 50, giving the universe an age of 20 billion years. De Vaucouleurs was equally certain that the Hubble constant was 100. This would mean that the universe was only half the size and age that Sandage believed, 10 billion years. Matters took a further lurch into uncertainty when, in 1994, a team from the Carnegie Observatories in California, using measures from the Hubble Space Telescope, suggested that the universe could be as little as 8 billion years old, an age even they conceded was younger than some of the stars within the universe. In February 2003, a team from NASA and the Goddard Space Flight Center in Maryland, using a new far-reaching type of satellite called the Wilkinson Microwave Anisotropy Probe, announced with some confidence that the age of the universe is 13.7 billion years, give or take 100 million years or so. There matters rest, at least for the moment. The difficulty in making final determinations is that there are often acres of room for interpretation. Imagine standing in a field at night and trying to decide how far away 2 distant electric lights are. Using fairly straightforward tools of astronomy, you can easily enough determine that the bulbs are of equal brightness, and that one is, say, 50% more distant than the other. But what you can't be certain of is whether the nearer light is, let us say, a 58-watt bulb that is 37 meters away, or a 61-watt light that is 36.5 meters away. On top of that, you must make allowances for distortions caused by variations in the Earth's atmosphere, by intergalactic dust, by contaminating light from foreground stars, and many other factors. The upshot is that your computations are necessarily based on a series of nested assumptions, any of which could be a source of contention. There is also the problem that access to telescopes is always at a premium, and historically measuring red shifts has been notably costly in telescope time. It could take all night to get a single exposure. In consequence, astronomers have sometimes been compelled, or willing, to base conclusions on notably scanty evidence. In cosmology, as the journalist Jeffrey Carr has suggested, we have a mountain of theory built on a molehill of evidence. Or, as Martin Rees has put it, our present satisfaction with our state of understanding may reflect the paucity of the data rather than the excellence of the theory. This uncertainty applies, incidentally, to relatively nearby things as much as to the distant edges of the universe. As Donald Goldsmith notes, when astronomers say that the galaxy M87 is 60 million light-years away, what they really mean, but do not often stress to the general public, is that it is somewhere between 40 million and 90 million light-years away, not quite the same thing. For the universe at large, matters are naturally magnified. For all the éclat surrounding the latest pronouncements, we remain a long way from unanimity. One interesting theory recently suggested is that the universe is not nearly as big as we thought, that when we peer into the distance, some of the galaxies we see may simply be reflections, ghost images created by rebounded light. The fact is, there is a great deal, even at quite a fundamental level, that we don't know, not least what the universe is made of. When scientists calculate the amount of matter needed to hold things together, they always come up desperately short. It appears that at least 90% of the universe, and perhaps as much as 99%, is composed of Fritz Zwicky's dark matter, stuff that is by its nature invisible to us. It is slightly galling to think that we live in a universe that for the most part we can't even see. But there you are. At least the names for the two main possible culprits are entertaining. They are said to be either WIMPs, or weakly interacting massive particles, which is to say specks of invisible matter left over from the Big Bang, or MACHOs, for massive compact halo objects, really just another name for black holes, brown dwarfs, and other very dim stars. Particle physicists have tended to favor the particle explanation of WIMPs. Astrophysicists, the stellar explanation of MACHOs. For a time, MACHOs had the upper hand, but not nearly enough of them were detected, so sentiment swung back towards WIMPs, with the problem that no WIMP has ever been found. Because they are weakly interacting, they are, assuming they even exist, very hard to identify. Cosmic rays would cause too much interference, so scientists must go deep underground. 1 kilometer underground, cosmic bombardments would be 1/1,000,000th what they would be on the surface. But even when all these are added in, 2/3 of the universe is still missing from the balance sheet, as one commentator has put it. For the moment, we might very well call them dunnos, for dark, unknown, non-reflective, non-detectable objects somewhere. Recent evidence suggests not only that the galaxies of the universe are racing away from us, but that they are doing so at a rate that is accelerating. This is counter to all expectations. It appears that the universe may be filled not only with dark matter, but with dark energy. Scientists sometimes also call it vacuum energy or quintessence. Whatever it is, it seems to be driving an expansion that no one can altogether account for. The theory is that empty space isn't so empty at all, that there are particles of matter and antimatter popping into existence and popping out again, and that these are pushing the universe outwards at an accelerating rate. Improbably enough, the one thing that resolves all this is Einstein's cosmological constant, the little piece of maths he dropped into the general theory of relativity to stop the universe's presumed expansion, and that he called the biggest blunder of my life. It now appears that he may have got things right after all. The upshot of all this is that we live in a universe whose age we can't quite compute, surrounded by stars whose distances from us and each other we don't altogether know, filled with matter we can't identify, operating in conformance with physical laws whose properties we don't truly understand. And on that rather unsettling note, let's return to planet Earth and consider something that we do understand, though by now you perhaps won't be surprised to hear that we don't understand it completely, and what we do understand, we haven't understood for long. Chapter 12. The Earth Moves. In one of his last professional acts before his death in 1955, Albert Einstein wrote a short but glowing foreword to a book by a geologist named Charles Hapgood, entitled Earth's Shifting Crust, a Key to Some Basic Problems of Earth Science. Hapgood's book was a steady demolition of the idea that continents were in motion. In a tone that all but invited the reader to join him in a tolerant chuckle, Hapgood observed that a few gullible souls had noticed an apparent correspondence in shape between certain continents. It would appear, he went on, that South America might be fitted together with Africa, and so on. It is even claimed that rock formations on opposite sides of the Atlantic match. Mr. Hapgood briskly dismissed any such notions, noting that the geologists K.E. Castor and J.C. Mendes had done extensive field work on both sides of the Atlantic and had established beyond question that no such similarities existed. Goodness knows what outcrops Messrs. Castor and Mendes had looked at, because in fact many of the rock formations on both sides of the Atlantic are the same. Not just very similar, but the same. This was not an idea that flew with Mr. Hapgood, or many other geologists of his day. The theory Hapgood alluded to was one first propounded in 1908 by an amateur American geologist named Frank Bursley Taylor. Taylor came from a wealthy family and had both the means and the freedom from academic constraints to pursue unconventional lines of inquiry. He was one of those struck by the similarity in shape between the facing coastlines of Africa and South America, and from this observation he developed the idea that the continents had once slid around. He suggested, presciently as it turned out, that the crunching together of continents could have thrust up the world's mountain chains. He failed, however, to produce much in the way of evidence, and the theory was considered too crackpot to merit serious attention. In Germany, however, Taylor's idea was picked up and effectively appropriated by a theorist named Alfred Wegener, a meteorologist at the University of Marburg. Wegener investigated the many plant and fossil anomalies that did not fit comfortably into the standard model of Earth history, and realized that very little of it made sense if conventionally interpreted. Animal fossils repeatedly turned up on opposite sides of oceans that were clearly too wide to swim. How, he wondered, did marsupials travel from South America to Australia? How did identical snails turn up in Scandinavia and New England? And how come to that did one account for coal seams and other semi-tropical remnants in frigid spots like Spitsbergen, over 600 kilometers north of Norway, if they had not somehow migrated there from warmer climes? Wegener developed the theory that the world's continents had once existed as a single landmass he called Pangaea, where flora and fauna had been able to mingle before splitting apart and floating off to their present positions. He set the idea out in a book called Die Entstehung der Kontinente und Ozeane, or The Origin of Continents and Oceans, which was published in German in 1912, and, despite the outbreak of the First World War in the meantime, in English 3 years later. Because of the war, Wegener's theory didn't attract much notice at first. But by 1920, when he produced a revised and expanded edition, it quickly became a subject of discussion. Everyone agreed that continents moved, but up and down, not sideways. The process of vertical movement, known as isostasy, was a foundation of geological belief for generations, though no one had any really good theories as to how or why it happened. One idea which remained in textbooks well into my own school days was the baked apple theory, propounded by the Austrian Eduard Suess just before the turn of the century. This suggested that as the molten earth had cooled, it had become wrinkled in the manner of a baked apple, creating ocean basins and mountain ranges. Never mind that James Hutton had shown long before that any such static arrangement would eventually result in a featureless spheroid as erosion leveled the bumps and filled in the divots. There was also the problem, demonstrated by Rutherford and Soddy early in the century, that earthly elements hold huge reserves of heat. much too much to allow for the sort of cooling and shrinking Seuss suggested. And anyway, if Seuss's theory were correct, then mountains should be evenly distributed across the face of the earth, which patently they were not, and of more or less the same ages. Yet by the early 1900s, it was already evident that some ranges, like the Urals and Appalachians, were hundreds of millions of years older than others, like the Alps and Rockies. Clearly the time was ripe for a new theory. Unfortunately, Alfred Wegener was not the man geologists wished to provide it. For a start, his radical notions questioned the foundations of their discipline, seldom an effective way to generate warmth in an audience. Such a challenge would have been painful enough coming from a geologist, but Wegener had no background in geology. He was a meteorologist, for goodness sake, a weatherman, a German weatherman. These were not remediable deficiencies. And so geologists took every pain they could to dismiss his evidence and belittle his suggestions. To get around the problems of fossil distributions, they posited ancient land bridges wherever they were needed. When an ancient horse named Hipparion was found to have lived in France and Florida at the same time, a land bridge was drawn across the Atlantic. When it was realized that ancient tapirs had existed simultaneously in South America and Southeast Asia, a land bridge was drawn there, too. Soon maps of prehistoric seas were almost solid with hypothesized land bridges. From North America to Europe, from Brazil to Africa, from Southeast Asia to Australia, from Australia to Antarctica. These connective tendrils had not only conveniently appeared whenever it was necessary to move a living organism from one landmass to another, but then had obligingly vanished without leaving a trace of their former existence. None of this, of course, was supported by so much as a grain of evidence. Nothing so wrong could be, yet it was geological orthodoxy for the next half-century. Even land bridges couldn't explain some things. One species of trilobite that was well known in Europe was also found to have lived on Newfoundland, but only on one side. No one could persuasively explain how it had managed to cross 3,000 kilometers of hostile ocean, but then failed to find its way around the corner of an island 300 kilometers wide. Even more awkwardly anomalous was another species of trilobite found in Europe and the Pacific Northwest of America, but nowhere in between, which would have required not so much a land bridge as a flyover. Yet as late as 1964, when the Encyclopaedia Britannica discussed the rival theories, it was Wegener's that was held to be full of numerous grave theoretical difficulties. To be sure, Wegener made mistakes. He asserted that Greenland is drifting west by about 1.6 kilometers a year, a clear nonsense. It's more like a centimeter. Above all, he could offer no convincing explanation for how the land masses moved about. To believe in his theory, you had to accept that massive continents somehow pushed through solid crust like a farm plow through soil without leaving any furrow in their wake. Nothing then known could plausibly explain what motored these massive movements. It was Arthur Holmes, the English geologist who did so much to determine the age of the Earth, who came up with a suggestion. Holmes was the first scientist to understand that radioactive warming could produce convection currents within the Earth. In theory, these could be powerful enough to slide continents around on the surface. In his popular and influential textbook, Principles of Physical Geology, first published in 1944, Holmes laid out a continental drift theory that was, in its fundamentals, the theory that prevails today. It was still a radical proposition for the time, and widely criticized, particularly in the United States, where resistance to drift lasted longer than elsewhere. One reviewer there fretted without any sense of irony that Holmes presented his arguments so clearly and compellingly that students might actually come to believe them. Elsewhere, however, the new theory drew steady, if cautious, support. In 1950, a vote at the annual meeting of the British Association for the Advancement of Science showed that about half of those present now embraced the idea of continental drift. Hapgood soon after cited this figure as proof of how tragically misled British geologists had become. Curiously, Holmes himself sometimes wavered in his conviction. In 1953 he confessed, "I have never succeeded in freeing myself from a nagging prejudice against continental drift. In my geological bones, so to speak, I feel the hypothesis is a fantastic one." Continental drift was not entirely without support in the United States. Reginald Daly of Harvard spoke for it, but he, you may recall, was the man who suggested that the moon had been formed by a cosmic impact, and his ideas tended to be considered interesting, even worthy, but a touch too exuberant for serious consideration, and so most American academics stuck to the belief that the continents had occupied their present positions forever, and that their surface features could be attributed to something other than lateral motions. Interestingly, oil company geologists had known for years that if you wanted to find oil, you had to allow for precisely the sort of surface movements that were implied by plate tectonics. But oil geologists didn't write academic papers. They just found oil. There was one other major problem with Earth theories that no one had resolved, or even come close to resolving. That was the question of where all the sediments went. Every year, the Earth's rivers carried massive volumes of eroded material, 500 million tons of calcium, for instance, to the seas. If you multiplied the rate of deposition by the number of years it had been going on, you arrived at a disturbing figure. There should be about 20 kilometers of sediments on the ocean bottoms, or, put another way, the ocean bottoms should by now be well above the ocean tops. Scientists dealt with this paradox in the handiest possible way. They ignored it. But eventually there came a point when they could ignore it no longer. In the Second World War, a Princeton University mineralogist named Harry Hess was put in charge of an attack transport ship, the USS Cape Johnson. Aboard this vessel was a fancy new depth sounder called a fathometer, which was designed to facilitate inshore maneuvers during beach landings. But Hess realized that it could equally well be used for scientific purposes, and never switched it off, even when far out at sea, even in the heat of battle. What he found was entirely unexpected. If the ocean floors were ancient, as everyone assumed, they should be thickly blanketed with sediments, like the mud on the bottom of a river or lake. But Hess's readings showed that the ocean floor offered anything but the gooey smoothness of ancient silts. It was scored everywhere with canyons, trenches, and crevasses, and dotted with volcanic seamounts that he called guyots, after an earlier Princeton geologist named Arnold Guyot. All this was a puzzle, but Hess had a war to take part in and put such thoughts to the back of his mind. After the war, Hess returned to Princeton and the preoccupations of teaching, but the mysteries of the seafloor continued to occupy a space in his thoughts. Meanwhile, throughout the 1950s, oceanographers were undertaking more and more sophisticated surveys of the ocean floors. In so doing, they found an even bigger surprise. The mightiest and most extensive mountain range on Earth was mostly underwater. It traced a continuous path along the world's seabeds, rather like the pattern on a tennis ball. If you began at Iceland and traveled south, you could follow it down the center of the Atlantic Ocean, around the bottom of Africa, and across the Indian and Southern Oceans and into the Pacific just below Australia. There it angled across the Pacific as if making for Baja California, before shooting up the west coast of the United States to Alaska. Occasionally its higher peaks poked above the water, as an island or archipelago. The Azores and Canaries in the Atlantic, Hawaii in the Pacific, for instance. But mostly it was buried under thousands of fathoms of salty sea, unknown and unsuspected. When all its branches were added together, the network extended to 75,000 kilometers. A very little of this had been known for some time. People laying ocean floor cables in the 19th century had realized that there was some kind of mountainous intrusion in the mid-Atlantic from the way the cables ran. But the continuous nature and overall scale of the chain was a stunning surprise. Moreover, it contained physical anomalies that couldn't be explained. Down the middle of the mid-Atlantic ridge was a canyon, a rift, up to 20 kilometers wide for its entire 19,000-kilometer length. This seemed to suggest that the Earth was splitting apart at the seams, like a nut bursting out of its shell. It was an absurd and unnerving notion, but the evidence couldn't be denied. Then in 1960, core samples showed that the ocean floor was quite young at the mid-Atlantic ridge, but grew progressively older as you moved away from it to east or west. Harry Hess considered the matter and realized that this could mean only one thing. New ocean crust was being formed on either side of the central rift, then being pushed away from it as more new crust came along behind. The Atlantic floor was effectively two large conveyor belts, one carrying crust towards North America, the other carrying crust towards Europe. The process became known as seafloor spreading. When the crust reached the end of its journey at the boundary with the continents, it plunged back into the earth in a process known as subduction. That explained where all the sediment went. It was being returned to the bowels of the earth. It also explained why ocean floors everywhere were so comparatively youthful. None had ever been found to be older than about 175 million years, which was a puzzle, because continental rocks were often billions of years old. Now Hess could see why. Ocean rocks lasted only as long as it took them to travel to shore. It was a beautiful theory that explained a great deal. Hess elaborated his arguments in an important paper which was almost universally ignored. Sometimes the world just isn't ready for a good idea. Meanwhile, two researchers working independently were making some startling findings by drawing on a curious fact of Earth history that had been discovered several decades earlier. In 1906, a French physicist named Bernard Brun had found that the planet's magnetic field reverses itself from time to time, and that the record of these reversals is permanently fixed in certain rocks at the time of their birth. Specifically, tiny grains of iron ore within the rocks point to wherever the magnetic poles happen to be at the time of their formation, then stay pointing in that direction as the rocks cool and harden. In effect, they remember where the magnetic poles were at the time of their creation. For years, this was little more than a curiosity, but in the 1950s, Patrick Blackett of the University of London and S.K. Runcorn of the University of Newcastle studied the ancient magnetic patterns frozen in British rocks, and were startled, to say the very least, to find them indicating that at some time in the distant past, Britain had spun on its axis and travelled some distance to the north, as if it had somehow come loose from its moorings. Moreover, they also discovered that if you placed a map of Europe's magnetic patterns alongside an American one from the same period, they fit together, as neatly as two halves of a torn letter. It was uncanny. Their findings were ignored too. It finally fell to two men from Cambridge University, a geophysicist named Drummond Matthews, and a graduate student of his named Fred Vine, to draw all the strands together. In 1963, using magnetic studies of the Atlantic Ocean floor, they demonstrated conclusively that the sea floors were spreading in precisely the manner Hess had suggested, and that the continents were in motion too. An unlucky Canadian geologist named Lawrence Morley came up with the same conclusion at the same time, but couldn't find anyone to publish his paper. In what has become a famous snub, the editor of the Journal of Geophysical Research told him, "Such speculations make interesting talk at cocktail parties, but it is not the sort of thing that ought to be published under serious scientific aegis." One geologist later described it as probably the most significant paper in the earth sciences ever to be denied publication. At all events, mobile crust was an idea whose time had finally come. A symposium of many of the most important figures in the field was convened in London under the auspices of the Royal Society in 1964, and suddenly it seemed everyone was a convert. The Earth, the meeting agreed, was a mosaic of interconnected segments whose various stately jostlings accounted for much of the planet's surface behavior. The name continental drift was fairly swiftly discarded when it was realized that the whole crust was in motion and not just the continents, but it took a while to settle on a name for the individual segments. At first, people called them crustal blocks or sometimes paving stones. Not until late 1968, with the publication of an article by 3 American seismologists in the Journal of Geophysical Research, did the segments receive the name by which they have since been known: plates. The same article called the new science plate tectonics. Old ideas die hard, and not everyone rushed to embrace the exciting new theory. Well into the 1970s, one of the most popular and influential geological textbooks, The Earth by the Venerable Harold Jeffreys, strenuously insisted that plate tectonics was a physical impossibility, just as it had in the first edition way back in 1924. It was equally dismissive of convection and sea-floor spreading, and in Basin and Range, published in 1980, John McPhee noted that even then 1 American geologist in 8 still didn't believe in plate tectonics. Today we know that the Earth's surface is made up of 8 to 12 big plates, depending on how you define big, and 20 or so smaller ones, and that they all move in different directions and at different speeds. Some plates are large and comparatively inactive, others small but energetic. They bear only an incidental relationship to the land masses that sit upon them. The North American plate, for instance, is much larger than the continent with which it is associated. It roughly traces the outline of the continent's western coast, which is why that area is so seismically active, because of the bump and crush of the plate boundary, but ignores the eastern seaboard altogether, and instead extends halfway across the Atlantic to the mid-ocean ridge. Iceland is split down the middle, which makes it tectonically half American and half European. New Zealand, meanwhile, is part of the immense Indian Ocean plate, even though it is nowhere near the Indian Ocean, and so it goes for most plates. The connections between modern land masses and those of the past were found to be infinitely more complex than anyone had imagined. Kazakhstan, it turns out, was once attached to Norway and New England. One corner of Staten Island, but only a corner, is European. So is part of Newfoundland. Pick up a pebble from a Massachusetts beach, and its nearest kin will now be in Africa. The Scottish Highlands and much of Scandinavia are substantially American. Some of the Shackleton Range of Antarctica, it is thought, may once have belonged to the Appalachians of the eastern U.S. Rocks, in short, get around. The constant turmoil keeps the plates from fusing into a single immobile plate. Assuming things continue much as at present, the Atlantic Ocean will expand until eventually it is much bigger than the Pacific. Much of California will float off and become a kind of Madagascar of the Pacific. Africa will push northward into Europe, squeezing the Mediterranean out of existence and thrusting up a chain of mountains of Himalayan majesty running from Paris to Calcutta. Australia will colonize the islands to its north and connect by some isthmian umbilicus to Asia. These are future outcomes, but not future events. The events are happening now. As we sit here, continents are adrift like leaves on a pond. Thanks to global positioning systems, we can see that Europe and North America are parting at about the speed a fingernail grows, roughly 2 meters in a human lifetime. If you were prepared to wait long enough, you could ride from Los Angeles all the way up to San Francisco. It is only the brevity of lifetimes that keeps us from appreciating the changes. Look at a globe, and what you are seeing really is a snapshot of the continents as they have been for just 0.1% of the Earth's history. Earth is alone among the rocky planets in having tectonics, and why this should be is a bit of a mystery. It is not simply a matter of size or density. Venus is nearly a twin of Earth in these respects, and yet has no tectonic activity. But it may be that we have just the right materials and just the right measures to keep the Earth bubbling away. It is thought though it is really nothing more than a thought, that tectonics is an important part of the planet's organic well-being. As the physicist and writer James Trefil has put it, it would be hard to believe that the continuous movement of tectonic plates has no effect on the development of life on Earth. He suggests that the challenges induced by tectonics, changes in climate for instance, were an important spur to the development of intelligence. Others believe the drifting of the continents may have produced at least some of the Earth's various extinction events. In November 2002, Tony Dixon of Cambridge University produced a report published in the journal Science, strongly suggesting that there may well be a relationship between the history of rocks and the history of life. What Dixon established was that the chemical composition of the world's oceans has altered abruptly and dramatically at times throughout the past half-billion years, and that these changes often correlate with important events in biological history, the huge outburst of tiny organisms that created the chalk cliffs of England's south coast, the sudden fashion for shells among marine organisms during the Cambrian period, and so on. No one can say what causes the ocean's chemistry to change so dramatically from time to time, but the opening and shutting of ocean ridges would be an obvious possible culprit. At all events, plate tectonics explain not only the surface dynamics of the Earth, how an ancient Hipparion got from France to Florida, for example, but also many of its internal actions. Earthquakes, the formation of island chains, the carbon cycle, the locations of mountains, the coming of ice ages, the origins of life itself. There was hardly a matter that wasn't directly influenced by this remarkable new theory. Geologists, as McPhee has noted, found themselves in the giddying position where the whole Earth suddenly made sense. But only up to a point. The distribution of continents in former times is much less neatly resolved than most people outside geophysics think. Although textbooks give confident-looking representations of ancient land masses with names like Laurasia, Gondwana, Rodinia, and Pangaea, these are sometimes based on conclusions that don't altogether hold up. As George Gaylord Simpson observes in Fossils and the History of Life, species of plants and animals from the ancient world have a habit of appearing inconveniently where they shouldn't, and failing to be where they ought. The outline of Gondwana, a once mighty continent connecting Australia, Africa, Antarctica, and South America, was based in large part on the distributions of a genus of ancient tongue fern called Glossopteris, which was found in all the right places. However, much later, Glossopteris was also discovered in parts of the world that had no known connection to Gondwana. This troubling discrepancy was, and continues to be, mostly ignored. Similarly, a Triassic reptile called Lystrosaurus has been found from Antarctica all the way to Asia, supporting the idea of a former connection between those continents, but it has never turned up in South America or Australia, which are believed to have been part of the same continent at the same time. There are also many surface features that tectonics can't explain. Take Denver. It is, as everyone knows, a mile high, but that rise is comparatively recent. When dinosaurs roamed the Earth, Denver was part of an ocean bottom, many thousands of meters lower. Yet the rocks on which Denver sits are not fractured or deformed in the way they would be if Denver had been pushed up by colliding plates, and anyway, Denver was too far from the plate edges to be susceptible to their actions. It would be as if you pushed against the edge of a rug, hoping to raise a rock at the opposite end. Mysteriously, and over millions of years, it appears that Denver has been rising like baking bread. So, too, has much of southern Africa. A portion of it, 1,600 kilometers across, has risen about 1.5 kilometers in 100 million years without any known associated tectonic activity. Australia, meanwhile, has been tilting and sinking. Over the past 100 million years, as it has drifted north towards Asia, its leading edge has sunk by nearly 200 meters. It appears that Indonesia is very slowly drowning and dragging Australia down with it. Nothing in the theory of tectonics can explain any of this. Alfred Wegener never lived to see his ideas vindicated. On an expedition to Greenland in 1930, he set out alone on his 50th birthday to check out a supply drop. He never returned. He was found a few days later frozen to death on the ice. He was buried on the spot and lies there yet, but about a meter closer to North America than on the day he died. Einstein also failed to live long enough to see that he had backed the wrong horse. In fact, he died at Princeton, New Jersey in 1955, before Charles Hapgood's rubbishing of continental drift theories was even published. The other principal player in the emergence of tectonics theory, Harry Hess, was also at Princeton at the time, and would spend the rest of his career there. One of his students was a bright young fellow named Walter Alvarez, who would eventually change the world of science in quite a different way. As for geology itself, its cataclysms had only just begun, and it was young Alvarez who helped to start the process. Part 4. Dangerous Planet. The history of any one part of the Earth, like the life of a soldier, consists of long periods of boredom and short periods of terror. British geologist Derek V. Ager. Chapter 13. Bang! People knew for a long time that there was something odd about the Earth beneath Manson, Iowa. In 1912, a man drilling a well for the town water supply reported bringing up a lot of strangely deformed rock, crystalline clast breccia with a melt matrix, and overturned ejecta flap, as it was later described in an official report. The water was odd, too. It was almost as soft as rainwater. Naturally occurring soft water had never been found in Iowa before. Though Manson's strange rocks and silken waters were matters of curiosity, 41 years would pass before a team from the University of Iowa got around to making a trip to the community, then, as now, a town of about 2,000 people in the northwest part of the state. In 1953, after sinking a series of experimental bores, university geologists agreed that the site was indeed anomalous, and attributed the deformed rocks to some ancient, unspecified volcanic action. This was in keeping with the wisdom of the day, but it was also about as wrong as a geological conclusion can get. The trauma to Manson's geology had come not from within the Earth, but from at least 100 million miles beyond. Sometime in the very ancient past, when Manson stood on the edge of a shallow sea, a rock about 1.5 miles across, weighing 10 billion tons and traveling at perhaps 200 times the speed of sound, ripped through the atmosphere and punched into the earth with a violence and suddenness that we can scarcely imagine. Where Manson now stands became an instant hole, 3 miles deep and more than 20 miles across. The limestone that elsewhere gives Iowa its hard mineralized water was obliterated and replaced by the shocked basement rocks that so puzzled the water driller in 1912. The Manson impact was the biggest thing that has ever occurred on the mainland United States, of any type, ever. The crater it left behind was so colossal that if you stood on one edge you would only just be able to see the other side on a good day. It would make the Grand Canyon look quaint and trifling. Unfortunately for lovers of spectacle, 2.5 million years of passing ice sheets filled the Manson crater right to the top with rich glacial till, then graded it smooth so that today the landscape at Manson and for miles around is as flat as a tabletop, which is of course why no one has ever heard of the Manson crater. At the library in Manson, they are delighted to show you a collection of newspaper articles and a box of core samples from a 1991 to 92 drilling program. Indeed, they positively bustle to produce them, but you have to ask to see them. Nothing permanent is on display, and nowhere in the town is there any historical marker. To most people in Manson, the biggest thing ever to happen was a tornado that rolled up Main Street in 1979, tearing apart the business district. One of the advantages of all that surrounding flatness is that you can see danger from a long way off. Virtually the whole town turned out at one end of Main Street and watched for half an hour as the tornado came towards them, hoping it would veer off, then prudently scampered when it did not. 4 of them, alas, didn't move quite fast enough and were killed. Every June now, Manson has a week-long event called Crater Days, which was dreamed up as a way of helping people forget that unhappy anniversary. It doesn't really have anything to do with the crater. Nobody's figured out a way to capitalize on an impact site that isn't visible.
Very occasionally we get people coming in and asking where they should go to see the crater, and we have to tell them that there is nothing to see, says Anna Schlapko, the town's friendly librarian. Then they go away kind of disappointed. However, most people, including most Iowans, have never heard of the Manson crater. Even for geologists, it barely rates a footnote. But for one brief period in the 1980s, Manson was the most geologically exciting place on Earth. The story begins in the early 1950s, when a bright young geologist named Eugene Shoemaker paid a visit to Meteor Crater in Arizona. Today, Meteor Crater is the most famous impact site on Earth and a popular tourist attraction. In those days, however, it didn't receive many visitors and was still often referred to as Barringer Crater, after a wealthy mining engineer named Daniel M. Barringer, who had staked a claim on it in 1903. Barringer believed that the crater had been formed by a 10-million-ton meteor, heavily freighted with iron and nickel, and it was his confident expectation that he would make a fortune digging it out. Unaware that the meteor and everything in it would have been vaporized on impact, he wasted a fortune and the next 26 years cutting tunnels that yielded nothing. By the standards of today, crater research in the early 1900s was a trifle unsophisticated, to say the least. The leading early investigator, G.K. Gilbert of Columbia University, modeled the effects of impacts by flinging marbles into pans of oatmeal. For reasons I cannot supply, Gilbert conducted these experiments not in a laboratory at Columbia, but in a hotel room. Somehow from this, Gilbert concluded that the moon's craters were indeed formed by impacts, in itself quite a radical notion for the time, but that the Earth's were not. Most scientists refused to go even that far. To them, the moon's craters were evidence of ancient volcanoes and nothing more. The few craters that remained evident on the Earth, most had been eroded away, were generally attributed to other causes, or treated as fluky rarities. By the time Shoemaker came along, a common view was that Meteor Crater had been formed by an underground steam explosion. Shoemaker knew nothing about underground steam explosions. He couldn't, they don't exist. But he did know all about blast zones. One of his first jobs out of college had been to study explosion rings at the Yucca Flats nuclear test site in Nevada. He concluded, as Barringer had before him, that there was nothing at Meteor Crater to suggest volcanic activity, but that there were huge distributions of other stuff, anomalous fine silicas and magnetites principally, that suggested an impact from space. Intrigued, he began to study the subject in his spare time. Working first with his colleague Eleanor Helen, and later with his wife Carolyn, and associate David Levy, Shoemaker made a systematic survey of the inner solar system. They spent 1 week each month at the Palomar Observatory in California, looking for objects, asteroids primarily, whose trajectories carried them across the Earth's orbit. At the time we started, only slightly more than a dozen of these things had ever been discovered in the entire course of astronomical observation, Shoemaker recalled some years later in a television interview. Astronomers in the 20th century essentially abandoned the solar system, he added. Their attention was turned to the stars, the galaxies. What Shoemaker and his colleagues found was that there was more risk out there, a great deal more, than anyone had ever imagined. Asteroids, as most people know, are rocky objects orbiting in loose formation in a belt between Mars and Jupiter. In illustrations, they are always shown as existing in a jumble, but in fact the solar system is quite a roomy place, and the average asteroid actually will be about 1.5 million kilometers from its nearest neighbor. Nobody knows even approximately how many asteroids there are tumbling through space, but the number is thought to be probably not less than 1 billion. They are presumed to be a planet that never quite made it, owing to the unsettling gravitational pull of Jupiter, which kept and keeps them from coalescing. When asteroids were first detected in the 1800s, the very first was discovered on the first day of the century by a Sicilian named Giuseppe Piazzi. They were thought to be planets, and the first two were named Ceres and Pallas. It took some inspired deductions by the astronomer William Herschel to work out that they were nowhere near planet-sized, but much smaller. He called them asteroids, Latin for star-like, which was slightly unfortunate, as they are not like stars at all. Sometimes now they are more accurately called planetoids. Finding asteroids became a popular activity in the 1800s, and by the end of the century about 1,000 were known. The problem was that no one was systematically recording them. By the early 1900s, it had often become impossible to know whether an asteroid that popped into view was new, or simply one that had been noted earlier and then lost track of. By this time, too, astrophysics had moved on so much that few astronomers wanted to devote their lives to anything as mundane as rocky planetoids. Only a few, notably Gerard Kuiper, the Dutch-born astronomer for whom is named the Kuiper Belt of Comets, took an interest in the solar system at all. Thanks to his work at the McDonald Observatory in Texas, followed later by work done by others at the Minor Planet Center in Cincinnati and the Space Watch Project in Arizona, a long list of lost asteroids was gradually whittled down until by the close of the 20th century only one known asteroid was unaccounted for, an object called 719 Albert. Last seen in October 1911, it was finally tracked down in 2000, after being missing for 89 years. So from the point of view of asteroid research, the 20th century was essentially just a long exercise in bookkeeping. It is really only in the last few years that astronomers have begun to count and keep an eye on the rest of the asteroid community. As of July 2001, 26,000 asteroids had been named and identified, half in just the previous 2 years. With up to 1 billion to identify, the count obviously has barely begun. In a sense, it hardly matters. Identifying an asteroid doesn't make it safe. Even if every asteroid in the solar system had a name and known orbit, no one could say what perturbations might send any one of them hurtling towards us. We can't forecast rock disturbances on our own surface. Put those rocks adrift in space, and what they might do is beyond guessing. Any asteroid out there that has our name on it is very likely to have no other. Think of the Earth's orbit as a kind of motorway on which we are the only vehicle, but which is crossed regularly by pedestrians who don't know enough to look before stepping off the verge. At least 90% of these pedestrians are quite unknown to us. We don't know where they live, what sort of hours they keep, how often they come our way. All we know is at some point, at uncertain intervals, they trundle across the road down which we are cruising at over 100,000 kilometers an hour. As Stephen Ostrow of the Jet Propulsion Laboratory has put it, suppose that there was a button you could push and you could light up all the Earth-crossing asteroids larger than about 10 meters. There would be over 100 million of these objects in the sky. In short, you would see not a couple of thousand distant twinkling stars, but millions upon millions upon millions of nearer, randomly moving objects, all of which are capable of colliding with the Earth, and all of which are moving on slightly different courses through the sky at different rates. It would be deeply unnerving. Well, be unnerved because it is there. We just can't see it. Altogether, it is thought though it is really only a guess based on extrapolating from cratering rates on the Moon, that some 2,000 asteroids big enough to imperil civilized existence regularly cross our orbit. But even a small asteroid, the size of a house, say, could destroy a city. The number of these relative tiddlers in Earth-crossing orbits is almost certainly in the hundreds of thousands, and possibly in the millions, and they are nearly impossible to track. The first one wasn't spotted until 1991, and that was after it had already gone by. Named 1991 BA, it was noticed as it sailed past us at a distance of 170,000 kilometers, in cosmic terms the equivalent of a bullet passing through one's sleeve without touching the arm. 2 years later, another, somewhat larger asteroid missed us by just 145,000 kilometers, the closest pass yet recorded. It, too, was not seen until it had passed, and would have arrived without warning. According to Timothy Ferris, writing in the New Yorker, such near misses probably happen 2 or 3 times a week and go unnoticed. An object 100 meters across couldn't be picked up by any Earth-based telescope until it was within just a few days of us, and that is only if a telescope happened to be trained on it, which is unlikely, because even now the number of people searching for such objects is modest. The arresting analogy that is always made is that the number of people in the world who are actively searching for asteroids is fewer than the staff of a typical McDonald's restaurant. It is actually somewhat higher now, but not much. While Gene Shoemaker was trying to get people galvanized about the potential dangers of the inner solar system, another development, wholly unrelated on the face of it, was quietly unfolding in Italy, with the work of a young geologist from the Lamont Doherty Laboratory at Columbia University. In the early 1970s, Walter Alvarez was doing field work in a comely defile known as the Botaccioni Gorge, near the Umbrian hill town of Gubbio, when he grew curious about a thin band of reddish clay that divided 2 ancient layers of limestone, one from the Cretaceous period, the other from the Tertiary. This is a point known to geology as the KT boundary, and it marks the time, 65 million years ago, when the dinosaurs and roughly half the world's other species of animals abruptly vanished from the fossil record. Alvarez wondered what it was about a thin lamina of clay, barely 6 millimeters thick, that could account for such a dramatic moment in the Earth's history. At the time, the conventional wisdom about the dinosaur extinction was the same as it had been in Charles Lyell's day a century earlier, namely, that the dinosaurs had died out over millions of years. But the thinness of the clay layer clearly suggested that in Umbria, if nowhere else, something rather more abrupt had happened. Unfortunately, in the 1970s, no tests existed for determining how long such a deposit might have taken to accumulate. In the normal course of things, Alvarez almost certainly would have had to leave the problem at that. But luckily he had an impeccable connection to someone outside his discipline who could help. His father, Luis. Luis Alvarez was an eminent nuclear physicist. He had won the Nobel Prize for Physics the previous decade. He had always been mildly scornful of his son's attachment to rocks, but this problem intrigued him. It occurred to him that the answer might lie in dust from space. Every year, the Earth accumulates some 30,000 tons of cosmic spherules, space dust in plainer language, which would be quite a lot if you swept it into one pile, but is infinitesimal when spread across the globe. Scattered through this thin dusting are exotic elements not normally much found on Earth. Among these is the element iridium, which is 1,000 times more abundant in space than in the Earth's crust, because it is thought most of the iridium on Earth sank to the core when the planet was young. Luis Alvarez knew that a colleague of his at the Lawrence Berkeley Laboratory in California, Frank Asaro, had developed a technique for measuring very precisely the chemical composition of clays using a process called neutron activation analysis. This involved bombarding samples with neutrons in a small nuclear reactor and carefully counting the gamma rays that were emitted. It was extremely finicky work. Previously, Asaro had used the technique to analyze pieces of pottery, but Alvarez reasoned that if they measured the amount of one of the exotic elements in his son's soil samples and compared that with its annual rate of deposition, they would know how long it had taken the samples to form. On an October afternoon in 1977, Luis and Walter Alvarez dropped in on Asaro and asked him if he would run the necessary tests for them. It was really quite a presumptuous request. They were asking Asaro to devote months to making the most painstaking measurements of geological samples merely to confirm what seemed entirely self-evident to begin with, that the thin layer of clay had been formed as quickly as its thinness suggested. Certainly no one expected his survey to yield any dramatic breakthroughs. Well, they were very charming, very persuasive, Asaro recalled in an interview in 2002. And it seemed an interesting challenge, so I agreed to try. Unfortunately, I had a lot of other work on, so it was 8 months before I could get to it. He consulted his notes from the period. On June 21st, 1978, at 1:45 p.m., we put a sample in the detector. It ran for 224 minutes, and we could see we were getting interesting results, so we stopped it and had a look. The results were so unexpected, in fact, that the 3 scientists at first thought they had to be wrong. The amount of iridium in the Alvarez sample was more than 300 times normal levels, far beyond anything they might have predicted. Over the following months, Asaro and his colleague Helen Michel worked up to 30 hours at a stretch. Once you started, you couldn't stop, Asaro explained, analyzing samples, always with the same results. Tests on other samples from Denmark, Spain, France, New Zealand, Antarctica showed that the iridium deposit was worldwide and greatly elevated everywhere, sometimes by as much as 500 times normal levels. Clearly, something big and abrupt, and probably cataclysmic, had produced this arresting spike. After much thought, the Alvarezes concluded that the most plausible explanation, plausible to them at any rate, was that the Earth had been struck by an asteroid or comet. The idea that the Earth might be subjected to devastating impacts from time to time was not quite as new as is now sometimes suggested. As far back as 1942, a Northwestern University astrophysicist named Ralph B. Baldwin had suggested such a possibility in an article in Popular Astronomy magazine. He published the article there because no academic publisher was prepared to run it, and at least 2 well-known scientists, the astronomer Ernst Opek and the chemist and Nobel laureate Harold Urey, had also voiced support for the notion at various times. Even among paleontologists, it was not unknown. In 1956, a professor at Oregon State University, M.W. de Laubenfels, writing in the Journal of Paleontology, had actually anticipated the Alvarez theory by suggesting that the dinosaurs may have been dealt a death blow by an impact from space. And in 1970, the president of the American Paleontological Society, Dewey J. McLaren, proposed at the group's annual conference the possibility that an extraterrestrial impact may have been the cause of an earlier event, known as the Frasnian extinction. As if to underline just how unnovel the idea had become by this time, in 1979, a Hollywood studio actually produced a movie called Meteor. It's 5 miles wide, it's coming at 30,000 miles per hour, and there's no place to hide. Starring Henry Fonda, Natalie Wood, Carl Malden, and a very large rock. So when, in the first week of 1980, at a meeting of the American Association for the Advancement of Science, the Alvarezes announced their belief that the dinosaur extinction had not taken place over millions of years, as part of some slow, inexorable process, but suddenly, in a single explosive event, it shouldn't have come as a shock. But it did. It was received everywhere, but particularly in the paleontological world, as an outrageous heresy. Well, you have to remember, Asaro recalls, that we were amateurs in this field.
Walter was a geologist specializing in paleomagnetism. Luis was a physicist, and I was a nuclear chemist. And now here we were telling paleontologists that we had solved a problem that had eluded them for over a century. It's not terribly surprising that they didn't embrace it immediately. As Luis Alvarez joked, we were caught practicing geology without a license. But there was also something much deeper and more fundamentally abhorrent in the impact theory. The belief that terrestrial processes were gradual had been elemental in natural history since the time of Lyell. By the 1980s, catastrophism had been out of fashion for so long that it had become literally unthinkable. For most geologists, the idea of a devastating impact was, as Eugene Shoemaker noted, against their scientific religion. Nor did it help that Luis Alvarez was openly contemptuous of paleontologists and their contributions to scientific knowledge. "They're really not very good scientists. They're more like stamp collectors," he wrote in the New York Times in an article that stings yet. Opponents of the Alvarez theory produced any number of alternative explanations for the iridium deposits. For instance, that they were generated by prolonged volcanic eruptions in India, called the Deccan traps. Trap comes from a Swedish word for a type of lava. Deccan is the name of the area today. And above all insisted that there was no proof that the dinosaurs disappeared abruptly from the fossil record at the iridium boundary. One of the most vigorous opponents was Charles Officer of Dartmouth College. He insisted that the iridium had been deposited by volcanic action, even while conceding in a newspaper interview that he had no actual evidence of it. As late as 1988, more than half of all American paleontologists contacted in a survey continued to believe that the extinction of the dinosaurs was in no way related to an asteroid or cometary impact. The one thing that would most obviously support the Alvarez's theory was the one thing they didn't have: an impact site. Enter Eugene Shoemaker. Shoemaker had an Iowa connection. His daughter-in-law taught at the University of Iowa, and he was familiar with the Manson crater from his own studies. Thanks to him, all eyes now turn to Iowa. Geology is a profession that varies from place to place. In Iowa, a state that is flat and stratigraphically uneventful, it tends to be comparatively serene. There are no alpine peaks or grinding glaciers, no great deposits of oil or precious metals, not a hint of a pyroclastic flow. If you're a geologist employed by the state of Iowa, a big part of the work you do is to evaluate manure management plans, which all the state's animal confinement operators, pig farmers to the rest of us, are required to file periodically. There are 15 million pigs in Iowa, so a lot of manure to manage. I'm not mocking this at all. It's vital and enlightened work. It keeps Iowa's water clean. But with the best will in the world, it's not exactly dodging lava bombs on Mount Pinatubo, or scrabbling over crevasses on the Greenland ice sheet in search of ancient life-bearing quartzes. So we may well imagine the flutter of excitement that swept through the Iowa Department of Natural Resources when, in the mid-1980s, the world's geological attention focused on Manson and its crater. Trowbridge Hall in Iowa City is a turn-of-the-century pile of red brick that houses the University of Iowa's Earth Sciences Department, and, way up in a kind of garret, the geologists of the Iowa Department of Natural Resources. No one now can remember quite when, still less why, the state geologists were placed in an academic facility, but you get the impression that the space was conceded grudgingly, for the offices are cramped and low-ceilinged, and not very accessible. When being shown the way, you half expect to be taken out onto a roof ledge and helped in through a window. Ray Anderson and Brian Witzka spend their working lives up here, amid disordered heaps of papers, journals, furled charts, and hefty specimen stones. Geologists are never at a loss for paperweights. It's the kind of space where if you want to find anything, an extra chair, a coffee cup, a ringing telephone, you have to move stacks of documents around.
Suddenly we were at the center of things, Anderson told me, gleaming at the memory of it, when I met him and Witzke in their offices on a dismal, rainy morning in June. It was a wonderful time. I asked them about Gene Shoemaker, a man who seems to have been universally revered. "He was just a great guy," Witzke replied without hesitation. "If it hadn't been for him, the whole thing would have never gotten off the ground. Even with his support, it took 2 years to get it up and running. Drilling's an expensive business, about $35 a foot back then. More now. And we needed to go down 3,000 feet. Sometimes more than that," Anderson added. "Sometimes more than that," Witzke agreed. "And at several locations, so you're talking a lot of money. Certainly more than our budget would allow." So a collaboration was formed between the Iowa Geological Survey and the U.S. Geological Survey. "At least, we thought it was a collaboration," said Anderson, producing a small, pained smile. "It was a real learning curve for us," Witzke went on. "There was actually quite a lot of bad science going on throughout the period, people rushing in with results that didn't always stand up to scrutiny. One of those moments came at the annual meeting of the American Geophysical Union in 1985, when Glenn Izzett and C.L. Pillmore of the U.S. Geological Survey announced that the Manson crater was of the right age to have been involved with the dinosaurs' extinction. The declaration attracted a good deal of press attention, but was unfortunately premature. A more careful examination of the data revealed that Manson was not only too small, but also 9 million years too early. The first Anderson or Witzke learned of this setback to their careers was when they arrived at a conference in South Dakota and found people coming up to them with sympathetic looks and saying, "We hear you lost your crater." It was news to them that Izzett and the other USGS scientists had just announced refined figures revealing that Manson couldn't after all have been the extinction crater. "It was pretty stunning," recalls Anderson. "I mean, we had this thing that was really important, and then suddenly we didn't have it anymore. But even worse was the realization that the people we thought we'd been collaborating with hadn't bothered to share with us their new findings. Why not?" He shrugged. "Who knows? Anyway, it was a pretty good insight into how unattractive science can get when you're playing at a certain level." The search moved elsewhere. By chance, in 1990, one of the searchers, Alan Hildebrand of the University of Arizona, met a reporter from the Houston Chronicle who happened to know about a large, unexplained ring formation 193 kilometers wide and 48 kilometers deep under Mexico's Yucatan Peninsula at Chicxulub, near the city of Progreso, about 950 kilometers due south of New Orleans. The formation had been found by Pemex, the Mexican oil company, in 1952, the year, coincidentally, that Gene Shoemaker first visited Meteor Crater in Arizona. But the company's geologists had concluded that it was volcanic, in line with the thinking of the day. Hildebrand traveled to the site and decided fairly swiftly that they had their crater. By early 1991, it had been established to nearly everyone's satisfaction that Chicxulub was the impact site. Still, many people didn't quite grasp what an impact could do. As Stephen Jay Gould recalled in one of his essays, "I remember harboring some strong initial doubts about the efficacy of such an event. Why should an object only 6 miles across wreak such havoc upon a planet with a diameter of 8,000 miles? Conveniently, a natural test of the theory arose soon after, when the Shoemakers and Levy discovered Comet Shoemaker-Levy 9, which they soon realized was headed for Jupiter. For the first time, humans would be able to witness a cosmic collision, and witness it very well thanks to the new Hubble Space Telescope. Most astronomers, according to Curtis Peebles, expected little, particularly as the comet was not a coherent sphere, but a string of 21 fragments. "My sense," wrote one, "is that Jupiter will swallow these comets up without so much as a burp." 1 week before the impact, Nature ran an article, "The Big Fizzle is Coming," predicting that the impact would constitute nothing more than a meteor shower. The impacts began on the 16th of July, 1994, went on for a week, and were bigger by far than anyone, with the possible exception of Gene Shoemaker, expected. One fragment, known as Nucleus G, struck with a force of about 6 million megatons, 75 times all the nuclear weaponry in existence. Nucleus G was only about the size of a small mountain, but it created wounds in the Jovian surface the size of Earth. It was the final blow for critics of the Alvarez theory. Luis Alvarez never knew of the discovery of the Chicxulub crater or of the Shoemaker-Levy comet, as he died in 1988. Shoemaker also died early. On the 3rd anniversary of the Jupiter collision, he and his wife were in the Australian outback, where they went every year to search for impact sites. On a dirt track in the Tanami Desert, normally one of the emptiest places on Earth, they came over a slight rise just as another vehicle was approaching. Shoemaker was killed instantly, his wife injured. Some of his ashes were sent to the moon aboard the Lunar Prospector spacecraft. The rest were scattered around Meteor Crater. Anderson and Witzke no longer had the crater that killed the dinosaurs, but we still had the largest and most perfectly preserved impact crater in the mainland United States, Anderson said. A little verbal dexterity is required to keep Manson's superlative status. Other craters are larger, notably Chesapeake Bay, which was recognized as being an impact site in 1994, but they are either offshore or deformed. Chicxulub is buried under 2 to 3 kilometers of limestone and mostly offshore, which makes it difficult to study, Anderson went on, while Manson is really quite accessible. It's because it is buried that it is actually comparatively pristine. I asked them how much warning we would receive if a similar hunk of rock were coming towards us today. "Oh, probably none," said Anderson breezily. "It wouldn't be visible to the naked eye until it warmed up, and that wouldn't happen until it hit the atmosphere, which would be about 1 second before it hit the Earth. You're talking about something moving many tens of times faster than the fastest bullet. Unless it had been seen by someone with a telescope, and that's by no means a certainty, it would take us completely by surprise." How hard an impactor hits depends on a lot of variables: angle of entry, velocity and trajectory, whether the collision is head-on or from the side, and the mass and density of the impacting object, among much else, none of which we can know so many millions of years after the fact. But what scientists can do, and Anderson and Witzke have done, is measure the impact site and calculate the amount of energy released. From that, they can work out plausible scenarios of what it must have been like, or, more chillingly, would be like if it happened now. An asteroid or comet traveling at cosmic velocities would enter the Earth's atmosphere at such a speed that the air beneath it couldn't get out of the way and would be compressed, as in a bicycle pump. As anyone who has used such a pump knows, compressed air grows swiftly hot, and the temperature below it would rise to some 60,000 Kelvin, or 10 times the surface temperature of the Sun. In this instant of its arrival in our atmosphere, everything in the meteor's path, people, houses, factories, cars, would crinkle and vanish like cellophane in a flame. 1 second after entering the atmosphere, the meteorite would slam into the Earth's surface where the people of Manson had a moment before been going about their business. The meteorite itself would vaporize instantly, but the blast would blow out 1,000 cubic kilometers of rock, earth, and superheated gases. Every living thing within 250 kilometers that hadn't been killed by the heat of entry would now be killed by the blast. Radiating outwards at almost the speed of light would be the initial shock wave, sweeping everything before it. For those outside the zone of immediate devastation, the first inkling of catastrophe would be a flash of blinding light, the brightest ever seen by human eyes, followed an instant to a minute or two later by an apocalyptic sight of unimaginable grandeur, a roiling wall of darkness reaching high into the heavens, filling one entire field of view, and traveling at thousands of kilometers an hour. Its approach would be eerily silent, since it would be moving far beyond the speed of sound. Anyone in a tall building in Omaha or Des Moines, say, who chanced to look in the right direction would see a bewildering veil of turmoil followed by instantaneous oblivion. Within minutes, over an area stretching from Denver to Detroit and encompassing what had once been Chicago, St. Louis, Kansas City, the Twin Cities, the whole of the Midwest, in short, nearly every standing thing would be flattened or on fire, and nearly every living thing would be dead. People up to 1,500 kilometers away would be knocked off their feet and sliced or clobbered by a blizzard of flying projectiles. Beyond 1,500 kilometers, the devastation from the blast would gradually diminish. But that's just the initial shock wave. No one can do more than guess what the associated damage would be, other than that it would be brisk and global. The impact would almost certainly set off a chain of devastating earthquakes. Volcanoes across the globe would begin to rumble and spew. Tsunamis would rise up and head devastatingly for distant shores. Within an hour, a cloud of blackness would cover the earth, and burning rock and other debris would be pelting down everywhere, setting much of the planet ablaze. It has been estimated that at least 1.5 billion people would be dead by the end of the first day. The massive disturbances to the ionosphere would knock out communication systems everywhere, so survivors would have no idea what was happening elsewhere or where to turn. It would hardly matter. As one commentator has put it, fleeing would mean selecting a slow death over a quick one. The death toll would be very little affected by any plausible relocation effort, since Earth's ability to support life would be universally diminished. The amount of soot and floating ash from the impact and following fires would blot out the sun, certainly for months, possibly for years, disrupting growing cycles. In 2001, researchers at the California Institute of Technology analyzed helium isotopes from sediments left from the later KT impact and concluded that it affected the Earth's climate for about 10,000 years. This was actually used as evidence to support the notion that the extinction of dinosaurs was swift and emphatic, and so it was in geological terms. We can only guess how well or whether humanity would cope with such an event. And in all likelihood, remember, this would come without warning, out of a clear sky. But let's suppose we did see the object coming. What would we do? Everyone assumes we would send up a nuclear warhead and blast it to smithereens. There are some problems with that idea, however. First, as John S. Lewis notes, our missiles are not designed for space work. They haven't the oomph to escape Earth's gravity. And even if they did, there are no mechanisms to guide them across tens of millions of kilometers of space. Still less could we send up a shipload of space cowboys to do the job for us, as in the movie Armageddon. We no longer possess a rocket powerful enough to send humans even as far as the moon. The last rocket that could, Saturn V, was retired years ago and has never been replaced. Nor could we quickly build a new one because, amazingly, the plans for Saturn launchers were destroyed as part of a NASA spring cleaning exercise. Even if we did manage somehow to get a warhead to the asteroid and blast it to pieces, the chances are that we would simply turn it into a string of rocks that would slam into us one after the other in the manner of Comet Shoemaker-Levy on Jupiter. But with the difference that now the rocks would be intensely radioactive. Tom Garrels, an asteroid hunter at the University of Arizona, thinks that even a year's warning would probably be insufficient to take appropriate action. The greater likelihood, however, is that we wouldn't see any object, even a comet, until it was about 6 months away, which would be much too late. Shoemaker-Levy 9 had been orbiting Jupiter in a fairly conspicuous manner since 1929, but it was over half a century before anyone noticed. Because these things are so difficult to compute and must incorporate such a significant margin of error, even if we knew an object was heading our way, we wouldn't know until nearly the end, the last couple of weeks anyway, whether collision was certain. For most of the time of the object's approach, we would exist in a kind of cone of uncertainty. It would certainly be the most interesting few months in the history of the world. And imagine the party if it passed safely. So how often does something like the Manson impact happen? I asked Anderson and Witzke before leaving. Oh, about once every 1,000,000 years on average, said Witzke. And remember, added Anderson, this was a relatively minor event. Do you know how many extinctions were associated with the Manson impact? No idea, I replied. None, he said with a strange air of satisfaction. Not one. Of course, Witzke and Anderson added hastily, and more or less in unison, there would have been terrible devastation across much of the earth, as just described, and complete annihilation for hundreds of miles around Ground Zero. But life is hardy, and when the smoke cleared, there were enough lucky survivors from every species that none permanently perished. The good news, it appears, is that it takes an awful lot to extinguish a species. The bad news is that the good news can never be counted on. Worse still, it isn't actually necessary to look to space for petrifying danger. As we are about to see, Earth can provide plenty of danger of its own. 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 Chapter 14. The Fire Below. In the summer of 1971, a young geologist named Mike Voorhees was scouting around on some grassy farmland in eastern Nebraska, not far from the little town of Orchard, where he had grown up. Passing through a steep-sided gully, he spotted a curious glint in the brush above and clambered up to have a look. What he had seen was the perfectly preserved skull of a young rhinoceros, which had been washed out by recent heavy rains. A few yards beyond, it turned out, was one of the most extraordinary fossil beds ever discovered in North America, a dried-up waterhole that had served as a mass grave for scores of animals, rhinoceroses, zebra-like horses, saber-toothed deer, camels, turtles. All had died from some mysterious cataclysm just under 12 million years ago in the time known to geology as the Miocene. In those days, Nebraska stood on a vast, hot plain, very like the Serengeti of Africa today. The animals had been found buried under volcanic ash up to 3 meters deep. The puzzle of it was that there were not, and never had been, any volcanoes in Nebraska. Today, the site of Voorhees' discovery is called Ashfall Fossil Beds State Park. It has a stylish new visitor center and museum with thoughtful displays on the geology of Nebraska and the history of the fossil beds. The center incorporates a lab with a glass wall through which visitors can watch paleontologists cleaning bones. Working alone in the lab on the morning I passed through was a cheerfully grizzled-looking fellow in a blue work shirt whom I recognized as Mike Voorhees from a BBC Horizon documentary in which he had featured. They don't get a huge number of visitors to Ashfall Fossil Beds State Park. It's slightly in the middle of nowhere, and Voorhees seemed pleased to show me around. He took me to the spot atop a 6-meter-high ravine where he had made his find. It was a dumb place to look for bones, he said happily. But I wasn't looking for bones. I was thinking of making a geological map of eastern Nebraska at the time, and really just kind of poking around. If I hadn't gone up this ravine, or the rains hadn't just washed out that skull, I'd have walked on by and this would never have been found. He indicated a roofed enclosure nearby, which had become the main excavation site. There, some 200 animals had been found lying together in a jumble. I asked him in what way was it a dumb place to hunt for bones. Well, if you're looking for bones, you really need exposed rock. That's why most paleontology is done in hot, dry places. It's not that there are more bones there. It's just that you have some chance of spotting them. In a setting like this, he made a sweeping gesture across the vast and unvarying prairie, you wouldn't know where to begin. There could be really magnificent stuff out there, but there's no surface clues to show you where to start looking. At first, they thought the animals were buried alive, and Voorhees stated as much in a National Geographic article in 1981. The article called the site a Pompeii of prehistoric animals, he told me, which was unfortunate because just afterwards we realized that the animals hadn't died suddenly at all. They were all suffering from something called hypertrophic pulmonary osteodystrophy, which is what you would get if you were breathing a lot of abrasive ash. And they must have been breathing a lot of it because the ash was feet thick for hundreds of miles. He picked up a chunk of grayish clay-like dirt and crumbled it into my hand. It was powdery but slightly gritty. Nasty stuff to have to breathe, he went on, because it's very fine but also quite sharp. So anyway, they came here to this watering hole, presumably seeking relief, and died in some misery. The ash would have ruined everything. It would have buried all the grass and coated every leaf and turned the water into an undrinkable gray sludge. It couldn't have been very agreeable at all. The Horizon documentary had suggested that the existence of so much ash in Nebraska was a surprise. In fact, Nebraska's huge ash deposits had been known about for a long time. For almost a century they had been mined to make household cleaning powders like Comet and Ajax. But curiously, no one had ever thought to wonder where all the ash came from. I'm a little embarrassed to tell you, Voorhees said, smiling briefly, that the first I thought about it was when an editor at the National Geographic asked me the source of all the ash, and I had to confess that I didn't know. Nobody knew. Voorhees sent samples to colleagues all over the western United States, asking if there was anything about it that they recognized. Several months later, a geologist named Bill Bonishen from the Idaho Geological Survey got in touch and told him that the ash matched a volcanic deposit from a place called Bruno Jarbidge in southwest Idaho. The event that killed the plains animals of Nebraska was a volcanic explosion on a scale previously unimagined, but big enough to leave an ash layer 3 meters deep, some 1,600 kilometers away in eastern Nebraska. It turned out that under the western United States there was a huge cauldron of magma, a colossal volcanic hotspot, which erupted cataclysmically every 600,000 years or so. The last such eruption was just over 600,000 years ago. The hotspot is still there. These days, we call it Yellowstone National Park. We know amazingly little about what happens beneath our feet. It is fairly remarkable to think that Ford has been building cars and Nobel committees awarding prizes for longer than we have known that the Earth has a core. And of course the idea that the continents move about on the surface like lily pads has been common wisdom for much less than a generation. Strange as it may seem, wrote Richard Feynman, we understand the distribution of matter in the interior of the sun far better than we understand the interior of the Earth. The distance from the surface of the Earth to the middle is 6,370 kilometers, which isn't so very far. It has been calculated that if you sunk a well to the center and dropped a brick down it, it would take only 45 minutes for it to hit the bottom, though at that point it would be weightless since all the Earth's gravity would be above and around it rather than beneath it. Our own attempts to penetrate towards the middle have been modest indeed. 1 or 2 South African gold mines reach a depth of over 3 kilometers, but most mines on Earth go no more than about 400 meters beneath the surface. If the planet were an apple, we wouldn't yet have broken through the skin. Indeed, we haven't even come close. Until slightly under a century ago, what the best-informed scientific minds knew about Earth's interior was not much more than what a coal miner knew. Namely, that you could dig down through soil for a distance, and then you'd hit rock. And that was about it. Then, in 1906, an Irish geologist named R.D. Oldham, while examining some seismograph readings from an earthquake in Guatemala, noticed that certain shock waves had penetrated to a point deep within the Earth and then bounced off at an angle, as if they had encountered some kind of barrier. From this he deduced that the Earth has a core. 3 years later, a Croatian seismologist named Andrija Mohorovičić was studying graphs from an earthquake in Zagreb when he noticed a similar odd deflection, but at a shallower level. He had discovered the boundary between the crust and the layer immediately below, the mantle. This zone has been known ever since as the Mohorovičić discontinuity, or MOHO for short. We were beginning to get a vague idea of the Earth's layered interior, though it really was only vague. Not until 1936 did a Danish scientist named Inge Lehmann, studying seismographs of earthquakes in New Zealand, discover that there were two cores, an inner one, which we now believe to be solid, and an outer one, the one that Oldham had detected, which is thought to be liquid, and the seat of magnetism. At just about the time that Lehmann was refining our basic understanding of the Earth's interior by studying the seismic waves of earthquakes, two geologists at Caltech in California were devising a way to make comparisons between one earthquake and the next. They were Charles Richter and Benno Gutenberg, though for reasons that have nothing to do with fairness, the scale became known almost at once as Richter's alone. They were nothing to do with Richter either. A modest fellow, he never referred to the scale by his own name, but always called it the magnitude scale. The Richter scale has always been widely misunderstood by non-scientists, though it is perhaps a little less so now than in its early days, when visitors to Richter's office often asked to see his celebrated scale, thinking it was some kind of machine. The scale is, of course, more an idea than a thing, an arbitrary measure of the Earth's tremblings based on surface measurements. It rises exponentially, so that a 7.3 quake is 50 times more powerful than a 6.3 earthquake, and 2,500 times more powerful than a 5.3 earthquake. Theoretically, at least, there is no upper limit for an earthquake, nor, come to that, a lower limit. The scale is a simple measure of force, but says nothing about damage. A magnitude 7 quake happening deep in the mantle, say 650 kilometers down, might cause no surface damage at all, while a significantly smaller one, happening just 6 or 7 kilometers under the surface, could wreak widespread devastation. Much, too, depends on the nature of the subsoil, the quake's duration, the frequency and severity of aftershocks, and the physical setting of the affected area. All this means that the most fearsome quakes are not necessarily the most forceful, though force obviously counts for a lot. The largest earthquake since the scale's invention was, depending on which source you credit, either one centered on Prince William Sound in Alaska in March 1964, which measured 9.2 on the Richter scale, or one in the Pacific Ocean off the coast of Chile in 1960, which was initially logged at 8.6 magnitude, but later revised upwards by some authorities, including the U.S. Geological Survey, to a truly grand scale 9.5. As you will gather from this, measuring earthquakes is not always an exact science, particularly when it involves interpreting readings from remote locations. At all events, both quakes were whopping. The 1960 quake not only caused widespread damage across coastal South America, but also set off a giant tsunami that rolled nearly 10,000 kilometers across the Pacific and slapped away much of downtown Hilo, Hawaii, destroying 500 buildings and killing 60 people. Similar wave surges claimed yet more victims as far away as Japan and the Philippines. For pure focused devastation, however, probably the most intense earthquake in recorded history was one that struck and essentially shook to pieces Lisbon, Portugal, on All Saints' Day, the 1st of November, 1755. Just before 10 in the morning, the city was hit by a sudden sideways lurch, now estimated at magnitude 9.0, and shaken ferociously for 7 full minutes. The convulsive force was so great that the water rushed out of the city's harbor and returned in a wave over 15 meters high, adding to the destruction. When at last the motion ceased, survivors enjoyed just 3 minutes of calm before a second shock came, only slightly less severe than the first. A third and final shock followed 2 hours later. At the end of it all, 60,000 people were dead, and virtually every building for miles reduced to rubble. The San Francisco earthquake of 1906, for comparison, measured an estimated 7.8 on the Richter scale and lasted less than 30 seconds. Earthquakes are fairly common. Every day, on average, somewhere in the world, there are 2 of magnitude 2.0 or greater. That's enough to give anyone nearby a pretty good jolt. Although they tend to cluster in certain places, notably around the rim of the Pacific, they can occur almost anywhere. In the United States, only Florida, eastern Texas, and the upper Midwest seem, so far, to be almost entirely immune. New England has had 2 quakes of magnitude 6.0 or greater in the last 200 years. In April 2002, the region experienced a 5.1 magnitude shaking in a quake near Lake Champlain on the New York-Vermont border, causing extensive local damage and, I can attest, knocking pictures from walls and children from beds as far away as New Hampshire. The most common types of earthquakes are those where 2 plates meet, as in California along the San Andreas Fault. As the plates push against each other, pressures build up until one or the other gives way. In general, the longer the interval between quakes, the greater the pent-up pressure, and thus the greater the scope for a really big jolt. This is a particular worry for Tokyo, which Bill McGuire, a hazard specialist at University College London, describes as the city waiting to die, not a motto you will find on many tourism leaflets. Tokyo stands on the meeting point of 3 tectonic plates in a country already well known for its seismic instability. In 1995, as you will remember, the city of Kobe, nearly 500 kilometers to the west, was struck by a magnitude 7.2 quake, which killed 6,394 people. The damage was estimated at $99 billion. But that was as nothing, well, as comparatively little, compared with what may await Tokyo. Tokyo has already suffered one of the most devastating earthquakes in modern times. On the 1st of September 1923, just before midday, the city was hit by what is known as the Great Kanto Quake, an event over 10 times as powerful as Kobe's earthquake. 200,000 people were killed. Since that time, Tokyo has been eerily quiet, so the strain beneath the surface has been building for 80 years. Eventually, it is bound to snap. In 1923, Tokyo had a population of about 3 million. Today, it is approaching 30 million. Nobody cares to guess how many people might die, but the potential economic cost has been put as high as $7 trillion. Even more unnerving, because they are less well understood and capable of occurring anywhere at any time, are the rarer shakings of the type known as intraplate quakes. These happen away from plate boundaries, which makes them wholly unpredictable. And because they come from a much greater depth, they tend to propagate over much wider areas. The most notorious such quakes ever to hit the United States were a series of 3 in New Madrid, Missouri, in the winter of 1811 and 12. The adventure started just after midnight on the 16th of December, when people were awakened first by the noise of panicking farm animals. The restiveness of animals before quakes is not an old wives' tale, but is in fact well established, though not at all understood. And then by an almighty rupturing noise from deep within the earth. Emerging from their houses, locals found the land rolling in waves up to a meter high and opening up in fissures several meters deep. A strong smell of sulfur filled the air. The shaking lasted for 4 minutes, with the usual devastating effects to property. Among the witnesses was the artist John James Audubon, who happened to be in the area. The quake radiated outwards with such force that it knocked down chimneys in Cincinnati, over 600 kilometers away, and, according to at least one account, wrecked boats in East Coast harbors, and even collapsed scaffolding erected around the Capitol building in Washington, D.C. On the 23rd of January and the 4th of February, further quakes of similar magnitude followed. New Madrid has been silent ever since, but not surprisingly, since such episodes have never been known to happen in the same place twice. As far as we know, they are as random as lightning. The next one could be under Chicago, or Paris, or Kinshasa. No one can even begin to guess. And what causes these massive intraplate rupturings? Something deep within the earth. More than that, we don't know. By the 1960s, scientists had grown sufficiently frustrated by how little they understood of the Earth's interior that they decided to try to do something about it. Specifically, they got the idea to drill through the ocean floor — the continental crust was too thick — to the Moho discontinuity and to extract a piece of the Earth's mantle for examination at leisure. The thinking was that if they could understand the nature of the rocks inside the Earth, they might begin to understand how they interacted, and thus possibly be able to predict earthquakes and other unwelcome events. The project became known all but inevitably as the Mohole, and it was pretty well disastrous. The hope was to lower a drill through over 4,000 meters of Pacific Ocean water off the coast of Mexico, and drill some 5,000 meters through relatively thin crustal rock. Drilling from a ship in open waters is, in the words of one oceanographer, like trying to drill a hole in the sidewalks of New York from atop the Empire State Building using a strand of spaghetti. Every attempt ended in failure. The deepest they penetrated was only about 180 meters. The Mohole became known as the No-Hole. In 1966, exasperated with ever-rising costs and no results, Congress killed the project. 4 years later, Soviet scientists decided to try their luck on dry land. They chose a spot on Russia's Kola Peninsula, near the Finnish border, and set to work with the hope of drilling to a depth of 15 kilometers. The work proved harder than expected, but the Soviets were commendably persistent. When at last they gave up, 19 years later, they had drilled to a depth of 12,262 meters. Bearing in mind that the crust of the Earth represents only about 0.3% of the planet's volume, and that the Kola hole had not cut even 1/3 of the way through the crust, we can hardly claim to have conquered the interior. Even though the hole was modest, nearly everything about what it revealed surprised the researchers. Seismic wave studies had led the scientists to predict, and pretty confidently, that they would encounter sedimentary rock to a depth of 4,700 meters, followed by granite for the next 2,300 meters, and basalt from there on down. In the event, the sedimentary layer was 50% deeper than expected, and the basaltic layer was never found at all. Moreover, the world down there was far warmer than anyone had expected, with a temperature at 10,000 meters of 180 degrees Celsius, nearly twice the forecast level. Most surprising of all was that the rock at depth was saturated with water, something that had not been thought possible. Because we can't see into the Earth, we have to use other techniques, which mostly involve reading waves as they travel through the interior, to find out what is there. We know a little bit about the mantle from what are known as kimberlite pipes, where diamonds are formed. What happens is that deep in the Earth there is an explosion that fires in effect a cannonball of magma to the surface at supersonic speeds. It is a totally random event. A kimberlite pipe could explode in your back garden as you listen to this. Because they come up from such depths, up to 200 kilometers down, kimberlite pipes bring up all kinds of things not normally found on or near the surface. A rock called peridotite, crystals of olivine, and just occasionally, in about one pipe in 100, diamonds. Lots of carbon comes up with kimberlite ejecta, but most is vaporized or turns to graphite. Only occasionally does a hunk of it shoot up at just the right speed and cool down with the necessary swiftness to become a diamond. It was just such a pipe that made Johannesburg the most productive diamond mining city in the world. But there may be others, even bigger, that we don't know about. Geologists know that somewhere in the vicinity of northeastern Indiana there is evidence of a pipe or group of pipes that may be truly colossal. Diamonds up to 20 carats or more have been found at scattered sites throughout the region, but no one has ever found the source. As John McPhee notes, it may be buried under glacially deposited soil, like the Manson crater in Iowa, or under the Great Lakes. So how much do we know about what's inside the Earth? Very little. Scientists are generally agreed that the world beneath us is composed of 4 layers: a rocky outer crust, a mantle of hot, viscous rock, a liquid outer core, and a solid inner core. We know that the surface is dominated by silicates, which are relatively light and not heavy enough to account for the planet's overall density. Therefore, there must be heavier stuff inside. We know that to generate our magnetic field, somewhere in the interior there must be a concentrated belt of metallic elements in a liquid state. That much is universally accepted. Almost everything beyond that, how the layers interact, what causes them to behave in the way they do, what they will do at any time in the future, is a matter of at least some uncertainty, and generally quite a lot of uncertainty. Even the one part of it we can see, the crust, is a matter of some fairly strident debate. Nearly all geology texts tell you that continental crust is 5 to 10 kilometers thick under the oceans, about 40 kilometers thick under the continents, and 65 to 95 kilometers thick under big mountain chains, but there are many puzzling variabilities within these generalizations. The crust beneath the Sierra Nevada mountains, for instance, is only about 30 to 40 kilometers thick, and no one knows why. By all the laws of geophysics, the Sierra Nevadas should be sinking, as if into quicksand. Some people think they may be. How and when the Earth got its crust are questions that divide geologists into 2 broad camps: those who think it happened abruptly, early in the Earth's history, and those who think it happened gradually and rather later. Strength of feeling runs deep on such matters. Richard Armstrong of Yale proposed an early burst theory in the 1960s, then spent the rest of his career fighting those who did not agree with him. He died of cancer in 1991, but shortly before his death he lashed out at his critics in a polemic in an Australian earth science journal that charged them with perpetuating myths. According to a report in Earth magazine in 1998, "He died a bitter man," reported a colleague. The crust and part of the outer mantle together are called the lithosphere, from the Greek lithos meaning stone, which in turn floats on top of a layer of softer rock called the asthenosphere, from Greek words meaning without strength. But such terms are never entirely satisfactory. To say that the lithosphere floats on top of the asthenosphere suggests a degree of easy buoyancy that isn't quite right. Similarly, it is misleading to think of the rocks as flowing in anything like the way we think of materials flowing on the surface. The rocks are viscous, but only in the same way that glass is. It may not look it, but all the glass on Earth is flowing downwards under the relentless drag of gravity. Remove a pane of really old glass from the window of a European cathedral, and it will be noticeably thicker at the bottom than at the top. That is the sort of flow we are talking about. The hour hand on a clock moves about 10,000 times faster than the flowing rocks of the mantle. The movements occur not just laterally, as the Earth's plates move across the surface, but up and down, too, as rocks rise and fall under the churning process known as convection. Convection as a process was first deduced by the eccentric Count von Rumford at the end of the 18th century. 60 years later, an English vicar named Osmond Fisher presciently suggested that the Earth's interior might well be fluid enough for the contents to move about, but that idea took a very long time to gain support. In about 1970, when geophysicists realized just how much turmoil was going on down there, It came as a considerable shock. As Shauna Vogel put it in the book Naked Earth, The New Geophysics, it was as if scientists had spent decades figuring out the layers of the Earth's atmosphere, troposphere, stratosphere, and so forth, and then had suddenly found out about wind. How deep the convection process goes has been a matter of controversy ever since. Some say it begins 650 kilometers down. Others more than 3,000 kilometers below us. The problem, as James Trefil has observed, is that there are two sets of data from two different disciplines that cannot be reconciled. Geochemists say that certain elements on the planet's surface cannot have come from the upper mantle, but must have come from deeper within the Earth. Therefore, the materials in the upper and lower mantle must at least occasionally mix. Seismologists insist that there is no evidence to support such a thesis. So all that can be said is that at some slightly indeterminate point as we head towards the center of the Earth, we leave the asthenosphere and plunge into pure mantle. Considering that it accounts for 82% of the Earth's volume and 65% of its mass, the mantle doesn't attract a great deal of attention, largely because the things that interest Earth scientists and general readers alike happen either deeper down, as with magnetism, or nearer the surface, as with earthquakes. We know that to a depth of about 150 kilometers, the mantle consists predominantly of a type of rock known as peridotite. But what fills the next 2,650 kilometers is uncertain. According to a Nature report, it seems not to be peridotite. More than this, we do not know. Beneath the mantle are the two cores, a solid inner core and a liquid outer one. Needless to say, our understanding of the nature of these cores is indirect, but scientists can make some reasonable assumptions. They know that the pressures at the center of the Earth are sufficiently high, something over 3 million times those found at the surface, to turn any rock there solid. They also know from the Earth's history, among other clues, that the inner core is very good at retaining its heat. Although it is little more than a guess, it is thought that in over 4 billion years, the temperature at the core has fallen by no more than 110 degrees Celsius. No one knows exactly how hot the Earth's core is, but estimates range from something over 4,000 degrees to over 7,000 degrees Celsius, about as hot as the surface of the sun. The outer core is in many ways even less well understood, though everyone is in agreement that it is fluid and that it is the seat of magnetism. The theory was put forward by E.C. Bullard of Cambridge University in 1949 that this fluid part of the Earth's core revolves in a way that makes it, in effect, an electrical motor, creating the Earth's magnetic field. The assumption is that the convecting fluids in the Earth act somehow like the currents in wires. Exactly what happens isn't known, but it is felt pretty certain that it is connected with the core spinning and with its being liquid. Bodies that don't have a liquid core, the Moon and Mars, for instance, don't have magnetism. We know that the Earth's magnetic field changes in power from time to time. During the age of the dinosaurs, it was up to 3 times as strong as it is now. We also know that it reverses itself every 500,000 years or so on average, though that average hides a huge degree of unpredictability. The last reversal was about 750,000 years ago. Sometimes it stays put for millions of years. 37 million years appears to be the longest stretch. And at other times it is reversed after as little as 20,000 years. Altogether, in the last 100 million years, it has reversed itself about 200 times, and we don't have any real idea why. This has been called the greatest unanswered question in the geological sciences. We may be going through a reversal now. The Earth's magnetic field has diminished by perhaps as much as 6% in the last century alone. Any diminution in magnetism is likely to be bad news, because magnetism, apart from holding notes to refrigerators and keeping our compasses pointing the right way, plays a vital role in keeping us alive. Space is full of dangerous cosmic rays, which in the absence of magnetic protection would tear through our bodies, leaving much of our DNA in useless shreds. When the magnetic field is working, these rays are safely herded away from the Earth's surface and into two zones in near space called the Van Allen belts. They also interact with particles in the upper atmosphere to create the bewitching veils of light known as the auroras. A big part of the reason for our ignorance is that traditionally there has been little effort to coordinate what's happening on top of the Earth with what's going on inside it. According to Shauna Vogel, geologists and geophysicists rarely go to the same meetings or collaborate on the same problems. Perhaps nothing better demonstrates our inadequate grasp of the dynamics of the Earth's interior than how badly we are caught out when it plays up. And it would be hard to come up with a more salutary reminder of the limitations of our understanding than the eruption of Mount St. Helens in Washington State in 1980. At that time, the lower 48 states of the Union had not seen a volcanic eruption for over 65 years. Therefore, most of the government volcanologists called in to monitor and forecast St. Helens' behavior had seen only Hawaiian volcanoes in action, and they, it turned out, were not the same thing at all. St. Helens started its ominous rumblings on the 20th of March. Within a week it was erupting magma, albeit in modest amounts, up to 100 times a day, and being constantly shaken with earthquakes. People were evacuated to what was assumed to be a safe distance of 13 kilometers. As the mountain's rumblings grew, St. Helens became a tourist attraction for the world. Newspapers gave daily reports on the best places to get a view. Television crews repeatedly flew in helicopters to the summit, and people were even seen climbing over the mountain. On one day, more than 70 copters and light aircraft circled the peak. But as the days passed and the rumblings failed to develop into anything dramatic, people grew restless, and the view became general that the volcano wasn't going to blow after all. On the 19th of April, the northern flank of the mountain began to bulge conspicuously. Remarkably, no one in a position of responsibility saw that this strongly signaled a lateral blast. The seismologists resolutely based their conclusions on the behavior of Hawaiian volcanoes, which don't blow out sideways. Almost the only person who believed that something really bad might happen was Jack Hyde, a geology professor at a community college in Tacoma. He pointed out that St. Helens didn't have an open vent, as Hawaiian volcanoes have, so any pressure building up inside was bound to be released dramatically and probably catastrophically. However, Hyde was not part of the official team, and his observations attracted little notice. We all know what happened next. At 8:32 a.m. on a Sunday morning, 18th of May, the north side of the volcano collapsed, sending an enormous avalanche of dirt and rock rushing down the mountain slope at nearly 250 kilometers an hour. It was the biggest landslide in human history and carried enough material to bury the whole of Manhattan to a depth of 120 meters. A minute later, its flank severely weakened. St. Helens exploded with a force of 500 Hiroshima-sized atomic bombs, shooting out a murderous hot cloud at up to 1,050 kilometers an hour, much too fast, clearly, for anyone nearby to outrace it. Many people who were thought to be in safe areas, often far out of sight of the volcano, were overtaken. 57 people were killed. 23 of the bodies were never found. The toll would have been much higher had it not been a Sunday. On any weekday, many lumber workers would have been working within the death zone. As it was, people were killed 30 kilometers away. The luckiest person on that day was a graduate student named Harry Glicken. He had been manning an observation post 9 kilometers from the mountain, but he had a college placement interview on the 18th of May in California, and so had left the site the day before the eruption. His place was taken by David Johnston. Johnston was the first to report the volcano exploding. Moments later, he was dead. His body was never found. Glicken's luck, alas, was temporary. 11 years later, he was one of 43 scientists and journalists fatally caught up in a lethal outpouring of superheated ash, gases, and molten rock, what is known as a pyroclastic flow, at Mount Unzen in Japan, when yet another volcano was catastrophically misread. Volcanologists may or may not be the worst scientists in the world at making predictions, but they are without question the worst in the world at realizing how bad their predictions are. Less than 2 years after the Unzen catastrophe, another group of volcano watchers, led by Stanley Williams of the University of Arizona, descended into the rim of an active volcano called Galeras in Colombia. Despite the deaths of recent years, only 2 of the 16 members of Williams's party wore safety helmets or other protective gear. The volcano erupted, killing 6 of the scientists along with 3 tourists who had followed them, and seriously injuring several others, including Williams himself. In an extraordinarily unself-critical book called Surviving Galeras, Williams said he could only shake my head in wonder when he learned afterwards that his colleagues in the world of volcanology had suggested that he had overlooked or disregarded important seismic signals and behaved recklessly. How easy it is to snipe after the fact, to apply the knowledge we have now to the events of 1993, he wrote. He was guilty of nothing worse, he believed, than unlucky timing when Galeras behaved capriciously as natural forces are wont to do. I was fooled, and for that I will take responsibility, but I do not feel guilty about the deaths of my colleagues. There is no guilt. There was only an eruption. But to return to Washington. Mount St. Helens lost 400 meters of peak, and 600 square kilometers of forest were devastated. Enough trees to build 150,000 homes, or 300,000 according to some reports, were blown away. The damage was placed at $2.7 billion. A giant column of smoke and ash rose to a height of 18,000 meters in less than 10 minutes. An airliner some 48 kilometers away reported being pelted with rocks. 90 minutes after the blast, ash began to rain down on Yakima, Washington, a community of 50,000 people about 130 kilometers away. As you would expect, the ash turned day to night and got into everything, clogging motors, generators, and electrical switching equipment, choking pedestrians, blocking filtration systems, and generally bringing things to a halt. The airport shut down, and highways in and out of the city were closed. All this was happening, you will note, just downwind of a volcano that had been rumbling menacingly for 2 months. Yet Yakima had no volcano emergency procedures. The city's emergency broadcast system, which was supposed to swing into action during a crisis, did not go on the air because the Sunday morning staff did not know how to operate the equipment. For 3 days, Yakima was paralyzed and cut off from the world, its airport closed, its approach roads impassable. Altogether, the city received just over 1.5 centimeters of ash after the eruption of Mount St. Helens. Now bear that in mind, please, as we consider what a Yellowstone blast would do. 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 Chapter 15. Dangerous Beauty. In the 1960s, while studying the volcanic history of Yellowstone National Park, Bob Christensen of the United States Geological Survey became puzzled about something that oddly had not troubled anyone before. He couldn't find the park's volcano. It had been known for a long time that Yellowstone was volcanic in nature. That's what accounted for all its geysers and other steamy features. And the one thing about volcanoes is that they are generally pretty conspicuous. But Christensen couldn't find the Yellowstone volcano anywhere. In particular, what he couldn't find was a structure known as a caldera. Most of us, when we think of volcanoes, think of the classic cone shape of a Fuji or a Kilimanjaro, which is created when erupting magma accumulates in a symmetrical mound. These can form remarkably quickly. In 1943, at Paricutin in Mexico, a farmer was startled to see smoke rising from a patch on his land. In 1 week, he was the bemused owner of a cone 152 meters high. Within 2 years, it had topped out at almost 430 meters and was more than 800 meters across. Altogether, there are some 10,000 of these intrusively visible volcanoes on Earth, all but a few hundred of them extinct. But there is a second, less celebrated type of volcano that doesn't involve mountain building. These are volcanoes so explosive that they burst open in a single mighty rupture, leaving behind a vast subsided pit, the caldera, from a Latin word for cauldron. Yellowstone obviously was of this second type, but Christensen couldn't find the caldera anywhere. By coincidence, just at this time, NASA decided to test some new high-altitude cameras by taking photographs of Yellowstone, copies of which a thoughtful official passed on to the park authorities on the assumption that they might make a nice display for one of the visitor centers. As soon as Christensen saw the photos, he realized why he had failed to spot the caldera. Virtually the whole park, 9,000 square kilometers, was caldera. The explosion had left a crater nearly 65 kilometers across, much too huge to be perceived from anywhere at ground level. At some time in the past, Yellowstone must have blown up with a violence far beyond the scale of anything known to humans. Yellowstone, it turns out, is a supervolcano. It sits on top of an enormous hotspot, a reservoir of molten rock that begins at least 200 kilometers down in the earth and rises to near the surface, forming what is known as a superplume. The heat from the hotspot is what powers all of Yellowstone's vents, geysers, hot springs, and popping mud pots. Beneath the surface is a magma chamber that is about 72 kilometers across, roughly the same dimensions as the park, and about 13 kilometers thick at its thickest point. Imagine a pile of TNT about the size of an English county and reaching 13 kilometers into the sky to about the height of the highest cirrus clouds, and you have some idea of what visitors to Yellowstone are shuffling around on top of. The pressure that such a pool of magma exerts on the crust above has lifted Yellowstone and its surrounding territory about half a kilometer higher than they would otherwise be. If it blew, the cataclysm is pretty well beyond imagining. According to Professor Bill Maguire of University College London, you wouldn't be able to get within 1,000 kilometers of it while it was erupting. The consequences that followed would be even worse. Superplumes of the type on which Yellowstone sits are rather like martini glasses, thin on the way up, but spreading out as they near the surface to create vast bowls of unstable magma. Some of these bowls can be up to 1,900 kilometers across. According to current theories, they don't always erupt explosively, but sometimes burst forth in a vast continuous outpouring, a flood, of molten rock, as happened with the Deccan traps in India 65 million years ago. These covered an area of over 500,000 square kilometers and probably contributed to the demise of the dinosaurs. They certainly didn't help with their noxious outpourings of gases. Superplumes may also be responsible for the rifts that cause continents to break up. Such plumes are not all that rare. There are about 30 active ones on the Earth at the moment, and they are responsible for many of the world's best-known islands and island chains. Iceland, Hawaii, the Azores, Canaries, and Galapagos archipelagos, Little Pitcairn in the middle of the South Pacific, and many others. But apart from Yellowstone, they are all oceanic. No one has the faintest idea how or why Yellowstones ended up beneath the continental plate. Only two things are certain: that the crust at Yellowstone is thin, and that the world beneath it is hot. But whether the crust is thin because of the hot spot, or whether the hot spot is there because the crust is thin, is a matter of heated, as it were, debate. The continental nature of the crust makes a huge difference to its eruptions. Whereas the other supervolcanoes tend to bubble away steadily and in a comparatively benign fashion, Yellowstone blows explosively. It doesn't happen often, but when it does, you want to stand well back. Since its first known eruption 16.5 million years ago, it has blown up about 100 times. But the most recent 3 eruptions are the ones that get written about. The last eruption was 1,000 times as big as that of Mount St. Helens. The one before that was 280 times as big, and the one before that was so big nobody knows exactly how big it was. It was at least 2,500 times as big as St. Helens, but perhaps 8,000 times as monstrous. We have absolutely nothing to compare it to. The biggest blast in recent times was that of Krakatau in Indonesia in August 1883, which made a bang that reverberated around the world for 9 days and made water slosh as far away as the English Channel. But if you imagine the volume of ejected material from Krakatau as being about the size of a golf ball, then that from the biggest of the Yellowstone blasts would be the size of a sphere you could just about hide behind. On this scale, the Mount St. Helens eruption would be no more than a pea. The Yellowstone eruption of 2 million years ago put out enough ash to bury New York State to a depth of 20 meters, or California to a depth of 6 meters. This was the ash that made Mike Voorhees' fossil beds in eastern Nebraska. That blast occurred in what is now Idaho, but over millions of years, at a rate of about 2.5 centimeters a year, the Earth's crust has traveled over it, so that today it is directly under northwest Wyoming. The hot spot itself stays in one place, like an acetylene torch aimed at a ceiling. In its wake, it leaves the sort of rich volcanic plains that are ideal for growing potatoes, as Idaho's farmers long ago discovered. In another 2 million years, geologists like to joke, Yellowstone will be producing French fries for McDonald's, and the people of Billings, Montana will be stepping around geysers. The ash fall from the last Yellowstone eruption covered all or parts of 19 western states, plus parts of Canada and Mexico, nearly the whole of the United States west of the Mississippi. This, bear in mind, is the breadbasket of America, an area that produces roughly half the world's cereals. And ash, it is worth remembering, is not like a big snowfall that will melt in the spring. If you wanted to grow crops again, you would have to find some place to put all the ash. It took thousands of workers 8 months to clear 1.8 billion tons of debris from the 6.5 hectares of the World Trade Center site in New York. Imagine what it would take to clear Kansas. And that's not even to consider the climatic consequences. The last supervolcano eruption on Earth was at Toba, in northern Sumatra, 74,000 years ago. No one knows quite how big it was, but it was a whopper. Greenland ice cores show that the Toba blast was followed by at least 6 years of volcanic winter, and goodness knows how many poor growing seasons after that. The event, it is thought, may have carried humans right to the brink of extinction, reducing the global population to no more than a few thousand individuals. That would mean that all modern humans arose from a very small population base, which would explain our lack of genetic diversity. At all events, there is some evidence to suggest that for the next 20,000 years, the total number of people on Earth was never more than a few thousand at any time. That is, needless to say, a long time to spend recovering from a single volcanic blast. All this was hypothetically interesting until 1973, when an odd occurrence made it suddenly momentous. Water in Yellowstone Lake, in the heart of the park, began to run over the banks at the lake's southern end, flooding a meadow, while at the opposite end of the lake the water mysteriously flowed away. Geologists did a hasty survey and discovered that a large area of the park had developed an ominous bulge. This was lifting up one end of the lake and causing the water to run out at the other, as would happen if you lifted one side of a child's paddling pool. By 1984, the whole central region of the park, over 100 square kilometers, was more than a meter higher than it had been in 1924, when the park was last formally surveyed. Then, in 1985, the central part of the park subsided by 20 centimeters, about 8 inches. It now seems to be swelling again. The geologists realized that only one thing could cause this: a restless magma chamber. Yellowstone wasn't the site of an ancient supervolcano, it was the site of an active one. It was also at about this time that they were able to work out that the cycle of Yellowstone's eruptions averaged one massive blow every 600,000 years. The last one was 630,000 years ago. Yellowstone, it appears, is due. It may not feel like it, but you're standing on the largest active volcano in the world. Paul Doss, Yellowstone National Park geologist, told me soon after climbing off an enormous Harley-Davidson motorcycle and shaking hands when we met at the park headquarters at Mammoth Hot Springs early on a lovely morning in June. A native of Indiana, Doss is an amiable, soft-spoken, extremely thoughtful man who looks nothing like a National Park Service employee. He has a graying beard and hair tied back in a long ponytail. A small sapphire stud graces one ear. A slight paunch strains against his crisp Park Service uniform. He looks more like a blues musician than a government employee. In fact, he is a blues musician, harmonica. But he sure knows and loves geology. "And I've got the best place in the world to do it," he says, as we set off in a bouncy, battered four-wheel drive vehicle in the general direction of Old Faithful. He has agreed to let me accompany him for a day as he goes about doing whatever it is a park geologist does. The first assignment today is to give an introductory talk to a new crop of tour guides. Yellowstone, I hardly need point out, is sensationally beautiful, with plump, stately mountains, bison-specked meadows, tumbling streams, a sky-blue lake, wildlife beyond counting. It really doesn't get any better than this if you're a geologist, Doss says. You've got rocks up at Beartooth Gap that are nearly 3 billion years old, 3/4 of the way back to the Earth's beginning. And then you've got mineral springs here. He points at the sulphurous hot springs from which Mammoth takes its title, where you can see rocks as they're being born. And in between there's everything you could possibly imagine. I've never been any place where geology is more evident, or prettier. "So you like it?" I say. "Oh, no, I love it," he answers with profound sincerity. "I mean, I really love it here. The winters are tough and the pay's not too hot, but when it's good, it's just—" He interrupted himself to point out a distant gap in a range of mountains to the west, which had just come into view over a rise. The mountains, he told me, were known as the Gallatins. "That gap is 60 or maybe 70 miles across. For a long time, nobody could understand why that gap was there. And then Bob Christensen realized that it had to be because the mountains were just blown away. When you've got 60 miles of mountains just obliterated, you know you're dealing with something pretty potent. It took Christensen 6 years to figure it all out." I asked him what caused Yellowstone to blow when it did. "Don't know. Nobody knows. Volcanoes are strange things. We really don't understand them at all. Vesuvius in Italy was active for 300 years until an eruption in 1944, and then it just stopped. It's been silent ever since. Some volcanologists think that it is recharging in a big way, which is a little worrying because 2 million people live on or around it, but nobody knows." "And how much warning would you get if Yellowstone was going to go?" He shrugged. "Nobody was around the last time it blew, so nobody knows what the warning signs are. Probably you would have swarms of earthquakes and some surface uplift, and possibly some changes in the patterns of behavior of the geysers and steam vents, but nobody really knows. So it could just blow without warning?" He nodded thoughtfully. "The trouble," he explained, "is that nearly all the things that would constitute warning signs already exist in some measure at Yellowstone. Earthquakes are generally a precursor of volcanic eruptions, but the park already has lots of earthquakes, 1,260 of them last year. Most of them are too small to be felt, but they are earthquakes nonetheless. A change in the pattern of geyser eruptions might also be taken as a clue, he said, but these too vary unpredictably. Once the most famous geyser in the park was Excelsior Geyser. It used to erupt regularly and spectacularly to heights of 100 meters. But in 1888 it just stopped. Then in 1985 it erupted again, though only to a height of 25 meters. Steamboat Geyser is the biggest geyser in the world when it blows, shooting water 120 meters into the air, but the intervals between its eruptions have ranged from as little as 4 days to almost 50 years. If it blew today and again next week, that wouldn't tell us anything at all about what it might do the following week, or the week after, or 20 years from now, Doss says. The whole park is so volatile that it's essentially impossible to draw conclusions from almost anything that happens. Evacuating Yellowstone would never be easy. The park gets some 3 million visitors a year, mostly in the 3 peak months of summer. The park's roads are comparatively few, and they are kept intentionally narrow, partly to slow traffic, partly to preserve an air of picturesqueness, and partly because of topographical constraints. At the height of summer, it can easily take half a day to cross the park and hours to get anywhere within it. Whenever people see animals, they just stop wherever they are, Doss says. We get bear jams, we get bison jams, we get wolf jams. In the autumn of 2000, representatives from the U.S. Geological Survey and National Park Service, along with some academics, met and formed something called the Yellowstone Volcanic Observatory. 4 of these bodies were in existence already in Hawaii, California, Alaska, and Washington, but oddly there was none in the largest volcanic zone in the world. The YVO was not actually a thing so much as an idea, an agreement to coordinate efforts at studying and analyzing the park's diverse geology. One of its first tasks, Doss told me, was to draw up an earthquake and volcano hazards plan, a plan of action in the event of a crisis. There isn't one already? I said. Nope, afraid not, but there will be soon. Isn't that just a little tardy? He smiled. Well, let's just say that it's not any too soon. Once it is in place, the idea is that 3 people, Christensen in Menlo Park, California, Professor Robert B. Smith at the University of Utah, and Doss in the park, would assess the degree of danger of any potential cataclysm and advise the park superintendent. The superintendent would take the decision whether to evacuate the park. As for surrounding areas, there are no plans. You would be on your own once you left the park gates. Not much help if Yellowstone were going to blow in a really big way. Of course, it may be tens of thousands of years before that day comes. Doss thinks such a day may not come at all. Just because there was a pattern in the past doesn't mean that it still holds true, he says. There is some evidence to suggest that the pattern may be a series of catastrophic explosions, then a long period of quiet. We may be in that now. The evidence now is that most of the magma chamber is cooling and crystallizing. It is releasing its volatiles. You need to trap volatiles for an explosive eruption. In the meantime, there are plenty of other dangers in and around Yellowstone, as was made devastatingly evident on the night of the 17th of August, 1959, at a place called Hebgen Lake, just outside the park. At 20 minutes to midnight on that date, Hebgen Lake suffered a catastrophic quake. It was magnitude 7.5, not vast as earthquakes go, but so abrupt and wrenching that it collapsed an entire mountainside. It was the height of the summer season, though fortunately not so many people went to Yellowstone in those days as now. 80 million tons of rock, moving at more than 160 kilometers an hour, just fell off the mountain, traveling with such force and momentum that the leading edge of the landslide ran 120 meters up a mountain on the other side of the valley. Along its path lay part of the Rock Creek campground. 28 campers were killed, 19 of them buried too deep, ever to be found again. The devastation was swift, but heartbreakingly fickle. 3 brothers sleeping in one tent were spared. Their parents, sleeping in another tent beside them, were swept away and never seen again. A big earthquake, and I mean big, will happen sometime, Doss told me. You can count on that. This is a big fault zone for earthquakes. Despite the Hebgen Lake quake and the other known risks, Yellowstone didn't get permanent seismometers until the 1970s. If you needed a way to appreciate the grandeur and inexorability of geological processes, you could do worse than to consider the Tetons, the sumptuously jagged range that stands just to the south of Yellowstone National Park. 9 million years ago, the Tetons didn't exist. The land around Jackson Hole was just a high, grassy plain. But then a 64-kilometer-long fault opened within the Earth, and since then, about once every 900 years, the Tetons experience a really big earthquake, enough to jerk them another 2 meters higher. It is these repeated jerks over eons that have raised them to their present majestic heights of 2,000 meters. That 900 years is an average, and a somewhat misleading one. According to Robert B. Smith and Lee J. Siegel in Windows into the Earth, a geological history of the region, the last major Teton quake was somewhere between about 5,000 and 7,000 years ago. The Tetons, in short, are about the most overdue earthquake zone on the planet. Hydrothermal explosions are also a significant risk. They can happen any time, pretty much anywhere, and without any predictability. You know, by design, we funnel visitors into thermal basins, Doss told me after we had watched Old Faithful blow. It's what they come to see. Did you know there are more geysers and hot springs at Yellowstone than in all the rest of the world combined? I didn't know that. He nodded. 10,000 of them, and nobody knows when a new vent might open. We drove to a place called Duck Lake, a body of water a couple of 100 meters across. It looks completely innocuous, he said. It's just a big pond. But this big hole didn't used to be here. At some time in the last 15,000 years, this blew in a really big way. You'd have had several tens of millions of tons of earth and rock and superheated water blowing out at supersonic speeds. You can imagine what it would be like if this happened under, say, the parking lot at Old Faithful or one of the visitor centers. He made an unhappy face. Would there be any warning? Probably not. The last significant explosion in the park was at a place called Pork Chop Geyser in 1989. That left a crater about 5 meters across. Not huge by any means, but big enough if you happened to be standing there at the time. Fortunately, nobody was around, so nobody was hurt, but that happened without warning. In the very ancient past, there have been explosions that have made holes a mile across, and nobody can tell you where or when that might happen next. You just have to hope that you're not standing there when it does. Big rock falls are also a danger. There was a big one at Gardner Canyon in 1999, but again, fortunately, no one was hurt. Late in the afternoon, Doss and I stopped at a place where there was a rock overhang poised above a busy park road. Cracks were clearly visible. It could go at any time, Doss said thoughtfully. You're kidding, I said. There wasn't a moment when there weren't 2 cars passing beneath it, all filled with, in the most literal sense, happy campers. Oh, it's not likely, he added. I'm just saying it could. Equally, it could stay like that for decades. There's just no telling. People have to accept that there is risk in coming here. That's all there is to it. As we walked back to his vehicle to head back to Mammoth Hot Springs, Doss added, But the thing is, most of the time bad things don't happen. Rocks don't fall. Earthquakes don't occur. New vents don't suddenly open up. For all the instability, it's mostly remarkably and amazingly tranquil. Like the Earth itself, I remarked. Precisely, he agreed. The risks at Yellowstone apply to park employees as much as to visitors. Doss had got a horrific sense of that in his first week on the job 5 years earlier. Late one night, 3 young summer employees were engaging in an illicit activity known as hot potting, swimming or basking in warm pools. Though the park, for obvious reasons, doesn't publicize it, not all the pools at Yellowstone are dangerously hot. Some are extremely agreeable to lie in, and it was the habit of some of the summer employees to have a dip late at night, even though it was against the rules to do so. Foolishly, the threesome had failed to take a torch, which was extremely dangerous because much of the soil around the warm pools is crusty and thin, and one can easily fall through into a scalding vent below. In any case, as they made their way back to their dorm, they came across a stream that they had had to leap over earlier. They backed up a few paces, linked arms, and on the count of 3 took a running jump. In fact, it wasn't the stream at all, it was a boiling pool. In the dark, they had lost their bearings. None of the 3 survived. I thought about this the next morning as I made a brief call on my way out of the park at a place called Emerald Pool in the Upper Geyser Basin. Doss hadn't had time to take me there the day before, but I thought I ought at least to have a look at it, for Emerald Pool is a historic site. In 1965, a husband and wife team of biologists named Thomas and Louise Brock, while on a summer study trip, had done a crazy thing. They had scooped up some of the yellowy-brown scum that rimmed the pool and examined it for life. To their, and eventually the wider world's deep surprise, it was full of living microbes. They had found the world's first extremophiles, organisms that could live in water that had previously been assumed to be much too hot or acid or choked with sulfur to bear life. Emerald Pool, remarkably, was all these things. Yet at least 2 types of living things, Sulfolobus acidocaldarius and Thermophilus aquaticus, as they became known, found it congenial. It had always been supposed that nothing could survive above temperatures of 50 degrees Celsius. But here were organisms basking in rank, acidic waters nearly twice that hot. For almost 20 years, one of the Brock's 2 new bacteria, Thermophilus aquaticus, remained a laboratory curiosity, until a scientist in California named Carrie B. Mullis realized that heat-resistant enzymes within it could be used to create a bit of chemical wizardry, known as a polymerase chain reaction, which allows scientists to generate lots of DNA from very small amounts, as little as a single molecule in ideal conditions. It's a kind of genetic photocopying, and it became the basis for all subsequent genetic science, from academic studies to police forensic work. It won Mullis the Nobel Prize in Chemistry in 1993. Meanwhile, scientists were finding even hardier microbes, now known as hyperthermophiles, which demand temperatures of 80 degrees Celsius or more. The warmest organism found so far, according to Francis Ashcroft in Life at the Extremes, is Pyrolobus fumarii, which dwells in the walls of ocean vents, where the temperature can reach 113 degrees Celsius. The upper limit for life is thought to be about 120 degrees Celsius, though no one actually knows. At all events, the Brock's findings completely changed our perception of the living world. As NASA scientist Jay Bergstrahl has put it, wherever we go on Earth, even into what seemed like the most hostile possible environments for life, as long as there is liquid water and some source of chemical energy, we find life. Life, it turns out, is infinitely more clever and adaptable than anyone had ever supposed. This is a very good thing, for as we are about to see, we live in a world that doesn't altogether seem to want us here. Part 5. Life Itself. The more I examine the universe and study the details of its architecture, the more evidence I find that the universe, in some sense, must have known we were coming. Freeman Dyson. Chapter 16. Lonely Planet. It isn't easy being an organism. In the whole universe, as far as we yet know, there is only one place
an inconspicuous outpost of the Milky Way called the Earth that will sustain you, and even it can be pretty grudging. From the bottom of the deepest ocean trench to the top of the highest mountain, the zone that covers nearly the whole of known life is only around 20 kilometers thick. Not much when set against the roominess of the cosmos at large. For humans, it is even worse, because we happen to belong to the portion of living things that took the rash but venturesome decision 400 million years ago to crawl out of the seas and become land-based and oxygen-breathing. In consequence, no less than 99.5% of the world's habitable space by volume, according to one estimate, is fundamentally, in practical terms completely, off-limits to us. It isn't simply that we can't breathe in water, but that we couldn't bear the pressures. Because water is about 1,300 times heavier than air, pressures rise swiftly as you descend, by the equivalent of 1 atmosphere for every 10 meters of depth. On land, if you rose to the top of a 150-meter eminence, Cologne Cathedral or the Washington Monument, say, the change in pressure would be so slight as to be indiscernible. At the same depth under water, however, your veins would collapse and your lungs would compress to the approximate dimensions of a Coke can. Amazingly, people do voluntarily dive to such depths without breathing apparatus for the fun of it, in a sport known as free diving. Apparently, the experience of having your internal organs rudely deformed is thought exhilarating, though not presumably as exhilarating as having them return to their former dimensions upon resurfacing. To reach such depths, however, divers must be dragged down, and quite briskly, by weights. Without assistance, the deepest anyone has gone and lived to talk about it afterwards is 72 meters, a feat performed by an Italian named Umberto Pellizzari, who in 1992 dived to that depth, lingered for a nanosecond, and then shot back to the surface. In terrestrial terms, 72 meters is a good bit shorter than a football pitch, so even in our most exuberant stunts, we can hardly claim to be masters of the abyss. Other organisms do, of course, manage to deal with the pressures at depth, though quite how some of them do so is a mystery. The deepest point in the ocean is the Mariana Trench in the Pacific. There, some 11.3 kilometers down, the pressures rise to over 16,000 pounds per square inch. We have managed just once, briefly, to send humans to that depth in a sturdy diving vessel, yet it is home to colonies of amphipods, a type of crustacean similar to shrimp but transparent, which survive without any protection at all. Most oceans are, of course, much shallower, but even at the average ocean depth of 4 kilometers, the pressure is equivalent to being squashed beneath a stack of 14 loaded cement trucks. Nearly everyone, including the authors of some popular books on oceanography, assumes that the human body would crumple under the immense pressures of the deep ocean. In fact, this appears not to be the case. Because we are made largely of water ourselves, and water is virtually incompressible, in the words of Francis Ashcroft of Oxford University, the body remains at the same pressure as the surrounding water and is not crushed at depth. It is the gases inside your body, particularly in the lungs, that cause the trouble. These do compress, though at what point the compression becomes fatal is not known. Until quite recently, it was thought that anyone diving to 100 meters or so would die painfully, as his or her lungs imploded or chest wall collapsed, but the free divers have repeatedly proved otherwise. It appears, according to Ashcroft, that humans may be more like whales and dolphins than had been expected. Plenty else can go wrong, however. In the days of diving suits, the sort that were connected to the surface by long hoses, divers sometimes experienced a dreaded phenomenon known as the squeeze. This occurred when the surface pumps failed, leading to a catastrophic loss of pressure in the suit. The air would leave the suit with such violence that the hapless diver would be, all too literally, sucked up into the helmet and hosepipe. When hauled to the surface,
All that is left in the suit are his bones and some rags of flesh, the biologist J.B.S. Haldane wrote in 1947, adding for the benefit of doubters, "This has happened." Incidentally, the original diving helmet, designed in 1823 by an Englishman named Charles Deane, was intended not for diving, but for firefighting. It was called a smoke helmet, but being made of metal, it was hot and cumbersome. As Deane soon discovered, firefighters had no particular eagerness to enter burning structures in any form of attire, but most especially not in something that heated up like a kettle and made them clumsy into the bargain. In an attempt to save his investment, Deane tried it under water and found it was ideal for salvage work. The real terror of the deep, however, is the bends. Not so much because they are unpleasant, though of course they are, as because they are so much more likely. The air we breathe is 80% nitrogen. Put the human body under pressure, and that nitrogen is transformed into tiny bubbles that migrate into the blood and tissues. If the pressure is changed too rapidly, as with a too quick ascent by a diver, the bubbles trapped within the body will begin to fizz in exactly the manner of a freshly opened bottle of champagne, clogging tiny blood vessels, depriving cells of oxygen, and causing pain so excruciating that sufferers are prone to bend double in agony, hence the bends. The bends have been an occupational hazard for sponge and pearl divers since time immemorial, but didn't attract much attention in the Western world until the 19th century, and then it was among people who didn't get wet at all, or at least not very wet, and not generally much above the ankles. They were caisson workers. Caissons were enclosed dry chambers built on riverbeds to facilitate the construction of bridge piers. They were filled with compressed air, and often, when the workers emerged after an extended period of working under this artificial pressure, they experienced mild symptoms like tingling or itchy skin. But an unpredictable few felt more insistent pain in the joints, and occasionally collapsed in agony, sometimes never to get up again. It was all most puzzling. Sometimes the workers would go to bed feeling fine, but wake up paralyzed. Sometimes they wouldn't wake up at all. Ashcroft relates a story concerning the directors of a new tunnel under the Thames, who held a celebratory banquet as the tunnel neared completion. To their consternation, their champagne failed to fizz when uncorked in the compressed air of the tunnel. However, when at length they emerged into the fresh air of a London evening, the bubbles sprang instantly to fizziness, memorably enlivening the digestive process. Apart from avoiding high-pressure environments altogether, only two strategies are reliably successful against the bends. The first is to suffer only a very short exposure to the changes in pressure. That is why the free divers I mentioned earlier can descend to depths of 150 meters without ill effect. They don't stay down long enough for the nitrogen in their system to dissolve into their tissues. The other solution is to ascend by careful stages. This allows the little bubbles of nitrogen to dissipate harmlessly. A great deal of what we know about surviving at extremes is owed to the extraordinary father and son team of John Scott and J.B.S. Haldane. Even by the demanding standards of British intellectuals, the Haldanes were outstandingly eccentric. The senior Haldane was born in 1860 to an aristocratic Scottish family. His brother was Viscount Haldane, but spent most of his career in comparative modesty as a professor of physiology at Oxford. He was famously absent-minded. Once, after his wife had sent him upstairs to change for a dinner party, he failed to return, and was discovered asleep in bed in his pajamas. When roused, Haldane explained that he had found himself disrobing and assumed it was bedtime. His idea of a holiday was to travel to Cornwall to study hookworm in miners. Aldous Huxley, the novelist grandson of T.H. Huxley, who lived with the Haldanes for a time, parodied him, a touch mercilessly, as the scientist Edward Tantamount in the novel Point Counterpoint. Haldane's gift to diving was to work out the rest intervals necessary to manage an ascent from the depths without getting the bends. But his interests ranged across the whole of physiology, from studying altitude sickness to the problems of heat stroke in desert regions. He had a particular interest in the effects of toxic gases on the human body. To understand more exactly how carbon monoxide leaks killed miners, he methodically poisoned himself, carefully taking and measuring his own blood samples the while. He quit only when he was on the verge of losing all muscle control, and his blood saturation level had reached 56%, a level, as Trevor Norton notes in his entertaining history of diving Stars Beneath the Sea, only fractionally removed from nearly certain lethality. Haldane's son Jack, known to posterity as JBS, was a remarkable prodigy who took an interest in his father's work almost from infancy. At the age of 3, he was overheard demanding peevishly of his father, "But is it oxyhemoglobin or carboxyhemoglobin?" Throughout his youth, the young Haldane helped his father with experiments. By the time he was a teenager, the two often tested gases and gas masks together, taking it in turns to see how long it took them to pass out. Though JBS Haldane never took a degree in science, he studied classics at Oxford. He became a brilliant scientist in his own right, mostly working for the government at Cambridge. The biologist Peter Medawar, who spent his life around mental Olympians, called him the cleverest man I ever knew. Huxley parodied the younger Haldane, too, in his novel Antic Hay, but also used his ideas on genetic manipulation of humans as the basis for the plot of Brave New World. Among many other achievements, Haldane played a central role in marrying Darwinian principles of evolution to the genetic work of Gregor Mendel, to produce what is known to geneticists as the modern synthesis. Perhaps uniquely among human beings, the younger Haldane found the First World War a very enjoyable experience, and freely admitted that he enjoyed the opportunity of killing people. He was himself wounded twice. After the war, he became a successful popularizer of science and wrote 23 books, as well as over 400 scientific papers. His books are still thoroughly readable and instructive, though not always easy to find. He also became an enthusiastic Marxist. It has been suggested, not altogether cynically, that this was out of a purely contrarian instinct, and that if he had been born in the Soviet Union, he would have been a passionate monarchist. At all events, most of his articles first appeared in the Communist Daily Worker. Whereas his father's principal interests concerned miners and poisoning, the younger Haldane became obsessed with saving submariners and divers from the unpleasant consequences of their work. With Admiralty funding, he acquired a decompression chamber that he called the pressure pot. This was a metal cylinder into which 3 people at a time could be sealed and subjected to tests of various types, all painful and nearly all dangerous. Volunteers might be required to sit in ice water while breathing aberrant atmosphere, or subjected to rapid changes of pressurization. In one experiment, Haldane himself simulated a dangerously hasty ascent to see what would happen. What happened was that the dental fillings in his teeth exploded. Almost every experiment, Norton writes, ended with someone having a seizure, bleeding, or vomiting. The chamber was virtually soundproof, so the only way for occupants to signal unhappiness or distress was to tap insistently on the chamber wall, or to hold up notes to a small window. On another occasion, while poisoning himself with elevated levels of oxygen, Haldane had a fit so severe that he crushed several vertebrae. Collapsed lungs were a routine hazard. Perforated eardrums were quite common, too. But as Haldane reassuringly noted in one of his essays, the drum generally heals up, and if a hole remains in it, although one is somewhat deaf, one can blow tobacco smoke out of the ear in question, which is a social accomplishment. What was extraordinary about this was not that Haldane was willing to subject himself to such risk and discomfort in the pursuit of science, but that he had no trouble talking colleagues and loved ones into climbing into the chamber, too. Sent on a simulated descent, his wife once had a fit that lasted 13 minutes. When at last she stopped bouncing across the floor, she was helped to her feet and sent home to cook dinner. Haldane happily employed whoever happened to be around, including on one memorable occasion a former Prime Minister of Spain, Juan Negrin. Dr. Negrin complained afterwards of minor tingling and a curious velvety sensation on the lips, but otherwise seems to have escaped unharmed. He may have considered himself very lucky. A similar experiment with oxygen deprivation left Haldane without feeling in his buttocks and lower spine for 6 years. Among Haldane's many specific preoccupations was nitrogen intoxication. For reasons that are still poorly understood, at depths beyond about 30 meters, nitrogen becomes a powerful intoxicant. Under its influence, divers had been known to offer their air hoses to passing fish, or to decide to try to have a smoke break. It also produced wild mood swings. In one test, Haldane noted, the subject alternated between depression and elation, at one moment begging to be decompressed because he felt bloody awful, and the next minute laughing and attempting to interfere with his colleague's dexterity test. In order to measure the rate of deterioration in the subject, a scientist had